Okay, good morning, dear colleagues. I suggest that we slowly start. We are very happy to see that many people relatively early in the morning after, I guess many people had a great evening yesterday. So it is our great pleasure to have our third keynote speaker, Professor Samuel Horvath. Samuel currently working in Mohammed bin Zayed University of Artificial Intelligence in Abu Dhabi. And before that, he did his PhD in Saudi Arabia in AIST'. And Sam is a very well-known expert on distributed and federated learning, and he will be talking exactly on some aspects of these topics today. So Sam, go ahead.
Right, thank you, Maxim, for a very generous introduction, and thanks to all organizers for inviting me. So what I want to talk about today is federated learning, and let me just briefly discuss outline of my talk. So first, what I'll try to do, I'll try to give you some kind of like a gentle introduction to what we mean by federated learning and how it developed. Then I'm going to discuss several practical and research challenges that kind of needs to be addressed in order to deploy federated learning in real-world scenarios. And then I'm going to talk a bit about our recent work that we did on decomposable models that are targeted to face some of the challenges of the federated learning. All right, so let me start with the motivation of why we do federated learning. So if we look at kind of like a traditional machine learning, so originally what we did, you would have a single machine, you would just kind of put all your data in and try to train your machine learning model. But as we kind of progressed, what we see that essentially this models gets bigger and they require more and more data. So therefore we moved from local solutions to cloud-based solutions. Now, the thing with that is, like with this ever-increasing data collection, what we have to consider is that majority of those data comes from clients that might have, and that data collection might have some negative privacy implication of these data collections. On top of that, many countries do have different privacy initiatives, such as GDPR in the European Union, or there is CCPA in the US that essentially kind of forbids direct data collections. So with this in mind, essentially, if we want to further progress machine learning by collecting ever more data, that might not be kind of standard solution, might not be the feasible solution, because not respecting those privacy initiatives, we can almost completely lose the access to the data. Now, this is where federated learning kind of comes to save us by bringing training actually to the edge, so to those clients that own data. And the main premise of federated learning is following. So we do assume that we have some orchestrator. Okay, so I'll just point here if that works. Yeah, so we have some orchestrator who orchestrates the whole training process. And what it asks those clients to do, it asks them to compute some kind of like updates to the model when we do training. And those updates are supposed to be very focused, and they are intended for immediate aggregation. So essentially this orchestrator, or you can think about it as a central server, only sees the aggregated information in order to prevent any data leakage. So therefore, kind of federated learning is kind of its basic definition. What it gives us at least a hope to train on this large decentralized data sets. On top of that, there is an increasing demand to have something what's called data locality paradigm, meaning that the data should be processed where they were actually collected. And on top of that, there are several recent studies that show that when you care about the carbon footprint of your model, then if you design your federated learning algorithm well, then you actually have a lower carbon footprint when compared to standard centralized learning. So some of the kind of success stories of federated learning, so where is already commercially applied. This is in the big industry players. For instance, Apple have it in their Hey Siri or QuickType. Google uses kind of the same thing for Hey Google and Gboard. Then where we see this kind of a federated learning as a next game changer. So this is pretty much all applications that historically wouldn't have much of a data. And the reason for that would be like very strong privacy constraints. This might be, let's say, like smart health applications. There are already several startups working on that, such as Doc.ai or Oken, and also a lot in fintech applications where essentially privacy is a key. And there are several banks already working on that, how to do kind of decentralized fraud detection, for instance, WeBank. And I mean, the thing is, like the applications of federated learning, you can think about that as essentially any machine learning task that you would like to do, but you have to collect a lot of private data. The good thing about machine learning and why it's kind of getting more and more widespread is several open source frameworks for federated learning. There is, among the most popular, you have a Flower, FedML, also Meta has its own federated learning simulator, same for Microsoft, and also quite popular is the NVIDIA Flare, which is the SDK for federated learning. I'll also do a bit of an advertisement. So when you're looking for the resource to get to know more about like recent research about federated learning, so we've been running for, I think, roughly 3 years, so ever since COVID, we are running the online seminar where we have more than 100 talks about different kind of aspects of federated learning. They're all on YouTube. So if you are interested, just Google Flow Seminar, register, and you will have access to all the talks that we had. And also, some of the great resources are some recent review articles, or there is even a recent book on federated learning as well. All right, so when we talk about federated learning, there are two main settings that we usually consider. So first is something called cross-silo federated learning. And what we have in cross-silo federated learning, we have different organizations. You can think about them as a kind of a big organizations that want to collaborate. For instance, the example that I have here are hospitals that have a patient records. They would like to train some smart health assistants based on all of these records. But we have to realize that the data are private. So what you kind of care about here the most is the privacy of the data. So, and here what we usually assume that the kind of a number of the institutions that try to collaborate is relatively small. And the main thing that we would care about in this setup is privacy. So the setting that I will consider more in this talk is cross-device federated learning. So in cross-device federated learning, what we have, so all those clients that we have are devices. You can think about them as mobile devices or different IoT devices, and they want to collaborate in order to solve some machine learning problem. You can think about that as a recommendation problem where the whole process is orchestrated by a central server. You can this one you can think about as a provider, and what's their goal? What's their goal is to train this model in this federated way where we only communicate the very focused updates that are intended for immediate aggregation. And also one other thing that we have to respect here, that this is all trained within those devices, and also the model that we eventually going to obtain is going to be deployed for those devices. And one of the kind of main challenge here is essentially like different heterogeneity that comes with the client, and also the fact that the number of clients, you can think about that as a number of phones that might be in millions or hundreds of millions. All right, and that brings me to this kind of second part of the talk, where I would like to discuss challenges that essentially makes, or challenges that if we can address those, we would be able to make federated learning practical. So the first one, and one of the most prevalent one, is the communication bottleneck. So for those of you, so the example that I list here is for distributed training. So for those of you who are familiar with this, we know that essentially just by adding more and more GPUs, that doesn't necessarily lead to this perfect linear scaling. And the reason for that is at some point what you're going to hit is the fact that communication is actually much slower than computation. So for instance, I have in this example right here, what you have is essentially if you run, let's say, DeepLight, which is a very communication heavy model on 8P100s with still relatively fast network, then what you're going to end up with is that essentially more than 90% of your training time going to be spent on communication. And in many applications, this would be the major limiting factor. Now, if we move to federated learning, now here, this issue is even more prevalent because now we do not have those machines, those clients being in a single data centers. The issue is that they are all connected through some wireless links or some other end user internet connections, and this would be even slower than the data center links. Also, on top of that, you operate in a system where you have actually a lot of clients, so even the kind of the capacity to aggregate those updates becomes the bottleneck. And especially what we see in the real world application is that like the model download is still kind of a slow. So when the clients download the model from the master or from the orchestrator, but then the uploading is the key limitation of the system. So thankfully, there are several remedies that one can employ. So you can think about the communication compression, which means that essentially those updates from the client before they are sent back for the aggregation, they're actually compressed. And there is a nice line of research linking this, that if you design your compression very well, you can essentially add more privacy into the systems. Then another possibilities are that essentially you do not communicate very often. What you can do, you can try to define the local problem that is some kind of harder than just giving the local update. By local update, you can think about just computing the gradient with respect to your local data, but you're going to do kind of more local work such that you reduce the amount of communication. Or what you can try to do in some smart way, you can try to limit the number of devices that will communicate. And what that smart way might be, you can think about like how to kind of figure out which clients might have updates that are more important than others, but still respecting the privacy of the clients. Now, another issue, and that's something that we're going to look at later more in detail, is the system heterogeneity. So the thing with system heterogeneity is, like when you train in this federated network, a lot of the clients might be either unreliable or very heterogeneous. So, and this vast heterogeneity is also one of the key challenges when you want to deploy and train these models in kind of in this wild. So remedies that you can here incorporate is try to kind of devise the algorithms that would be strugglers resilient, meaning that like if you have some clients that kind of fall behind the training schedule, you can still allow them to update the global model later. Also very popular here is the asynchronous updates, but here the challenge with the asynchronous updates is that usually kind of once you have asynchronous updates, it's much harder to guarantee privacy. Or another thing is like when you have the devices that are not able to compute and even like store with, or work with the model, then you can just simply drop them. All right, another challenge that also quite prevalent with federated learning and maybe not very standard in standard centralized learning is client availability. So when we talk about this cross-device federated learning, what is the standard consideration is that in order not to reduce the user experience, you only participate in training when you are connected to fast network. Also, you're connected to the charger. And also with you, there is a large number of devices connected because we want to kind of hide your updates such that your privacy doesn't suffer. And with this, essentially, it creates quite non-trivial constraints, and with that, you have actually a lot of variations that might be undesired, meaning that they actually can kind of break your optimization algorithm, and this is something that needs to be addressed. Another issue with generally, like with deploying federated learning systems onto devices is the fact that like systems are really not very mature. So for instance, kind of what's already happening for quite a long time is actually on-device inference. So that's already deployed in many devices, but the full kind of federated learning loop is still kind of a work in progress, but it's we are kind of moving towards there. And nowadays there is actually a couple of providers already allow to run like a forward and backward on the devices. Another issue is the issue of limited labels. So while we do have, like when you think about your mobile phone, like you do have a lot of, let's say, text, a lot of photos that maybe we can train on, but the thing with that is there's very few labels. And that's, for instance, one reason if we would go back to kind of these first applications, which was next word predictions, for instance, for Gboard. The thing is, there you don't need labels, and this is why kind of the first applications of federated learning was for next word prediction. Now, so line of work that people are looking at is how to incorporate semi-supervised learning while exploiting the data structure within the federated learning, how to actually incentivize clients to label data, and then we can talk about personalization. So now the first thing about federated learning is that we might be actually training on very different kind of, within the clients, we might have very different subset of data. And then the question is whether the kind of a global model, which is kind of standard way of doing federated learning, is the right thing to do. So with, let's say, when we look at this application right here, which would be next word prediction, that's very much depend on the context and of the user. So here, that would be not a case. So what the so kind of a possible direction for the research and things that people are looking at is how to incorporate kind of a meta-learning approaches into federated learning. There's actually a lot of work on trying to kind of link federated learning and meta-learning together, and also how to kind of discover kind of interesting structures within our kind of a federated network by looking at the clustering or some kind of a balance between local and global model, where by local you mean you kind of think, you can think about that as a model that trained purely on the kind of a distribution of the data that you only see locally, and globally that would be the global distribution. And another kind of popular subset of the federated learning is split learning. Another kind of a very important issue that maybe was not discussed at kind of the rise of the federated learning or when it was originally introduced is privacy guarantees. So the thing with this is, while we have by construction that the data, they actually never leave the device, we do not have any formal guarantees that from the updates that we sent, even though they are aggregated and there's like a lot of techniques to make them kind of private, we do not have, or we did not have originally, formal guarantees that federated learning does not introduce any privacy loss. And also when you think about that, essentially you cannot have zero privacy loss if you have the learning. So, and then also there was a couple of works that essentially showed that even when you do federated learning in a very in a way that you try to have very focused updates, you average or aggregate over many clients, still, if you're smart, then privacy leaks are possible. And this is where remedies such as general cryptography comes. So that's more like a kind of having a system more safe. But when we talk about true privacy of the client, that's where differential privacy pops up. And for those of you who are not familiar with differential privacy, what differential privacy generally says, that kind of the informal definition is that if I train the model and if you use my data or do not use my data, the actually output of that model doesn't change much. And by how much change, that's essentially like, but by the upper bound, how much it can change, that's the guarantee that you have in respect of differential privacy. Now, another issue that comes with federated learning is that essentially we can think about federated learning as a collaboration among many and potentially mutually untrusted clients. So it's very easy target for poisoning, and you can think about that essentially because everything is open, you might have a competition, people might be training the similar model, so there is incentive to kind of destroy your competitive model. So when designing the federated learning algorithm that you're going to deploy in a while, you have to be aware of that. And but thankfully, so in order to kind of prevent that, there are several defense mechanisms that can at least remedy these poisoning attacks. Now, the last thing that I want to discuss is about the challenges, is this incentives to participate. So when we think about like, why would I even kind of give you my data to participate in this like federated learning training, that's something that has to be somehow clearly defined, also with respect to label. So for instance, like your model would improve if I labeled the data, but why would I do that? Also, with a local training, there is a cost incurred with like energy, privacy, and so on. And also another, like the last issue is also whether I do even benefit from the federation. Now also, that's kind of from the point of a client, but from the point of this kind of orchestrator, we also would like to know like what's your contribution. So do you even contribute to federation? Like by not having your data, do I have any benefit? Another issues comes with like the ownership of the model. So who actually like owns the model? Is it the community or is it some kind of this global service provider? And this actually opens up a very interesting question, especially if you work on economics. So in general, we already have kind of when we talk about these three edges, which is computer science, economic, and statistics, we have already like a lot of discipline when it comes to the intersection of two, such as the economics plus computer science would be algorithmic game theory. Then statistics with computer science is essentially the basics of machine learning. Statistics plus econometrics, statistics plus econometrics. But the thing is, when we look in the middle, so this is where we kind of see the federated or collaborative learning when addressing all of these issues. So with this, I hope that I at least a bit persuade you that federated learning presents kind of a new realm of unique, complex challenges. When we want to overcome these, we must devise some kind of a system-aware, efficient optimization techniques. And the key area to focus is optimization theory, networking, and scheduling techniques. And with this, in the hope that these techniques will help streamline this data processing and improve our performance, and therefore enhance the overall effectiveness of federated learning models. All right, so that was kind of that was the first part, and now the second part that I want to focus on is this decomposable models. Now, with this, I would like to start with the motivation. So our motivation comes from like a very popular linear algebra techniques that are widely used in machine learning, such as principal component analysis and singular value decompositions. So why these are very popular? Because they can give you dimensionality reduction, noise reduction, you can extract features, and also you can significantly improve your computational efficiency. And now the question that we start with is whether we can make kind of a PCA or SVD version of neural networks. So in order to answer that question, let me first kind of try to look at the SVD, how we could potentially represent that as a neural network. So if you look at this decomposition right here, then how we can have it as a neural network is we can consider the neural network that has one hidden layer without any activation, without any bias. That would essentially represent this mapping. Now, the nice thing that you can note about that is, like, if we do this kind of a pruning within this hidden layer, then what you can get the singular value, the SVD, but the reduced SVD, where we only keep the first, let's say here, 2 singular vectors, and so on and so forth. Now, so this at least kind of gives us the good example that kind of we can represent this matrix factorization within the neural networks. Now, maybe the most interesting part is whether we can actually learn this. And the thing is that we can, so if we just define kind of general matrix decomposition, we can define it as a following optimization problem. Now, if you want to retransform it into SVD, then what you can, SVD would essentially solve this problem individually for each kind of each rank K. So here, this one means the first K columns of matrix U. Now, the nice thing with that, you can even put it all together. So you can have it as a summation across all the ranks. Summation, the nice thing about summation you can represent with like an expectation. And once you see this, and you're already kind of familiar with what we do when we have like many terms in machine learning, what you can do, you can just simply apply SGD, and that leads to our construction of what we call the order dropout. So essentially what we show that essentially if you define your problem in this way, you apply SGD, but SGD not in the data points, you essentially like apply SGD to the models, then you can actually learn SVD with a standard kind of machine learning training loop. And also the nice thing about that, if you're kind of interested in optimization, you can still see this problem as an overparameterized problem, although even it's kind of a not, but because the gradient at the optimum, even for each subproblems, are 0. Now, how does this look in practice? So in practice, what we do is, like, if we will about to learn the, let's say, like SVD, so we would apply this, our order dropout techniques in the hidden layer, and what in each step we do, we have some distribution over the width. In each step, we sample the width, and that's the number of neurons that we keep. So essentially, that's why we call it dropout, and order dropout because it's preserved the natural order of the neurons. Now, the nice thing about that is that here you can recover, with this construction, as I saw, you can recover SVD as a special case. So for SVD, if you have your mapping between the data and the output to be linear, and then you sample your data from the uniform ball, that essentially you can say that the training loop, like the standard training loop with this network, with order dropout, recover SVD as a special case, and that's what I have here. So essentially you see that across any of these like submatrices, so here that would be essentially this rank K matrix, that it converges to the best K rank approximation of the matrix A within the single loop. And it's also within the sampling. So we do not need to evaluate with respect to every single matrix, but we can just sample one at a time. Now also, you can recover PCA with this in this very kind of a similar scenario, where the only difference is that now I'm going to sample uniformly at random from my data set, but the thing is the mapping between the features and the labels, essentially that's the same thing here. And what you can see, so here the example that we have here is we only have the data to come from like the 3-dimensional space, and you can see that quickly the network discovers that and essentially provides you this with this 3 principal components and zero out the rest. Okay, and then in general case, I'm not going to discuss much about that, but essentially, if we talk about this general case for these linear networks, that is something in between. What it does is essentially does PCA on the transform data set by that mapping A. Now, how do we generalize that to neural networks? That essentially comes or boils down to these two works that I'm going to present. So first is titled Fair and Accurate Federated Learning on the Heterogeneous Targets, where we're going to use the order dropout. And this is essentially the work where we introduce this notion of order dropout. So first, let me acknowledge my collaborators here, Steve, Mario, Stelios, Ilias, and Nick. So just to remind you, the problem that we're trying to solve here is we're trying to look at heterogeneous devices. So we want to address the issue of having different tiers of devices within our training. But we do want to avoid this kind of a standard construction where when you look at federated loop in general, that the widely accepted norm is that the model that you have, so all the local models, everything that you're going to deploy has to have exactly the same architecture with the global model. So, and in order to achieve that, you can drop low-tide devices or essentially limit the global model size in order to accommodate all your clients. Now, the drawbacks of those approaches that I just discussed is, first, when you drop low-tide devices, you might have very limited participation. And also, now, federated learning as kind of training on a very, also not just like heterogeneous devices, but very heterogeneous data. So by dropping low-tide devices, you actually might lose a very important part of your data set. And therefore have a lot of bias due to unseen data. Also, by limiting the global model size, you might actually degrade performance for high-tier devices. Now, what will be our goals and what we want to achieve with this work is we want to have a fairness in participation, meaning that every single client can participate. And also, we want to have very competitive performance, meaning that all devices should have as good performance as possible, considering their local or network constraints. Now, how do we achieve that? So, I mean, very kind of naive way is first, we're just going to simply drop this assumption that every single client needs to run or store the same global model. And what we're going to do is, for these lower tier devices, we're going to deploy the thinner models. I'll show you how we do it later, where the model, the width that we're going to deploy will depend dynamically on the local network and network constraints. That's might be memory, computational capabilities, load, battery level, or let's say limited bandwidth. So, and how do we achieve that? It's exactly through the order dropout that I just discussed. So here, so if we have a general network as the one on the left, then what we can do is we can apply our order dropout technique in the following way. So what we're going to do, we define a set of relative submodel width. So these are numbers between 0 and 1. And we define distribution over those width. And what we're going to do in each step, we're going to sample from that distribution. And based on the width, we're going to kind of apply that width limitation into every layer, but the input and output layer to keep the structure of the network unchanged. Now, just to give you kind of a brief motivation or the how this relates to kind of a standard random dropout. So for order dropout, the motivation is not necessarily only regularization, but the motivation is that once we apply this technique, we kind of enforce as much knowledge as possible towards the left of the network, while the standard random dropout, the motivation is to prevent codependence of the neurons. And also another kind of a difference between the random dropout and order dropout is that our inference is exact, while random dropout has inexact inference where you kind of where you just approximate the ensemble with a simple average of weights. So those are kind of the main differences. Now, just to show you like one example, so consider this is our network right here. So we have the sampling, let's say that sampling sample 0.4. That means we keep 40% of each hidden layer, and which here yields 2 neurons per each hidden layer that we consider. And then once we're going to deploy or train, then we can accommodate the width of the network based on the tier of the device that we are about to deploy to. Now, how do we apply this into kind of a federated learning training loop? So the construction is following. So we have a set of our devices. What we're going to first we take the architecture. We take a set of the width that we want to train on our model, and also the distribution of the width that we want to sample from. Here example is, for instance, like let's look at Cypher 10 on ResNet. So we might have a 5 width that we want to train on, and you can see that essentially leads to different number of mecs and parameters per network across different width. And what we're going to do for the devices, we essentially split them into several tiers. And then what we're going to do, each tier is assigned with the P max value, which is essentially the maximal width that those devices might work with while respecting the constraints. Now, what we're going to do then for like kind of a single communication route or single training step of our federated training. As standard, we're just going to select the devices to participate based on the constraints that I discussed. Then for each device, we send the model that corresponds to its P max, so the maximum width that it can work with. Now it performs local steps, but with the order dropout in order to kind of train across all the width that it's capable to train on, just because to get the proper solution to get this kind of a decomposable network as I described before. Once we have this, they obtain the update of the model that's just communicating back, and then the server aggregates this is kind of in this non-uniform manner. In a sense, we just aggregate over the client for the given neuron or for a given set of width, we aggregate over the clients that essentially updated it. And then for the inference, you just deploy based on the device capabilities. Now, one of the nice things, because you already have the model that's trained, like that's actually decomposable, is that even after deployment, imagine that now we take this device from the higher tier, even if this phase, we can then scale the model dynamically during the inference. For instance, like if that model has current increase or like has decreased battery level or increased load, then in order to kind of perform within the constraint, we can just simply decrease the size of the model because we train it in this decomposable manner. Okay, so let me show you some of the experiments. So here, okay, so that's strange. So here, the one on the right, I'm going to focus on the Cypher only. So here what we did, essentially we're going to just use the same training setup as for this model right here. And what we're going to do, we're just going to train it with the order dropout. And what are these red squares right here? That's a model that's optimized and trained from the scratch. So here the red models, essentially what you have 5 different trainings, while this one, the orange one, is ours, just training by a single loop based on the hyperparameters of the bigger model. And what you can see, essentially performance is more or less on par. And we believe like with the tuning, if kind of like a regularization hits in, that if you would tune a bit of parameter, then you can actually have even better performance than just models trained from the scratch. Now another thing is what might be maybe a bit, or what somebody might say, that essentially like, okay, do we really learn the meaningful decomposition of the model? And one way to check it, we take our model trained with order dropout, and we just compare it to the model that was trained only for a full width. And we're going to obtain with like random dropout, we're going to obtain the models that have the same number of parameters as our model with order dropout and look at its performance. Just kind of to double check that it's not just some kind of implicit property of a general training that you would discover that essentially like any model of that with your sample would have the same performance. And here you essentially see very huge drop, that even if you take like 40% of the network width, then essentially that corresponds pretty much to random guess, but we can still do more than 90%. Yeah, apologies that it seems that from the Mac to Windows doesn't like some figures. So here, the next thing that also want to link here, that's a nice property of the order dropout, is that you can actually increase the granularity of the width that you train on. So when we go from the uniform grid of size 5 to uniform grid of size 10, then essentially you can see that the performance across the intersecting width very well intersects. And then once we actually going to deploy this into federated learning, there where we see the best increase in the performance, where the reason is that essentially the only available baseline at the time of this work was to kind of consider that in order to accommodate the clients that cannot run the given model, we just, when we train the model on that given client, we're just going to apply random dropout, and that's the way how we're going to match the constraint of the client. But with that, you can actually see if you're trying to train the larger and larger models, you actually might see the decrease in the performance, while for us, you can see the steady increase of a performance, meaning that the more compute power or more like parameters you can store, the better model you can get. And this is also just to double check that the scalability also transfer to the federated learning. Now, what I'm going to discuss quickly is this next work that also is based on the order dropout, where there's kind of a motivation or kind of a usage of the order dropout is slightly different. So again, to acknowledge my collaborators, this is Steve, Shashank, and Hongi. So what's the main challenge that we're trying to overcome here is actually how to train large deep models, or like how to make kind of training of large, small deep models kind of equivalent to train large deep models. And if we look at the standard problems with training large deep models, particularly those one with billions or millions of parameters, there is energy consumption, resource demands, and data requirements. Now, so the thing is, like, why do we actually train large models? The reason is that they perform so well. The reason for that is this is a still kind of active area of research, might be due to implicit regularization, meaning that the model biases towards the simpler solutions, and also smoothness in the landscape, so it's actually easy to optimize larger models than the smaller ones. Now, what would be our goals is whether we can kind of keep the benefit of training larger models, where we actually going to train smaller models. And then the aim is to design models that can maintain high performance while significantly reducing the size of computational requirements. And how we're going to do it? We're going to do it through order dropout, and we're going to try to discover some kind of low-dimensional structures via this efficient decomposition. And by low-dimensional structures here, I mean low rank of the weights. That's based on the prior work that I essentially observed that's kind of one good notion of low dimensionality. All right, and how we're going to do it? Essentially, you already see that with order dropout is kind of connected to the decompositions. So what we're going to do is, like, if we have original mapping m times n, we transform it into factorized mapping, we'll try to decompose it, try to essentially remove the zeros, and that's how we get the low rank approximation. And how we make this kind of low rank approximation nice and trainable, this is the way how we design it with the order dropout. So let's have this, our original network. What we're going to do, like within each layer, we're going to input the layer that has an inner dimension of a minimum of these two layers. Then what we're going to do, we're just going to input this as a factorized layer, where we're going to deploy order dropout in this factorized layer. The order dropout here doesn't have any bias or any activation. And then what we're going to do for training now our sampling is going to be a bit different. What we're going to do is we're going to sample one layer at a time. So here, that might be the first one, and we're going to sample its rank. So this is essentially in each step the network that we're going to evaluate. And the reason for that is to essentially learn an efficient factorization of this layer that we can later prune. And that factorization is essentially the one that should account the data and should account the structure of network as well. Now that essentially, these are the main component of the method that we propose here called Maestro. So just to walk you through the algorithm, so what we do here, so essentially this first part right here is just an order dropout. So this is just a sampling and obtaining the prune network. And then something that I didn't discuss, so in order to have essentially low ranks, we somehow have to enforce it. And one good way to enforce low rank is lasso penalty. And because we have a natural ordering, we can do group lasso. And then the last thing, to actually have good adaptive pruning, so to actually prune as we train, we have this condition right here. So essentially what it tells, like once the network discovers that I don't need certain ranks, I'm just going to simply drop it. Now let me quickly walk you through the experiments. So essentially what this table tells you, that essentially with any other method that does low rank approximation with just standard SVD, but not the decomposition that's essentially tailored to the data and the network, we do much better, and we can do much sparser networks as well. Then also, what I want to show here, that essentially it's here, the one in the middle, what we display here is the ranks per layer for a different group lasso penalties. And what you can actually see here, that it might be not that the network learns only decomposition within the layer, but also some global decomposition, because the thing here is that by increasing the group lasso penalty, you always get a subset of the original network. Another thing, just kind of a sanity check, when we compare, like when we kind of design a pruning technique, because again, you get a decomposition. So even with having a network, you can do post-training pruning because you have decomposed network already. We can compare it to SVD, which is kind of a naive linear approximation when we go for the decomposition. So we can see that we do much better there. And also another interesting thing is that we actually don't need to kind of look for a good pruning technique. What we can actually do, we can just look, oh, what's the other networks found, and I'll try to replicate that. And it actually works relatively well. Okay, so I'll just have 2 more slides just to summarize that we discussed 2 main, or one of the 2 key challenges in federated learning. One is the efficient training and inference and heterogeneous devices. We looked at order dropout as a technique that would enable the composition of networks. And we introduced these 2 techniques to exploit order dropout, that is Fjord and Maestro, and some other interesting application of order dropout that we're looking at right now is the automatic rank selection for LoRa, some model alignment, one-shot architectures, and also network consolidation. So with this, let me conclude, and thank you for your attention.
Thanks a lot, Sam, for this amazing talk. Colleagues, do we have questions?
Thank you for a great presentation. My question about cybersecurity and privacy of federated learning. What's the future of federated learning? Is it, for example, integration with edge AI and quantum cryptography and something else? What else there should be done to be more efficient and more private and more secure?
So yeah, thank you for your question. That's a very good question. I mean, the main thing is, in terms of like when you ask about like privacy, I mean, we can make it as private as we want, right? The thing with that is like what you want to actually achieve is best kind of accuracy or performance privacy trade-off. So that's one of the main challenge, because I mean, always like you just don't need to communicate, you don't need to care about any privacy whatsoever. Like you just kind of, I keep my data private, never communicate that. That has a perfect privacy, but essentially zero utility. So there is really like the main challenge that people are looking at is right now, like how to, first of all, it actually turns out that it's even in this kind of a federated network, it's highly non-trivial to even train without any privacy constraint. just as I introduced the federated learning, that's still kind of a non-trivial task. Then when you add like formal privacy guarantees on the top of that, that introduce the extra layer of challenge, and there's a lot of work going on to like how to find the optimal trade-off between the utility and privacy. So that's kind of the main thing. But you can deploy it essentially anywhere where you collect the private data, or where you not collect private data, but where you want to actually train on the private data.
Hi, thank you again for a great talk. I have a question. Could we expect at some time some, I don't know, unified framework for doing that, like Hugging Face? It'll say like, you know, combined all this, and from the user perspective, you just check a model. Could we expect something similar for federated learning? Because you've mentioned a lot of frameworks and they're kind of independent to each other. So what's the reason? It's like still under progress, or?
Yes, I like pretty much. I mean, that's the main two frameworks. I mean, they kind of like where I think, I mean, they're also both of them like startups, and one of the kind of main goal for them is to provide kind of like unified one-stop shop for federated learning. That's
Thank you so much for very interesting talk. My question is about, as I understand, there are several approaches which helps you to make training process more efficient. And you show some graphics on ResNet, as far as I remember, yes. And on ResNet, we have approximately no drop in accuracy, approximately no drop in score. My question is, the result of this good score is a result of some of these approaches, or you apply one, for example, dropout or matrix approximation of the layer?
yeah. So I mean, essentially, I mean that's the ones where you do not essentially lose any accuracy. I mean, what we kind of show here, I think that's the one. This is the one that you point out to. Yeah. So essentially, what we show here that, I mean, first of all, like if you kind of do things well, you can kind of improve tiny a bit.
Yeah.
Yes. So essentially, I mean, that's when kind of a regularization kicks in, like the standard thing that you would expect to get with the decomposition, that you remove a noise, and then we show like you can actually, like if you really care about like you trying to push the number of parameters smaller and smaller, like you can still do that by just increasing this sparsity penalty.
Okay. So am I understand correctly that this table shows the approach of regularization?
Yes. So it's, I mean, regularization plus pruning, right?
Thank you.
Okay, dear colleagues, I think that we are a bit running out of time because next sessions should already start. So I suggest that if you have any more questions to Sam, that you just approach him like during coffee break and something like that. So let us thank Sam again.
Yeah, thank you.
Yes, and let us proceed. Let me remind that we again have two parallel sessions. So the NLP session is going to be here, and in the second venue we have, I guess, computer vision, right?
clicker. Good.
Да давай сейчас начнем.
Да, до 11.
А у тебя первый докод, что ли? У тебя должно быть 50 начаться, значит у тебя 25 до 15. Ну плюс-минус 17. Ну тут вот есть планшет.
До 15 минут.
Окей. Hi everyone, let's start another session with the first talk.
Okay, so thank you very much. I'm going to present a joint work. Mostly work has been done by Ozge Sevgili. So she is a PhD student at University of Hamburg, and also this work is with some collaborators also from Hamburg and Indian Institute of Technology. So the work is about the task of ultrafine entity typing. So what is entity typing and ultrafine entity typing is? Consider this example. You have this Olympic National Park. And this, as I mentioned, many of you know about entity linking task, and this is when you take a certain mention, and then you need to link this mention to a knowledge graph, to a knowledge base, let's say Wikidata or Wikipedia. So you assume then in Wikipedia there is a specific page about Olympic National Park, and then it's quite useful to link these because you can harvest, get all the information from Wikidata about this national park, maybe attributes, mentions, description, and so on. Now, the reality is, even the biggest knowledge graphs, they, due to inherent, let's say, power law of distribution or scarcity of the data, they cannot cover everything. So I remember this case, then there is this BubbleNet database, like knowledge graph. And if you look for word Python, there are about 50 census of the word Python, and there are like 2 roller coaster parks, one in Germany, another in the United States, in Florida somewhere. And that actually gives you an idea that you, even if you, no matter how hard you try, there will be always this gap. There will be always the long tail of some entities which just nobody even either cared to enter in a knowledge graph or actually never managed to insert in there. So that's why entity typing come to rescue. Then you just label with certain hypernym and like is a relation, and then you can still get a certain idea of what its mention is, even if it's not inside the knowledge graph. Now, inside this area, there are different granularities, because you can, let's say, this is a park, or this is a location, or geographical area, or maybe you can say this is an Olympic park, right? So there are really also a hard question, what kind of granularity you need to take. And this talk we speak about a case when you deal with pretty high granularity. So you speak about like tens of thousands of census or labels, but then the task is relatively easy when you take, let's say, 100 or 50 different types. Then you can collect easily a lot of data. But this information might be not so specific, not so useful for different applications. And the problem with ultrafine typing, when you deal with a large vocabulary, is then it starts to get again hitting this problem of scarcity of the data. So you don't have this amount of label enough data, and people try to come up with different ways with this problem. And one of the approach, maybe not the most successful even, but still interesting, I hope, I will present today. That's unsupervised approach, so that we don't use certain manual annotated data. Rather, we use distributional semantics and let's say bottom-up approach to do it. How people also approach this problem? People try to use the distance supervision. So, okay, for this entity typing thing, what people try to do, they try to think, hey, where can I just get the data for free? Where the data occur? you might get entity linking data sets, and for an entity link, you can look in the knowledge base and see, hey, what is the hypernym of this entity, and then use it. Maybe generate several hypernyms. This is a common approach to, let's say, automatically generate such kind of data sets. People also just try to use something like Hearst pattern, so rule-based approach to extract these ISA relations from text. Let's say I say a sentence like, such cars as Mercedes, BMW, and Audi, they are expensive and luxurious. Well, that would be like a second approach, but there are also some approaches which use zero-shot and unsupervised techniques, again, to avoid this bottleneck. But what we are trying to do, so we are trying to leverage unsupervised induced word senses using this job-in-text framework, which is based on distributional semantics, and it contains not only distributional representations of words, but also distributional representations of word senses, labels with hypernyms. And what we actually do in this work, we try to see how much useful these hypernym labels to the task of entity typing and unsupervised entity typing. So we try to disambiguate the context with respect to these induced senses. So how it actually works. So really at the core of this approach, a repository of these distributionally induced senses. So these are coming from this job-in-text framework, and you can look at this paper and this paper just for the background work. So this is not what has been proposed in this work, but rather like infrastructure which we are using. And what it proposes for every word, you have, let's say in this case, is word Rennes. So Rennes might be a city in France. So in this case, you see this first cluster, let's say Lille, Montpellier, and other variations of Rennes. But you also have this football club. Basically, this football club has a different hypernym. And here you see these labels for ISA labels, like club will be the common ISA label for one sense, for German sense, and the city is a hypernym, is a label for this sense. And well, basically the magic of this is that none of this is done using human labor. Instead, how people actually obtain this label? First, you obtain something like a word-to-vec distributionally related words, and then you perform clustering, and then you group these words, obtain these clusters of words. But again, you don't have hypernyms. But how hypernyms are obtained? Every word is assigned a list of automatically induced hypernyms, let's say using these patterns. And then these counts correspond to common hypernyms for this cluster. Let's say this is a noisy procedure. So of course, this term will contain a lot of hypernyms, but the common hypernyms will actually pop up at the top. So that's actually the trick, how you get relatively clean hypernyms here at the top. So city or club, they will be common hypernyms for a lot of these distribution-related cities, because they are all cities, right? There might be even some noisy words, but still. Okay, but this is what we are kind of leveraging, what kind of using. Now, how method works? Well, you have this input, and always you have, of course, certain mention you need to assign the hypernym to in context. So you need to disambiguate this, and this becomes your sense repository. When the rest is very simple, actually. So you vectorize the context using Esbert representation, and you vectorize the mention, because it also contains the word Rennes, but by itself contains certain information. And then you vectorize these guys as well, using, of course, the same vectorizer. So they can be, a certain similarity computation can be done. And basically, the rest is just picking the most relevant cluster and picking hypernyms from it.
to label it. Here, of course, a few additional steps apply. So if you go for real data sets for entity typing, you see not just unusual words, but something like this. So mentions might be really long, might be really elaborate, and even if you obtain sense inventory in this bottom-up way from the text corpus, there might be no sense representations or mentions for this kind of multi-word expression. So that's why head words, a lot of additional post-processing or pre-processing are done. So head words are collected. So different words, keywords from these mentions might be collected, and then candidates for senses, they obtained from these, not necessarily from the exact mention. Of course, also certain other steps like singularization of the hypernyms and the mentions are done. So matching might be done more smoothly. But essentially, as soon as all of these normalizations, linguistic normalizations are done, you perform this vectorization of the context and you compare the context vector with candidates prototypes for different senses, and you pick the most appropriate hypernym label. So the experiment-wise, what has been done, we took the setup of Choi et al., which was this paper, and compared to it and to some other baselines. The first baseline was just to pick the first cluster for a given word or pick a random cluster. So this means picking something. So this is a very important baseline in every word sense disambiguation task. It's called most frequent sense baseline. Why it's important? Because of the distribution again. So most words are used in the dominant sense, and of course, the largest cluster or first cluster in this case will have dominant sense, and this is kind of considered always a strong baseline. Random cluster is just pick a random sense, and then Choi et al. Well, this is approach which rely on encoding with a bidirectional STM CNN. And train certain multitask objective, and also some other approaches based on mask language model and NLI were considered. Of course, there are quite a few moving parts in this method, so you can select head words differently. You can singularize these different words, mentions differently. Here, an entity linking and principal, the way actually how do you yield candidates maybe is more important than the kind of a neural network you use. This is many studies show this, and because this is a similar study, this is not a difference. If you in some entity linking business or this kind of entity typing business, the way how do you select mention, how do you match it, it's very important. How do you generate candidates? Okay. Of course, some parameters correspond to job text itself. For job text is a fixed, let's say, granularity of clustering. So clustering can be fine or more coarse grained. So you can have for different words, let's say for Jaguar, you can have 3 senses or you can have 10 senses. And of course, they might be also different, more noisy, less noisy, and so on and so forth. Here, of course, last parameter we will take into account, and it's important one, is a number of predictions. So you can take only first hypernym, or you can take more hypernyms, like first 5 or 10. Here you can just return to this example. So first, second, third labels, they seems to be relevant, but if you go down the list, this is just automatically created list, and of course you hit at some point where there will be like a very noisy hypernyms which correspond to some very generic or irrelevant senses. All right, so here is a table with results. So first of all, we see that indeed first cluster and random cluster, they relatively strong baselines. So you can, but the method itself is actually outperforming these baselines. So actually, it does a certain disambiguation consistently. However, the results from the literature are pretty strong based on these other approaches. So in the end, what kind of a contribution of this work managed to do is to, in combination with approach of Choi, the method yields certain improvement. So basically, itself, the methods show that the clusters are pretty noisy, so just using the method by itself yield quite noisy results. But it yields some additional information, and if you combine this with a method of choice, especially taking only a few predictions, so you see here the precision really drops quite significantly if you take first hypernym or second 3, first 5 or 7. So precision drops, but recall, of course, increase with time. So what actually worked much better is also to drop in pronouns. What is the reason why if you combine with pronouns, if you work with pronouns, it doesn't really work? Well, the reason very simple. Think of pronouns like it. If you have senses, even if you have some senses, several senses of the word it or she, he, hypernyms of the senses will be completely meaningless. And if you take some mention in context and you have something like mention it, well, there is no way to correctly generate candidates for this. So that's why if you take setup without pronouns, this boost actually for ultrafine setup can be obtained, like you see here. But that's kind of summarized in this picture. If you don't, if you consider pronouns, the results more or less stay the same. But this additional information coming from distribution labels, they're useful in setup without pronouns. Okay. So in this case, slight improvement of F-score were improved. And of course, there are certain errors in the method. You can see here, this is what was generated, and these are kind of true predictions. So for instance, you see the method generated something like a violation difficulty for this mention, but the true label was like a crime or something. And again, you see the task is pretty challenging for real data sets, as you have very long mentions. And in this case, the method seems to generate quite plausible results. But again, according to human judgment, sometimes these might be somehow relevant, but they're also not mentioned in the gold standard. Okay, so the summary of this talk is like this. We explored how information from job text from unsupervisedly induced word senses can be used for the task of unsupervised for entity typing. It seems that if you don't consider pronouns, results can be improved if combined with the method of choice. That means word senses contain helpful and complementary information. However, word senses induced just from text, they are pretty noisy, and you need to deal with them with extreme care, because also you need to be very careful about how you candidates generate. So that's pretty much it. In case you have any questions, I will be happy to answer. And Ozge might be also on a Zoom link, so in case Ozge, you want to say something?
Yes, I'm also here. Thanks for the talk.
Okay, Amalia, if you can maybe make a Zoom, change to the Zoom camera, that would be also great.
We don't have questions in the audio, maybe we have one in the Zoom.
Okay. No, I mean.
Yeah, we have one raised hand.
Okay.
I mean, if you show Zoom, probably we can take short questions.
Yeah, let me take this. I think it's something different. Oh, it's a different Zoom. Sorry.
Yeah, well, if you start Zoom, then everyone in Zoom will see themselves, which is probably not.
Okay, do you have any questions in the Zoom?
Yes, we do. If you can hear me.
Yeah, thanks.
Testing.
Yes, yes, we can hear you.
Ah, okay, perfect. So yeah, just one very simple question. It seems that all the experiments were done with the English data, so I'm not familiar with this job in text framework. So how easy will it be to extend it to other languages, and does it exist for other languages?
Yes, it actually exists for multiple languages. I'm sure it has support for German, for Russian, for Italian. Not sure how long this list is, but yes, I think about let's say maybe 5 to 10 languages are supported. And yeah, you can look at the website. They have a nice web demo. You can just enter a word and look up all of these word senses. Actually, it's a snapshot of this demo. So you enter certain term, select maybe model and language, and you will see something like this. You see this automatically induced sense clusters and these labels.
Just in case I can't see your screen.
Okay. Can you, if you cannot see? Okay. I think something.
Because yeah, right now what we see,
Okay.
what we here in Zoom see is only the video stream full screen.
Okay, good. Okay,
no
good.
slides. But
Yes,
anyway,
okay.
Thanks. Yeah.
Okay, let's thank the speaker again.
Thank you very much.
Good morning, guys. My name is Maria Maslova, and today I'm going to present a project which title is RUCAM, Comparative Argumentative Machine for the Russian Language. And my colleagues are Irina Nikishina, Stefan Rebrikov, as well as Chris and Sebastian. What is wrong? That's nice. So I'm going to speak about quite an important topic, the problem of choice. I'm sure that all of you have faced the necessity to choose between iOS and Android, holiday places, car models, and so on. And one more topical issue is the choice between cats and dogs. So who is for cats in this auditory? Raise your hands. And for dogs? I see. So in the end of the presentation, we will see how our system responds to this question. So it is quite logical to create a sort of system that will help to solve this problem, the problem of choice, with the support of some reliable arguments. However, this task is quite complicated as it lies concurrently in the field of question answering and argument mining. Still, one of the most known and prominent research in the field is CAN, the system which can answer users' comparative input with the support of some arguments extracted from the large text corpus. However, CAM is English-oriented and there are no analogs for the Russian language. So now we present RuCam, a system aimed at comparing two objects from a general domain in Russian with argumentative explanation. If compared to its predecessor, RuCam has following differences. It allows to work with comparative questions in natural language. It has the component for object and aspect identification from comparative questions, and it uses an elastic search index of open tuple large crawled aggregated corpus, abbreviated OSCAR. We do not only develop a similar system and a pipeline from an engineering perspective, we also try to pose and answer following research questions. What are the main peculiarities of CAM that need to be taken into account when adapting it to other languages? And one more question, a more specific one, what are the main challenges while adopting CAM specifically to the Russian language? To start answering these questions, let's look at the system design. The process can be split into two steps, question analysis and argument retrieval, argument mining. The first step is about the identification of interrogative and comparative nature of a sentence. Also, it includes object and aspect identification process. And the second step consists of the search of relevant arguments for the input objects, their classification, and ranking. Let's consider each step in detail. The processing of a request starts with identifying the question type, so whether it is comparative or not. It can be done in different ways, including a rule-based approach. Here we stick to the idea of special patterns in comparative questions, which include comparative forms, explicit mention of comparison, similarity, difference, etc. To implement some machine learning approaches, we first compile a data set from the sources shown in the table. And here's an example taken from this data set. Then we use a routine BERT and fine-tune BERT from another research. As you can see in the table, the latter shows the best results, but comparative questions are quite specific kind of question that can be identified with nice quality, even using rule-based methods. After identifying the question as comparative, we need to extract objects and optionally aspects to further provide them for the argument retrieval stage. At this step, we also implement several approaches, and including a rule-based one. It is founded on the idea that all requests have certain structure, namely they contain two objects compared and connective of comparative nature between them. We consider following cases: two nouns, two verbs, the combination of noun and adjective, and the combination of a noun and two subordinate adjectives. Also, we expect a connective from the list of conjunctions and synthetic words expressing comparison between these two objects. In order to create a data set for the task, we take 6 1,000 sentences from the previous step that have been labeled as comparative and manually annotate them. 3 experts in computational linguistics were asked to label the first and the second object, and optionally aspect and common object. A common object is a specific structure with noun subordinating to adjectives. So, for example, in a sentence, in a phrase, green or black tea, tea is an example of common object. So, the level of annotation agreement is shown when creating the final data set for models fine-tuning. We use the annotation version supported by the majority of annotation. And that's one more example, considering our own example, yeah. We use fine-tuned transformer encoders and a few short approach on generative transformers to solve object and aspect extraction task. The table presents the results for each model. We see that generative models perform on par or even slightly better than baselines, and significantly worse than transformer encoders. Still, they may perform much better after proper fine-tuning, as we have shown them only 5 examples. Regarding lower and zero scores for common object and aspect labels, we claim that there are 2 problems. The first is the inconsistency of annotation, and the second is a complex nature of these labels. I'm in semantic sense. In order to retrieve arguments in favor of one or the other object, we use open super-large crawled aggregated corpus, OSCAR. We use OSCAR instead of the common crawl, while it is claimed to be its filtered version. We store and index this data with Elasticsearch. When indexing documents, we decide to create 2 indexes. The first one is for storing document information, like the number of sentences, web link, and so on. And the second is for storing sentences themselves. To retrieve sentences, we first do the snowball stemming, not lemmatization because of the time constraints, and then apply wildcards to be able to find all word forms. We send a Boolean JSON query and require that the clause must appear in matching documents. We consider the step to be the most challenging in all CAM pipeline, as Russian language has a highly fusional morphology, which makes it much more difficult to retrieve sentences than in English, because query words may occur in any form. And look at the elastic output for our objects, just an example. After the candidate sentences with possible arguments are found, it is necessary to understand whether the sentence argues in favor of the first or the second object. Again, we have a rule-based approach that requires a list of keywords with adjectives and adverbs with the meaning of superiority or inferiority of the first object over the second. Also take into account negation cases when the sense of a sentence is reversed. We collect a data set from 140 pairs and annotate them using the Yandex Toloka system for data crowdsourcing. To do this, we select same or similar pairs from the same domains as in English research, English conversion, like programming languages, car manufacturers, food, drinks, and so on, and make queries to Elasticsearch to extract all sentences matching the query. Then we create a system of tags. There are 3 tags. Better tag means that the first item wins over the second. worst tag means that the first item loses, and the tag none means that there is no comparison between the objects we are interested in. Unfortunately, the annotated dataset is highly imbalanced, as 75% of sentences belong to none, and for example, only 9% belong to the worst tag. At this step, we also implement several transformer encoders and few short approaches with generative transformers. The results for comparative sentences classification are inconsistent and relatively low for all the models due to the class imbalance problem. It is interesting that the rule-based approach produces a quite decent result on better sentences, then it even outperforms BERT-Large on worst sentences and generative transformers on non-sentences. The process of sentence ranking is identical to the one in CAM. We score comparative sentences by combining the classifier confidence and the Elasticsearch score. When displaying the arguments in RUCAM on a certain object, we sum up not only better arguments where the current object is the first item, but also worse arguments where the object is the second one in the sentence. For instance, both sentences, cats are better than dogs and dogs are worse than cats, are used in favor of cats when comparing them with dogs. The main outcome of our research is the final system where we integrate all the parts described above. The evaluation of the system is currently work in progress. We plan to evaluate RUCAM analogously to CAM evaluation pipeline by asking whether users are performing faster while searching something of comparative nature if compare the work with RUCAM with the keyword search. And also, we can ask some users just to play with the system to collect their feedback. That's it about the pipeline, and it's time to answer research questions in general. In general, when transferring CAM to other languages, you should take the following peculiarities into account: the difference in the notion of comparative sentences in different languages, difference in the syntax and morphology of languages when re-implementing rule-based approaches, and the existence of the relevant data sets and pre-trained large language models for training for different subtasks, as well as large text corpora containing comparative sentences for search in the target language. So, nevertheless, as it has been shown in Russian, it might be quite smooth if at least some of the required tools are available. What do we have now? We have RUCAM, the first instrument which helps to answer general domain comparative questions in Russian. Inspired by the CAM system, we create a similar pipeline, adding new steps for comparative question identification, object and aspect identification, and sentence classification. We also present several new data sets in Russian that might be further used for the fine-tuning of language models for each subtask. And from the performed experiments, we can see that rule-based approaches show decent result on all subtasks of comparative question answering, as well as few short generative transformers, and this subtask needs to be further investigated. And finally, let's look at our comparison at our small research. According to our system, cats win over dogs and do that quite confidently, so that's interesting. And that's an example of some top-ranked sentences. extracted from the Elasticsearch. As future directions, we plan to incorporate a summarization system that would be able to produce a coherent answer from two lists of arguments for each object. It will allow us to compare the results of various instruct-tuned models for Russian and ChatGPT with the RUCAM pipeline. Thank you for your attention.
Okay, any questions?
Thank you for your work. Can you elaborate a bit more on how you plan to evaluate the system outputs? Because your experiments were based on different components, right? So whether classifier argument identification works well, whether sentence classification works well. But ultimately, a user has certain information need, and it's presented with these outputs, right? Whether cat is better or not, and how would you judge whether this system is satisfying this information need well or not?
So for users, there will be a sort of front end to use and to input and work slower, faster, and what else should I say?
Okay, yeah, that's a human study. Do you think it's a possibility to do it in automatic, like a reproducible way, so that tomorrow somebody will develop another system and it can be compared as well, or it's just not obvious?
As I understand for now, the main way of evaluation is supposed to be human-based, but maybe we should think more about some ways of evaluation, of automatic evaluation also, that just a sort of future work, I suppose so.
Okay, and maybe if okay, I will pass.
Thank you for the talk. The question is like related to what Alexander asked. Have you tried to ask questions like compare something that is incomparable, and how system deals with such thing? I mean, it's partially due to lack of data, partially due to some strange query, and what is the default behavior, what is the intended behavior in your system? Like if I compare cats and Audi or something like this. What is the best? What? Yeah, of course. In this data set, if you train it on this data set, cats will be always better than humans. Yes.
In fact, I suppose there will be not enough output from the corpus if we pose such question.
Yeah, clearly. But what is the default behavior in this case, or some like? What system should do? Yeah, sure. Please.
Oops, sorry. For now, yeah, for now there's going to be done a request. So if we identify that the question is comparative, then the two objects will go to the Elasticsearch system and will retrieve some sentences. In my opinion, there will be almost no sentences comparing cat and BMW, depending, like, sometimes we have a cat as a machines, and then this is the disambiguation problem in this case. So yeah, but mostly it's for future work, because one of the limitations of this, yeah, so there might be some incomparable objects, and this is, yeah, quite a limitation for now. But in future work, yeah, normally we are planning to apply some taxonomic structures to look for hypernyms and looking for how they close are related, or maybe they're like in the different parts of the graph, so they cannot be compared. Not compare, yeah. Yeah, that could be done with some more fine-tuning, something, or some kind of unsupervised baselines using taxonomy on WordNet, in my opinion.
Thank you for the talk. Have you considered to do more classes? It's like, it seems to me that sometimes the answer to the comparable question is things are equally good or equally bad. And have you thought of this classes?
We've never thought about that, but I think that as a final result, we should receive a sort of process for the first object and the second object, and that output requires the classification better, worse, and none, and nothing more.
Okay, thank you.
Okay, let's thank the speaker again. And now it's time for the third talk.
Okay, hello everyone. I'm Maxim Savkin, and I would like to present our paper called Tuning Free Discriminative Nearest Neighbor Few-Shot Intent Detection via Consecutive Knowledge Transfer. So let's start from an introduction to the task. Intent classification is task of identifying user intent given an utterance. Naturally, it appears in dialogue systems and comes along with the task of autoscope detection. Here you can see on the slide, tell me a joke is an example which doesn't belong to any of the predefined in-scope intents, so it belongs to the autoscope class. I would like to emphasize the importance of autoscope detection as it is crucial for generating an appropriate response. We will solve both of these problems simultaneously. So the motivation behind this work is that most of the existing methods for intent classification rely on expensive fine-tuning and have high training requirements, especially state-of-the-art models. And also most of them are focused on in-scope classification, completely missing autoscope detection. Our approach, on the other hand, in our approach, we try to create a model which can work as a service. So it doesn't require any task-specific fine-tuning. It takes a few-shot data set and a set of unlabeled utterances as input and produces a set of intent labels. We try to inherit the discriminative nearest neighbor architecture. It utilizes a standard k-nearest neighbors and replaces the distance function with a deep cross-encoder Raperta model. This model takes an input and a training utterance and tries to predict the probability of these utterances belonging to the same intent class. So it is some sort of a similarity function, but based on a deep cross-encoder model. So in the original paper, strong capabilities of this similarity function were achieved by fine-tuning it on pairs of examples from the target dataset. However, we suggest to completely skip the fine-tuning step and focus more on creating a strong pre-trained similarity function which can differentiate between unseen intents. So further, I'll focus on retraining this similarity function. We consider using several binary classification tasks. The first one is natural language inference. It is popular for pre-training some strong binary discriminators. The second one is paraphrasing. It suits a bit better for similarity prediction. And the final one is a consecutive pre-training, where a model firstly trains on a large natural language inference dataset so that it can learn some inter-utterance relations. And then it tunes on a smaller paraphrasing dataset so to better match the similarity prediction. We also, for natural language inference, merge the last two classes, neutral and contradiction, into non-entailment. So it's a binary classification task. One problem with paraphrasing is that it lacks large high-quality datasets. So to mitigate this issue, we've tried using a small high-quality dataset and augment some non-paraphrases. For generating non-paraphrases, we use some sort of clustering. You can notice that paraphrasing is an equivalence relation, so paraphrasing dataset can be divided into equivalence classes, and utterances from the same class have the same meaning and can be considered paraphrases, and utterances from different classes can be considered non-paraphrases. They possibly have different meaning. So all those missing connections you can see on the slide will become our newly generated non-paraphrases, which we will use to increase the results for paraphrasing data. As for the metrics for the final model for intent classification, we are using in-scope accuracy, out-of-scope precision and recall, which are defined as standard recall and precision, but positive class is an out-of-scope and negative class is a combination of all in-scope classes. We randomly sample 10 few-shot datasets from the original datasets and report the average and standard deviation for all the metrics. The datasets we'll be using are the following. We'll be using a large Kling 150 dataset, which contains 10 domains and a wide variety of intents, and a banking dataset, which contains only one domain, but 77 fine-grained intents. So let's move on to the results of pre-training. As you can see on the left plot, a natural language inference task, despite being so popular, achieved the worst results due to its directional nature. And the best results we were able to obtain so far are with consecutive pre-training, where a model firstly trains on a large natural language inference dataset and then tunes on a paraphrasing dataset with newly augmented non-paraphrases. This is the third column. I would also like to notice that augmentation really helped to increase both in-scope accuracy and out-of-scope recall by introducing new non-paraphrases. So let's compare our model against other tuning-free methods. The first one is TF-IDF KNN classification. And the second one is embedding KNN vanilla, which is actually just a KNN based on beam encoder Roberta model, which was pre-trained on a natural language inference task, only pre-trained, no fine-tuning at all. So here you can see that on the Kling dataset and banking subset of Kling, we are achieving the best results so far, even getting much and our approach is much more stable to threshold selection than our approaches, as it has much larger area under the curves of in-scope accuracy and out-of-scope recall. We also thought that it would be important to compare our model with some fine-tuned methods. DNC is the state-of-the-art model for out-of-scope detection, and here you can see that as expected, fine-tuned methods are better in initial in-scope accuracy. However, for standard Roberto model, you can see a huge drop in accuracy, which means that it has a lot of low confidence predictions. And our model has a larger area under the curves on in-scope accuracy, so it is more stable to selection of threshold. These results are not included in our paper, but we decided that it's also would be important to see how our model stacks against ChatGPT. So the whole clean data set didn't fit in the prompt, so we've used only a banking subset of clean data set. And with standard out-of-scope examples, you can see that ChatGPT with zero-shot prompts achieves nearly ideal results. And we suppose that it's all due to the fact that it memorized this dataset quite well. So we've decided to change all text labels with indexes, and we also replaced standard out-of-domain examples, out-of-domain out-of-scope examples with harder in-domain out-of-scope examples. And as you can see, our model still attains relatively high recall and accuracy, while ChatGPT really struggles with these harder out-of-scope examples. So only a few shot ChatGPT is able to produce some relatively good results. Yeah, so summarizing our paper, I would like to say that we've developed a model that doesn't require any task-specific fine-tuning. So it can be applied to any data set for intent classification. It supports an out-of-scope detection, has the best performance on clean data set, and it is robust to threshold selection. Thank you.
Do we have any questions?
Thank you. Can you elaborate on this difference between setups in domain and out of domain? So you mentioned, yeah, just next up. Yeah, next slide.
This slide.
Just the one before conclusion. So you mentioned that you removed some identifiers and converted them to numerical. What does it actually mean?
I mean that ChatGPT probably has memorized the dataset quite well. So we've decided to reduce the effects of this memorization and replaced all text labels with just indexes. So it couldn't memorize just by prompting just so well.
But would it be fair to ChatGPT? I mean, in the sense that maybe your system memorized these indices, but ChatGPT...
No, it doesn't take labels just at all. So it just takes input utterances and compares them between themselves only, and doesn't take a label as input. So it's totally fair, I think.
Okay, thank you.
Do we have more questions in the audience? Okay, maybe we have some time for one Zoom question, if we have one. No, we don't have questions in the Zoom. Let's thank the speaker. Okay, now it's time for the fourth talk.
Hello, my name is Vasily, and we are going to talk about whether it is possible or not to find the number of topics in a natural language processing data set. So a couple of words as an introduction. What is topic modeling about? A topic model receives as input a huge text collection, unlabeled, and as output, it produces topics. Topics as probabilities over words. So we can see what text is about, and we can locate the places in text where each topic is covered. So the problem of topic modeling can be viewed as a matrix decomposition problem. Topic model receives as input a matrix of word in document frequencies, and it decomposes this matrix into matrix multiplication of two matrices. First matrix of word probabilities and topics, matrix phi, and second matrix of probabilities of topics in documents. Well, but it is not clear how one should select this hyperparameter. Is it crucial or not? How to find it? So it seems that in some text collections, at least the number of topics can be well defined beforehand. For example, if we take some articles from Wikipedia, they are labeled, they are split into sections. So if we take some articles from, let's say, art section, some from biology section, some from history, we get a data set, and we can say, obviously, that there are 3 topics in it. So, but in real life, it may appear more complex because these topics labeled by humans, this is something that just helps to simplify the categorization process. So in real life, it may be, well, much more topics in this text collection. These bigger topics may be split into smaller ones, and furthermore, topics may combine and produce some new topics. So is there a number of topics in text collection or not? Can we find it or not? We are trying to find an answer to this question, and what are we gonna do? We're gonna train a topic model for a text collection with varying number of topics from low to high. And we're going to track some topic model quality measures and look at the plots, at the dependence of quality measure against number of topics. And if we, well, let's say, see some local minimum or maximum or plateau, it may be a sign that the number of topics corresponding to this interesting point is an optimal one. So this is the picture which we are, well, expect to see. After going further, I think it is important to say a couple of words about similar projects. We are not the first to try to track a lot of quality measures while training a topic model. We are even not the first to try to find a number of topics using these quality measures. But we believe that our research is one of the most extensive one. So what quality measures are we going to use? First, perplexity one may be the most common measure while training topic models. The lower the better. Second block are measures, diversity measures. They compare topics with each other, computing distances between pairs of topics. Because if a topic model produces topics which are all similar, it is bad. The second block is clustering measures, because topic modeling can be viewed as a soft clusterization problem. Words are split into topics, which are soft clusters. So we can adopt several measures from clustering analysis to use it as a measure of topic model quality. And the last on this slide is a block of stability measures. Well, topic models are unstable. It means that if we train a topic model on the same text collection with different random initializations, we can get different results. So we compare different topic models obtained with different random initializations with each other, compare their topics. Well, this is not all measures which we use. The next block are information theoretic measures. We use several of them, but the idea is the same. They compute roughly the difference between model complexity and model likelihood. So the bigger the likelihood, the better, but the bigger complexity, the worse. So these metrics are trying to find the balance between the two model characteristics. The next one is entropy. There are works where the authors propose to use this metric because, well, another analogy with between topic modeling and a complex system where we have several possible states, topics, and particles, that is words, can occupy several of them. So the optimal number of topics using this measure is the number of topics which gives an equilibrium state to the system. And the last block, which we use, the last block of measures are top tokens measures. We compute coherence and lift scores. That's it. Well, the methodology of our experiment is roughly described here. For each data set, we train a topic model with varying number of topics from minimum to maximum, compute topic model quality measures, and look at the plots. Minimum and maximum topic model, minimum and maximum number of topics which we vary depends on the data set. The models which we use are the following: PLSA, the simplest model, which have only one hyperparameter, the number of topics; LDA, the most known topic model, and a couple more. Decorrelated topic model, which is trained in order to produce topics which are distinct. Sparse topic model, which distinguishes its topics, it splits the topics into two groups: background topics, which are smooth and, well, about nothing, and specific topics, which are sparse and exact. Sparse means that the largest probability mass is spread only on a small group of topic words. Well, this is models and this is data sets. We use several data sets in English, several in Russian language. For each data set, we know at least approximately the number of topics in this data set they expected. This is our ground truth. Well, probably I should say a couple of words about the last data set, Good. This is our data set composed by our research group. It consists of good articles from Russian Wikipedia. So, and this is the result. This is the results. Table with 3 numeric columns. Each column is a score which we assign to each quality measure. So what they mean? The first column is Jacquard metric. It tells how the predictions of the same topic model but trained with different random seeds are consistent with each other. The lower the better in this table. It is called Jacquard because it is computed the following way. We take the predictions of topic models with different random seeds and we make two sets. The first set is a union of predictions. The next set is intersection of prediction, and we compute the Jacquard distance between these two sets. The next column is informativity. Well, it tells how the plot of dependence of quality measure against number of topics is readable by a human, whether it contains local minimum, maximum, or plateau, or it just random up and down and without any possibility to make a prediction out of it. The last column is called expected. Well, it tells whether the quality measure succeeded in finding the exact number of topics, whether it corresponds to the ground truth from the table with data sets. Well, what can we see from here? The best values in table are colored with blue, but these best values are obviously far from good. So maybe an indicator that there is no such notion as natural number of topics in a data set. And there are several illustrations to support some other conclusions. First, we found that optimal number of topics depends on the topic model used. For example, on this plot, we can see three curves. Each curve corresponds to a sparse model with different sparse hyperparameter. So one is more sparse than another. And as we can see, these models, this is the same sparse model with different parameters, they give different results as optimal number of topics as local minimum. What is more, we can see that this, broad lines averaged over random seeds, also each random seed produces a bit different number of topics. So it is also what impacts the result. And on this plot, we can see, not about this plot, other finding is the following. Different quality measures produces different results as number of topics. This is general case, which we studied. However, sometimes on this plot exactly, we could see that different quality measures give the same result. For example, here, one topic model, one data set, and several quality measures, and they point roughly at the same number of topics, 7. But this is not a rule, this is an exception. And that is probably it. So, conclusion, we found out that number of topics is probably not a natural characteristic of a data set. It is just another hyperparameter of a model, and it is also dependent on the quality measure which is used to find the number of topics. Perplexity and coherence, maybe a bit surprisingly, they failed to give any decent results. However, information theoretic criterion and Renier entropy achieved best results. Well, as a final remark, we want to say that probably this is not such an important task to find the optimal number of topics as just finding a way of training a topic model which has all topics interpretably good, whatever topic number you assign at the beginning. Well, that's it. Thank you for your attention.
At Zoom, it's fine listening me from the mic here. So I have one small question. So could you please summarize what we should do if we need to select the optimal number of topics? So basically run as many models as possible and then to select, as I understood correctly, but...
The best way, we think that if you should know beforehand, at least roughly what number of topics you have in your collection, and it is the best way. And the second, if you don't know how many topics you have, 2 or 200, then this is best to just probably train topic models, conduct many experiments, and in order to find the topic model which best describes your collection. Well, another way to train many topic models and collect good interpretable topics, put them aside, and by looking at how many topics you collected, you can see how many topics you have. So, something like this.
Okay. And
you start with some number of topics and start experimenting, making your topic model better or collecting topics.
Okay, thank you. We have more questions.
Yeah, thank you. Did you consider some also classification based experiments where you obtained representations to and measure quality of this?
No, we were concentrated on just intrinsic quality measures without trying to assess topic models by experts or secondary tasks because, well, if we try to select the number of topics based on secondary task, it obviously would produce better results because we just find the number of topics which give us best results. We wanted to find out whether there is some natural number of topics which could be found by intrinsic quality measures.
Yeah, I think that might be also different for different classification tasks or for different applications. Different granularities might be needed. So that might be kind of at the heart of this issue, right? So you have different hierarchy of granularities. Maybe for retrieval, you need coarser granularities. For, I don't know, authorship identification or something, you need very specific things. So they might be just this general idea that everything in computer science depends on application and there is just no universal representation. I mean, at least in terms of topics, which is works always well. Like in clustering, you might have different views on this data.
Yes. If you're trying to solve some secondary task, it is best to search the number of topics based on this task.
Yeah. Okay, thanks.
Okay, we have more questions.
Yes, we do.
No, Andrei, you have one question from the audience and then yours from Zoom.
Thank you for the insightful talk. I have a couple of small technical questions. That data set, wiki good, right? And as I believe, in all those data sets, you had the true number of classes, the topics, right? So how did you obtain the topics from the wiki, right? So it's categories probably, but what was the label set?
Well, yes, it was scraped from Wikipedia. We knew the categories of each article, so that's how we found the number of topics.
I mean, what was the topics? Like some categories from the Wikipedia?
Some large categories, yes, which are good topics are divided into. There are articles which called good, which are checked and well big and thorough, and there are several categories which these good articles belong to.
So there was some manual post-processing for the label set, right?
Yes.
Ah, great. And second question, also as a technical, what motivated the choice of the models in concern, right? PLSA, LDE, and different flavors of ARTM. So, I mean, the kingdom of topic models is rather large. So, why these?
Well, our main idea was to take just several topic models in order to exclude some, biases towards topic models. We just wanted to take more than one topic model, so we took PLSA, LDA as best, as well known as simplest approaches, and several other variations just to make more.
I mean, wouldn't like neural topic models contribute something else, or it was not really that important for the study?
No, we didn't consider neural topic modeling because, as well as I understand, there is also a hyperparameter T for these models. Well, we just excluded. What we excluded is the models which also try to find this number of topics as a result. For example, hierarchical Dirichlet process. We excluded these models because they introduce additional hyperparameters which need to be optimized, and they are also non-universal because in terms that they are assessed differently than the majority of topic models, which have just two matrices, phi and theta.
Yeah, of course, but some neural topic models have T as a parameter, like ETM, for example, by D, and so. But anyways, thanks for the answer.
Thanks for the question.
Let's thank the speaker again. And now we have the last talk of the session.
Control. Oops. Alt. Is it in browser? So you should open it not in browser but in Acrobat. Hello everybody, welcome to this talk. This talk is this work is done in collaboration with Kazan Federal University. So this is a part of a project of studying text complexity on different levels. So this part is related to text complexity at the sentence level. And the other parts of the work of this big project done in KFU is related to academic complexity, academic text complexity, and also lexical complexity. So the context is that of this project is that we want to do the prediction at the sentence level and at different levels, as I already discussed. And sentence complexity is one of these well-studied tasks already, but in Russian it's not that well-studied. And there are limitations for classical measures, so we tried not only the classical approach with the features, but also the deep neural networks to train and measure the performance on this task. Okay, and yeah, one thing that is there are other languages like Italian, English, and others that already get data set for sentence complexity. In Russian, there was no data set, and yeah, brief discussion of the work that people tried to do before us, and they collect data in different languages. They trained some classical approaches like on lexical features and syntactical features as well, and deep learning methods like pre-trained language models, and collected a lot of different data sets in this domain, including English and Italian. And our first part of the project was collecting the data in order to run the evaluation. So the data set, we resembled the methodology for English and Italian dataset collection. So we used the Toloka crowdsourcing platform and asked Tolokers to annotate the sentences according to 7 levels of complexity. But we also wanted to experiment with different features, so we sampled the data set from the syntax rules corpus, because there is a syntactic annotations and other interesting things that we can make use of later. Yeah, that was a sample of the sentences was related to the frequency of the lexems in the sentence. So we tried to sample the sentences of average frequency, like not to sample too complex, too rare words and so on, as our colleagues before did. And each bin contained 200 sentences, so overall it's like 1,200 sentences. So it's just sample interface of the UI. Those people just were asked to pick one of these scores. So there was a 10 out of 10 assessments per sentence. And yeah, just example of a sentence, example of this thing. And yeah, we collected data from people who are native speakers. There are no other like restrictions or something like this were applied when we collected the data. There is a slight imbalance of the data here. You can see the distribution of these scores among in the data set. And yeah, it's biased towards complexity, more complex sentences. which is kind of contradictory to what we have into other data sets, English and Italian, but it's still a kind of interesting observation. Regarding the assessment of agreement, so we have this distribution of complexities corresponding to the so the x-axis here is the sentence length in tokens, and y-axis is the average score, distribution of average score. And yeah, of course, there is clearly the correlation between two parameters, but also we measured the average number of people who agreed about the score on the sentence. So out of 10 people, assessors 4.3 on average agreed about the score, the complexity score. Of course, the sentence length is a crucial parameter. It's important to assess the complexity or readability of the sentence. But it's not the only one, and previously we analyzed, so previous work we analyzed what features can be important based on the features that are more important, more correlated to the target. We build a simple linear regression, and then in this work it's kind of a step further. We try to push the performance more to get more quality of this data, and then in the second part of the talk there will be some modeling, like classical and deep learning approaches. Here you can see the difference between discrepancy between Italian and English and Russian data, and you can see that yeah, in Italian and English you have relatively small number of complex sentences. Not complex here, but complexity on the y-score, but on the x-score again, just length of the sentence. And in those two data sets, there are relatively less number of sentences with a long, relatively less number of instances with long sentences. The same you can see here as a distribution of the complexity score. So pink is Russian, and this one is English, and this one is Italian. So the average complexity also different on different languages. So it can be due to sampling, of course, but maybe it's just also related to some other like linguistical properties, such as average length of word, average length of sentence, and maybe the also annotator basis. Here you can see that distributionally these properties like this Russian, English, and Italian data set, and here the frequency of lemmas, sentence length. So it's more or less similar. So here the discrepancy is apparent, but because we got the logarithmic frequency, so after the normalization they look the same. So these three data sets are comparable, and you can run the several experiments, several models on this data. Simple approaches like based on linear regression and decision trees and SVMs based on classical like TF-IDF metrics features. And then we tried also like modern approach based on BERT model and fine-tuning of BERT, and also graph-based neural network. So that was initial idea to select features, 3 features that we can select from the feature set of the, and then build a linear model that with the 3 parameters gives quite not very nice results. And for this quality, like R2 score is quite low, and MSE and MAE quite low. So the next idea about the BERT is quite obvious. I don't want to stop more on this. It's just fine-tuning of the pre-trained RuBERT, Italian BERT, and English-based model. Regarding the GNN, we make use of this model that gets the syntactical tree, dependency tree, augmented with additional edges. and also we use as features of these nodes in each syntactical tree, in dependency tree, the features provided by fast text. So it's the convolutional model actually gets the features and applies the graph-based convolution in order to find the representation of the whole, of each node, and then we do the pooling over the all these three. And the final linear layer decides what is the complexity of the sentence. Results of fine-tuned BERTs, of course, it's as it was expected, they were quite decent, and this is just number, outrageously low numbers, like good numbers, because of a large number of epochs. When we compare it to like GNN and SVM and other models, we can see that BERT-based models for all languages, they are much better. And linear regression sometimes just doesn't provide any reasonable result because of maybe a number of features, who knows. And this GNN model actually is not that bad compared to some other languages maybe. That's data set is available, and we are going to continue this studies in both cross-lingual, multilingual setting, maybe building a model that can be applied to several languages. And there is an interesting direction of research when the other group working on lexical complexity, so they want to measure the complexity of the word in context, and then using this thing you can measure the complexity of the context itself. Not just sample some sentences with words, but sample complex sentences or simple sentences with the same word and analyze its complexity in context. That's probably it. If I have time, I think I have some time for questions. Please go ahead.
Okay, I have one small question. Why English and Italian datasets use 7 scale?
Why do they use 7 scale?
Instead of 5, for example? Like for me, 5 was the simplest way to think if you're not satisfied with binary classification, because it's not the type of a binary classification task. Why not 5? Why did you decide 7?
That's a good question. Actually, I don't remember they explain it well in the paper. That's somehow this it's called a Likert scale, and that's usually from 1 to 5, and in this case it was like 7 for some. Maybe more fine-grained is better. I don't know really.
Okay,
that's a good question actually.
Thank you for the great talk and for the data set, finally. The question that I want to ask is, when I put myself in the shoes of the annotator, yet again about the scale, well, it's sort of hard to choose, I believe, however you explain each, I don't know, button, right? So I wonder if there are any gamified things or some procedures where people annotate the complexity of the text implicitly, so that the data set can be derived from the procedure. Is there anything of the sort?
Something that comes to my mind is this eye tracking thing that people like measure something like indirectly, like how long time, how many times you have this saccades or something like this, and when you read the text, and there are measures, and also I think in KFU there is a investigation of this part, how students in school read the text and how they perceive it using the eye trackers devices. But for this crowdsourcing, it's I think the only thing to do is to increase number of annotators and somehow control the output quality, like measure the time, how much time people spend on each sentence, for instance, annotating each sentence. It should be not less than like several seconds, maybe. So that's kind of general approach.
Thanks.
Okay, we have one more questions in the Zoom.
Yes, please.
Yes, thanks for the talk. So my question is also about the data set and also about putting myself in the shoes of the annotators. So the obvious strategy for an annotator is, of course, to just label long sentences as difficult and short sentences as not difficult. So the guidelines for the annotators, did they include any specific instructions about taking into account sentence length or not taking into account sentence length?
Yes, good question. Yeah, there was a short guideline. Actually, we provided like examples of sentences that are short, the hard and not hard, and we completely rely on the intuition of annotator in this case. I think any guideline in this part, when you try to gather an assessment of the complexity that is, or difficulty that is purely like perceptual thing, it's not kind of cannot be formulated or defined objectively, in my opinion. So we rely on the intuition, linguistic intuition of assessors, and we minimize these guidelines as we can. And then again, just if you have enough number of assessors per sentence, on average, you will get a good assessment, good score for the sentence. The guideline was very short, I'd say.
Yeah, and the guidelines didn't mention the sentence length in any way, right?
No, it was not related to any, bounded to any parameters or whatever. So we just like didn't want to push assessors or bias them towards some attribute or whatever.
Okay, thanks.
Okay, any more? Oh, two questions. Okay.
Yeah, thank you for the talk. I have one small question. Have you considered any relation of text complexity with linguistic acceptability? If there is some connection between these two notions, maybe the text complexity could be assessed with the perplexity of the models and other methods used for acceptability.
No, we didn't measure this exact relationship between these two things. What I was thinking about the measure connection between the grammaticality or some syntactical features. So that's why we're looking into syntax groups, because you can compute some syntactic-based parameters from the sentence. But like grammaticality or some, quality of sentence can be related to complexity, of course. But acceptance in this case, well, I don't think we have a lot of data in Russian. Maybe I just don't know about the.
There is the Rucola dataset, which is like in the very
Rucola, okay.
Yeah.
So that's maybe possible, yeah, to do this in this case.
Okay, great, thank you.
It's a good idea.
Yeah, it's just a very short comment related to Andrei's question. Do you think it makes sense to, when annotators are given different sentences, to provide the same length of the sentences so that they never biased indeed by this very strong yeah. So
that's good.
Maybe a model can learn better if you provide always.
Yes, that's good point. Actually, that's it needs different scheme of annotation. You give two sentences with the same length and decide ask annotator to measure to answer which one is more complex.
Yeah,
like this, right?
maybe they pay attention then to more non-trivial features. And
yeah.
Model
It was a similar thing we tried in previous work. That was a classifier that was trained on the pairs of sentences of the same length. But for annotators, here we collected only the scores per sentence, and that could be a bias towards the length of the sentence. to avoid this, yes, we didn't do this, but the idea is quite obvious, and maybe we'll try to do it. Right now, it's the goal of the project is to develop a model that will just sample complex sentences or simple sentences.
Thanks.
Yeah. Thank you.
Try to make it short because we're a little bit out of time. So 10 minutes for coffee break and then the next session on NLP.
Yeah, I see. Okay, do you hear me? Okay. Hello, everyone. My name is Alexey Andutov. I'm from Lomonosov Moscow State University. Yeah, I and my colleague Natalia Lukashevich prepared research with topic document level relation extraction in Russian. Excuse me. Can I use this? Do you hear me? 1, 2, 3. Okay, let's start. Okay, what are we going to talk about this today? First of all, why is the task of extracting information and subtask are relevant? We will short introduce what is a relation extraction task and what is the difference between sentence level and document level relation extraction. And I will show the problem of nested entities in this task and what models for document relationship extraction are used. Okay. Traditionally, one of the most important tasks in the NLP is information extraction, and one of these important subtasks and least explored is relation extraction. This task has a broad range of applications, starting creating and updating knowledge bases like Wikipedia and WordNet, to structuring documents like okay.
Is it working? Yeah, let's start.
Okay, could I continue, yeah? Okay, let's continue. Why this work is important? First, we address extraction with nested entities, and ignoring these aspects results in information loss. And next, we focus on the document level relation extraction. It's a complex problem, and it's crucial for understanding entire document. Notably, no studies focusing on Russian language have been published yet. What is the task of relation extraction? Look at this example. Given a sentence, the previous Cannes Film Festival was held from May 19 to 26. Given as entities, festival, and date, we should predict the type of relation, point in time, in this case. And also, a relation can be formulated as triplet subject, object, and relation type. But in this work, we consider document relation extraction, document level. And let's look an example, a news article about Konstantin Rubinov. We consider two entities, music band Гражданская оборона or Civil Defense and Konstantin Rubinov. At the same time, we see that Konstantin Rubinov have some mentions like Kuzi.io, that is a nickname of Rubinov, and we should recognize relation type founded by and recognize evidence supporting sentences that can help you to understand the relation type in this case. And what's the difference between sentence level and document level? First of all, in first case, you have single sentence and usually only two entities involved, but in document level relation extraction, you have a long entire document. Entities can be mentioned in various forms, and you should also predict the evidence. We use narrow.
Okay, there is no sound again on Zoom. Can someone from Zoom hear us?
Yes. Yes.
So we can continue, right? Or you haven't heard 3 slides before that?
It was okay.
It was okay. Okay, good.
Okay, let's continue. Yeah, we use a narrow data set, which contains annotations of entities and relations between some words, and there are about 30 different types of entities, like person or place, and about 50 different types of relations, like workplace, alternative name, or work as, and importantly, that some of these relations occur between sentences in the text. Okay, how this task of relation extraction can be solved? The baseline approach treats its classification task for a pair of entities in text. For example, given a sentence, you should mark two entities and apply sum of classifier. But we have some problems with more advanced approaches. For example, when we mask our entities, we have problem with overlapping entities like Moscow State University, and it can be used in some models like Spanbird. Okay, and one of these approaches solves this problem, and it's about tagging. In my previous work, I presented that this problem can be solved by several approaches. First of all, decomposition into subtasks, and each solved by a separate model. And in the main approach is joint extraction, where you use a single model to extract all of information in your text. And in short, that our results that using a single model provides better quality. This allows for incorporating all knowledges and into one model. Okay, we took this into account and considered some approach that addresses relation extraction in a general sense. And what approach did we use to solve the task of at the document level? We started from baseline, BLSTM that was mentioned in DocRed paper. Text with features like growth and entity type vectors and coordinates of entities in text. are applied by BSTM, and finally we aggregate some of entity mentions and classify by multi-class classification layer. But in this task, it's important to consider all of entities during prediction. And it seems a good idea. And in approach of DocuNet, after encoder our text, we build a relation matrix and use UNet architecture from computer vision approaches. And finally, we can pass this matrix and classify the output. In addition, we previously mentioned the concept of evidence or of supporting sentences that can help to recognize the target relation in our task. And in the extended narrow dataset, such labeling is also provided. The DREAM approach allows us to the additional markup. Beyond predicting the relationship, let's also model the importance of the sentence in this text. And finally, we can keep only the most important sentences and make predictions based on this document. And this approach is called fusion approach. So we see that best result was from DREAM and fusion approaches using Ru Roberta large encoder. And also let's look at some main problems we encountered when working with model on the Russian dataset NRL. First of all, in this task, you should process entire document, and we use window-based text processing with overlapping windows. Okay, next. The second problem is that the quadratic complexity based on the number of entities, and this is because the number of relationship in the document is the square of the number of entities. And a lot of relations in your text is labeled like no relation, and it's important. And in cases when I'm using some large models, it can be help that removing random negative relationships up to set ratio within the document. Okay, finally, we conduct first metrics on document level relation extraction in Russia, and specifically in the narrow data set. Also, metrics achieved nearly the state-of-the-art models for English, I mean benchmark Docret. We explored the issue of nested entities and implemented some enhancements to process longer text. And also, we see that balancing negative relationships helps optimize the training process in the task of document level relation extraction. Okay, that's all. Any questions?
Okay, so your experiments were done on only neural data set.
Yeah.
How you would estimate how generic this model is if you just go and start apply it to new text, let's say from Newswire or internet websites, just for harvesting very large database of relations about persons. Would it be accurate, or domain shift would be very, very severe?
Yeah, I'm sure that it's a general approach for relation extraction where we use these models. Yeah, first of all, we checked all of the models that have the best results of the English benchmarks, like DocRed, and we used approach that can be used in another dataset like Nerel and for another language like Russian. So I think that it can be used for any domain or any area, but in some of cases you can see some problems like problems with, I mean that you should optimize your model to a process, for example, in real time and so on.
Okay, thank you very much.
Second question. Okay, let's then thank the speaker again. And now it's time for the second talk of the session.
Hello, everyone. Can you hear me? Hello once again. My name is Maria, and today my colleague Leona, who is here via Zoom online, and we are going to present our joint work on the way to controllable text summarization. However, today I'm more like a presenter because the main research was performed by Alona, and she's the main contributor, so all credentials to her. And I was more like a tutor advisor. Unfortunately, Alona couldn't come today, but she's here with us, and after the talk, she will be ready to answer your questions with me. So today we are going to talk about the application of the new promising approach, namely the Hydra sum approach to controllable text summarization in Russia. And the structure of the, I'm sorry. Okay, so today first we will talk about the motivation, then briefly discuss all automatic text summarization approach, and then I'll give the brief overview of the original Hydra sum method. And then we will switch to our research, talk about the data, the experiments, and of course we will discuss the result. So basically, the concept of controllable text generation brings an additional layer of flexibility and customization to the summarization process. And this controllability allows users to specify specific attributes of the desired text, such as length or style, for example. This customization enhances the user experience by providing summaries that align more closely with their information and individual preferences. Moreover, it allows users to specify the level of compression to make it easier to summarize the desired text. As for the objectives of this study, the main one was to investigate whether the multi-encoder architecture utilizing transformer-based model called the Hydra sum is applicable to the Russian language because it has shown great results for English, and whether Hydra sum could produce more stylistically diverse or higher quality summaries than the classic approach of fine-tuning language model. This research lies in the field of natural language processing with the focus on automatic text summarization. As traditional methods of text summarization are mainly divided into the two big groups, namely the extractive and the abstractive ones, they provide no controllabilities, producing texts which are not stylistically diverse. The Hydra sum method, on the contrary, introduces some control. And briefly speaking, Hydra sum is a mixture of expert architecture with multiple decoders, which is based on the pre-trained language models. As a base model, the authors of the original paper choose Facebook's BART large, but they claim that it can be applied to any transformer model. In Hydra sum architecture, the base model is extended to consist of multiple decoders, namely the authors experiment with 2 and 3 decoder architecture, where each decoder captures different stylistic features of the input text, and each decoder has a total number of decoder block where the parameter of the bottom layer are shared among decoders. This is done to minimize the number of additional parameters introduced in the model architecture. The top layers of different decoders are pre-trained independently, thus each decoder can specialize and learn distant representations to suit its specific task. And an important thing is the gating mechanism, which is an important part of Hydra sum. Basically speaking, this gating mechanism is a weighted sum of the k decoder's output, and it dynamically determines how much each encoder's output contributes to the overall result, enabling flexibility in decision making based on the weighted contributions. After utilizing the gating mechanism, the outputs from the shared layers are fed into a feed-forward by softmax activation function, which outputs the overall next token probability. Thus, this process assigns weights to the outputs, determining their relative importance. The author provided 3 inference strategies, namely sampling from individual decoders, where one decoder is more extractive and the second one is more abstractive, and mixture of decoders using the gating mechanism, mixture of using manually specified gating mechanism. Basically speaking, to adapt Hydra sum architecture to the Russian language, we've chosen the classic summarization dataset known as Gazeta dataset, and recently it has been one of the most popular datasets for summarization tasks in Russia. The dataset consists of news articles and their summaries from Gazeta news website. Titles of the articles is date, URLs, and additional information. We also introduced 2 additional binary columns, namely the gate column and the send column. As a base model, we took MBART model, which is a multilingual language model pre-trained on the massive corpora. And besides MBART, we also train 3 baselines, namely the standard fine-tuning of the transformer model, like RUTI5 base, RUGPT3 small, and fine-tuning of MBART himself. Because, of course, we wanted to compare just the performance of the fine-tuned MBART with the MBART incorporated in the HydraSum architecture. To compare the performance, we evaluated it using the classical metric, namely we used Rouge scores, measuring the quality of generated text with respect to reference summaries. Apart from Rouge scores, we also measured generated summary relevant metrics such as abstractiveness, specificity, length, and readability. Just in 2 words, abstractiveness is measured with the help of 2 additional tools, namely coverage, which counts the proportion of words presented in both input text and in the summary. Density, which counts the average longest continuous extract copied from the input text. And this metric for evaluating generated summaries was suggested in the paper Newsroom, a dataset of 1.3 million summaries with diverse extractive strategy. To measure specificity of summaries, SpeciTeller tool was used, and the length of summaries is measured by 2 additional metrics, its absolute length and the compression rate. Now on to the results. We see some significant difference between the performance of 2 individual decoders. The first decoder, which is called decoder 0 here, provides longer summaries and has lower coverage and density. Then the second decoder, it is called decoder 1 here. And decoder 1 is more extractive than decoder 0 and shows bigger coverage. The most extractive summaries were produced by RUTI5 and MBART, and most abstractive appear to be the reference one, showing the low coverage and density, which is predictable because is the true answer. So mixture of decoders produced more abstractive summary than each decoder individually. And in terms of specificity, all generated summaries have results which are quite close to each other. It can be explained by the fact that all models were fine-tuned on the same dataset and therefore they share the same vocabulary. However, individual decoders of HydraSum architecture have also shown different results of specificity metric. Decoder 0 has generated a summary with the lowest specificity score among all summaries, whereas the highest result on this metric were shown by a mixture of decoder and the RUTI5 based model. To sum up, in this work, we studied the application of the HydraSum method to the Russian language. We found that the first decoder in it is more abstractive, while the most extractive summary were provided by RUTI5, and mixture of decoder provided more extractive summaries than other models. And all models showed close results on specificity metric. The time is up and I'm practically finished. During our experiments, the HydraSum approach proved to be quite promising for the Russian language. And as a part of the future research, we plan to train this model with more decoders and on a big and more diverse data set to try capturing more stylistic features. Moreover, it is important to try manually specify the gating mechanism during the inference stage. So now my colleague Alona and I, we are ready to answer your questions. Alona, can you hear us? Are you here?
Yeah, I'm here.
This is Alona.
Hello.
Okay. Do we have questions?
thank you for the talk. My question about these metrics that you use for evaluation of decoders' behavior. Like naive question, is it possible to somehow adjust the behavior of the model or fine-tune the model towards more abstractiveness output, more specific, or something like this? So you, as I understand from the last table, you just measured these metrics, but is it possible to change the metrics, the output corresponding to the required criteria? Is it clear, the question?
Yeah, Alona, can you answer?
In fact, yes, because it's like the future work which we are going to do. When you are manually specifying the gating mechanism, you can do it yourself, so you can assign weights, and thus you can kind of change the output to be more abstractive or more specific one, by adjusting the weights, by assigning the weights yourself, and
So it's manual approach, right?
Yeah, you can do it manually, right?
Okay, thank you.
Thank you very much for your talk. My question is about the mixture of two decoders. As I have seen from the results table, the results are lower. So can you please a little bit elaborate how this mixture of decoders was done? Maybe I missed it. And why do you think the results are lower? Thanks.
Just a second. Yes, so the mixture of decoders, it's when the model it's when the model decides which output to generate. So it samples from both decoders simultaneously. So the result was lower.
I think I may add, in the mixture of decoders, we basically assign the mixture of probabilities from the two decoders. Thus, we basically obtain the weighted probability from the two decoder. And here, as far as I remember, we used just the averaging from the two of the probabilities from the two decoders. And thus maybe we should have carried out, and this is our future plan, to experiment with different decoder weights, so that, for example, the first decoder or the second decoder is more important in the result.
Yeah, thanks for the talk. So just a quick question about this mixture of decoders. So what about its computational requirements? So is it more, I guess it's more compute intensive than just using one decoder, right? So how much of a problem it is?
I'm sorry, I didn't catch it.
I guess when you are using a mixture of decoders, when you sample from two decoders instead of one, right?
That's right.
It means that, I guess it's more compute intensive. And what's like, is it like twice as expensive, or the dependency is not linear? So just how much of a problem it is? Will it be like twice more expensive?
Well, it is expensive. It took a long time, much longer than training with one decoder, and but it's not really a problem because I did it in my Colab notebook. So I kind of spent some resources on it, but it was okay to do that.
Well, I guess it depends on the size of the training data or the inference data, but just my question is essentially, is the dependency linear? So is it just the case that when you use 2 decoders, when you sample from 2 decoders, it takes twice the amount of time or compute resources as when you sample from 1 decoder? Or is it more complicated?
Well, dependency is more complicated because, as we've mentioned in the beginning, they have the shared number of layers, the bottom layers, they share the bottom layers. And that's why, of course, the inference from the 2 decoder is not twice as expensive as sampling from 1 decoder. But I'm not ready to write the exact dependency. It's much more complicated than
but it's less than twice the amount.
Yes, less than twice because they have some shared parameters just for this purpose to save some computational resources during the fine-tuning and the inference stage.
Right. Thanks.
Hello, everyone. My name is Anna, and my work is dedicated to machine translation for Russian Hakaz language pair. My goal is to present the results that we were able to achieve and also to try to explain how we did it so that you can maybe repeat it on another language pair of your choice. The Hakaz language is a language spoken in Russia by about 40,000 people. And have a very limited amount of digitized data, so it is considered low resource. Actually, there exist 60,000 pairs in Russian and Hakaz, and they are from TIL corpus of Turkic languages. You can see the results of training the baseline model exclusively on Russian Hakaz data. And as you can see on the picture, everything that is less than 10 is hard to get a sense of, and everything that's above 50 is considered high quality, good translations. So the basic approach to improve the results of the model is transfer learning, which means you initialize the weights randomly and then you pre-train the model on a resource-rich language pair. And then you take these weights and initialize another model with them and fine-tune it on a low-resource language pair. So the biggest question, one of the biggest questions was which language to choose for pre-training. We wanted it to be Turkic as well because we thought that maybe it will help the model to train well. And we also wanted to be in Cyrillic script because we wanted to use the shared vocabulary between the parent model and the child model. So here you can see the languages that meet these requirements and the sizes of the available corpora. So as you can see, Kazakh language is the largest one. But the problem about these languages is that the data is mainly web scraped and it is not of a very good quality in terms of translation, but also it tends to lean to certain domains like news or government documents. So we decided that we will stick to Chuvash language, mainly because it is manually aligned and checked. And actually, it is the second in size, so for quantitative reasons as well.
The preprocessing of the data didn't include much for the parent data because it was of good quality, and we just did some additional shuffling. And the child data from the TIL corpus, it contains some trash symbols, random numbers, but also the Russian sentences were of good quality, but Hakaz sentences, for some reason, they lacked punctuation at all, and also had some mistakes. But luckily, we had another corpus that consisted of 30,000 pairs, and they were of good quality, and also they were the same sentences that were in TIL. So we replaced the translations that we were able to get from electronic corpus of the Hakaz language, and thus we improved the quality of half of the data set. The next step was tokenization, and this was done by byte pair encoding with dropout. For those who are not familiar with this technology, I will briefly explain. It goes like you split the sentences by characters, and then you set up the amount of merging operations. So you first glue together the symbols that appear most often together in the texts. So on the left side, you can see the traditional byte pair encoding, and the dropout technique actually is the same, but you just skip some merging operations. For example, you can see on the picture B that on the left and in the middle, the RE are glued together, and on the right one, the RE is skipped, and it starts with AT. So this is a good way to kind of augment the data, because when you do the dropout several times on a source data and get different tokenized sentences, you can then assign the same translation to all of them, and you kind of increase the amount of the data you can train it on. So here's the short information about the setting that I used. I used transformer model in its classic way from the original article. I optimized the bibliometric, and I used the shared vocabulary between Chuvash and Hakaz data. The experiments I did was the increasing the share of the Hakaz data in the vocabulary from being the same amount as Chuvash to 1.5 times larger. Another experiment included dropout in byte pair encoding. And the third one was adjusting the maximum sequence length parameter, because it turned out that 99% of the parent data was about 100 tokens long, and the child data 75 tokens long. So we played with this parameter a little bit. And actually, it showed that all of these experiments combined show the best results in metrics, comparing and has quite a big improvement comparing to baseline. I also compared character F metric, which compares not word n-grams but character n-grams, and sometimes is considered better. Here I compared my results to other works on low resource languages, but this is maybe not very representative, because there's a lot of factors that affect the result of the model, especially for different languages, but just so that you can see how it generally works. What is more representative, though, is examples of the sentences that the model gave to us. You can see on the top example that actually the meaning of the resulting translation is like the same to the reference translation. And in the below example, you can see that sometimes the model still makes mistakes, like here it missed the word to study, basically. And the future work, it may include adjusting the number of byte pair encoding merging operations, because some hypothesis includes that the more morphological the tokenization is, maybe the model will train better. Also, traditional way is to expand the corpus, and also trying another Turkic or not Turkic language for the parent model. So this is all, I think, and I'm ready to answer your questions.
Okay, do we have a question? Oh, we have 3 questions.
Did you consider pre-training in on some other languages to enable better transfer learning capabilities? Let's say you pre-train on some other languages in unsupervised or supervised way, which might boost performance for Hakas?
Yes, of course, this is a future work. We will try different languages and maybe just the NLB model, whatever, so that we can compare the results.
Do you have any idea, like, which languages are more beneficial, less beneficial? Because some might hurt, some might improve.
Yes, actually, I read some articles about this, and the main idea, I think, is to be similar in morphological structure. Because, for example, when you translate from English to Russian, then in English it will be the same word for all the cases and things like that. And it is difficult for the model to catch those differences. So the more complicated, I think, the language for the parent model, the better for the child model, since Hakas is very morphologically Eurasian.
But not necessarily the same linguistic family.
No, actually, there are studies that show that the size of the corpora makes the biggest difference. So they even pre-trained, I don't know, on Finnish language and fine-tuned on Turkish, something like that. And they still managed to achieve some good results.
Yeah, actually, some colleagues had similar experiments, and yeah, that was counterintuitive to me, but yeah, they pre-train on some completely different language, but with a similar morphological structure, and that actually give a boost. Okay, so makes sense. Thanks.
Thank you.
So thank you for your talk. I have a small question. So are you familiar with Hakas language, or is one of your colleagues knows it? How did you evaluate the results?
I am not familiar with Hakas language, but I know some Tatar, and it is quite similar, so I could actually visually evaluate it somehow. But for the sake of science, my translations were evaluated by the native speakers that I asked to do it.
Thank you.
Thank you for the talk. I have a couple, I think, technical questions. Could you please, maybe I've missed that, just elaborate a bit more what kind of model did you use?
Just transformer architecture with 6 encoder and 6 decoder layers and 8 attention areas.
I see. Okay, and with Blue, right, what kind of, I mean, for Blue evaluation, what kind of tokenization did you use?
It was the same tokenization as for the training.
The BPE thing?
Yes,
okay.
yes.
Well, that's interesting because maybe for the sake of, I don't know, getting a different view on the quality, maybe you should try to, I don't know, try some like raw tokenization by or some, I'm not sure about the existence of morphological analyzer for Hakas language, but something like stemming lemmatization and raw tokens, because this can give a different perspective on the evaluation. It's like the same issue that was widely discussed at the time when character level machine translation was popular. So that's a bit different thing. So and definitely worth comparing, I think.
Yes, I think we can do that.
Yeah, thank you for the talk. I have not a question, but rather a suggestion. You have said that one of the corpora was in some other script, in Latin, probably. Maybe you could use just some transliteration scheme and augment the data that way?
Yes, as I said, we wanted to be it in Cyrillic because we thought, first we used the shared vocabulary, but the transliteration crossed our minds, but I actually didn't find the good transliteration tool because, for example, for Turkish language, it is very difficult. It has many rules, and to transliterate it to Cyrillic is a very complicated separate task. So I didn't find the tool, and I didn't go for this idea.
Mm-hmm. Yeah, as far as I know, for like some languages exist like specific transliteration schemes. So if someone has developed it, it could be used.
I will have to look at it. Thank you.
Thank you.
Okay, more questions? Let me check with Zoom. Okay, we don't have questions in Zoom, so thank you.
Thank you very much.
And the next talk will be online.
Yes, that's true. Nice to meet you. I'm Zaitsev Alexey, and I'll be talking today about how difficult it is to make an adversarial attack for machine translation models. I have two authors that did most part of the job, most part of the experiments in writing, and I want to thank them, Pavel Burnyshov and Elizaveta Kostinov. We are participating in this project as well. So let's start on what and why we are doing. So basically, okay, all models, or most of the models we see today in NLP are neural networks. And we often see some very weird examples on how they work if you know the right way to attack it, how to make it do what you want, and what is, for example, is prohibited by the model actors. So it seems like a good goal to try to examine and how can we find some big points of a model. Can you hear me? Is everything well?
Alexey, we can
Yes,
see
yes,
your
we can.
slides. Let's wait a little bit.
Okay, maybe.
But we in Zoom can see your slides?
Yeah, we can see in Zoom, but we can see in the audience.
Oh, okay, let's wait for a couple of minutes. Oh.
This is where the hybrid conference starts.
Yeah, we're still waiting for slides.
Okay, I think the problem is Armenian internet.
No, I
We
don't
can
think so.
hear you, but we just can't see. I guess it's some connection problems.
I can try to share one more time. Maybe it would be better this way.
Let's try. Maybe it will work. I'm not sure.
Let's
No,
see
it's-
this. I suppose the problem is maybe that you kind of don't display the presentation on the screen for some reason. Maybe you should move something somewhere.
We can all move to Zoom, I guess, right? We all have separate laptops, so just let's open it and join Zoom. Okay, let's wait for 1 2 minutes. Probably it will be fine.
Yeah, I believe it has something to do with how Zoom translation is set up there on site.
Okay, I think the problem is that, okay, the display here, I can see the room. People are in, yes, and I see that the screen is kind
Yeah,
of.
we see the screen. Now you can see from my laptop what I see.
Yes, I see in two ways, and both ways I see that this is not my presentation for some reason. I don't know. Can someone try to kind of to see how the Zoom is working for the laptop in the hall, in the room?
I don't know. Let's wait from the team to manage it.
Okay.
We're trying.
But Lena, does the on-site team is the on-site team already working on it, or?
Yeah, they're trying.
Okay, they're trying. Cool. So there is still some hope.
Yeah, the work is going on. Maybe we're restarting the computer, I don't know. Sounds like the good option.
But you also can't see the videos of the online participants on the large screen there, right?
We still see the same slides about the conference.
Yeah, so just the placeholder.
So basically, I think that you should somehow move. I don't know what can be a problem, but okay, I'm not here, so it's very
Let's
hard.
probably leave that to the
We can move
to the local
to a live
organizing
session,
team.
I guess. Yes.
What I can do, I can
While-
do for all of you. What I can do anything for now.
I can show you the org team if you want.
Oh yes,
Train
yes.
new
Actually,
people
I see.
here.
Yes, another camera is kind of showing me.
Yeah, we
what's
can
going
see the
on.
video from the large camera.
Yes,
So,
yes.
But yeah, maybe indeed it's easier if for now just all the on-site participants simply join the Zoom room. So as to
We
see
have
the
10
slides.
participants here.
10 participants.
Let's count all
Let's
of them.
wait for a couple.
Oh yeah, we
more
see the
minutes.
slides now. Yeah, good.
Oh, very
Now we
good.
can.
Oh, cool.
Very good. Very
Perfect.
good. Thank
let's
you.
move on.
Can I continue now?
Yes, please continue.
Okay, so what is the problem? We want to find some vulnerable points of the model, and we can try to find this with adversarial attacks. So basically, adversarial attacks are a way to find these vulnerabilities. We try to find in an efficient way on how can we break the model, how we alter the output of the model by small enough change of the input. For example, we can see the following idea here. It's an example of an attack. In the bottom, so we have some model that tries to mark this input flat misguided comedy to a label. In this case, you can see that it is definitely a negative review. And so we try to fix this input with as small change as possible. So in this way, in this example, we change flat to witty. Basically, the meaning is almost the same. And in this case, the model outputs positive label, marking that we succeeded in breaking the model. And now the label is not correct because definitely it is still not a positive review, but okay, models think it is positive. So the question is, how should we design such attacks to common classification models for NLP, or, for example, translation models? The problem, maybe the main problem for this area, is that we don't have differentiability, and the search space for NLP is discrete, and we somehow should move in the discrete space, looking for adversarial attacks, for adversarial changes of the input. Basically, what we can try to do, we can try to, for example, in hot flip, calculate the gradient with respect to particular token in the input. And so we can try to say that if we have this first order approximation of what is going on, we can then find what and how we should change to change the loss most, and what we are doing and what's a pretty successful strategy. And also we can try to use more advanced models. This was proposed in our previous paper. It is based on the idea that we somehow should modify the loss function when designing the adversarial attack. So basically what we can try to do, we have this input sequence x1 is on the right, x1, x2, x3, and so on, xt, where d is the length of a sequence. And we want to train a generative model to modify it. So now the output is some x prime, x1 prime, x2 prime, and so on. And so what we want from this sequence, we can formally express in the loss function. The first is a classifier. So we want the label of the output to be different from what we have for initial sequence. And this we can encode with this second term here. And where C capital is the score of a model. Also, we can try to say that, okay, we should not be far away. And this deep Levenstein distance or whatever other distance like blur or similarity we wanted the similarity of x prime and x to be high in terms of how many tokens we change or in terms of some semantics metrics. And in this case, we design the loss function and we can backpropagate using the softmax trick into the generator and make it generate adversarial examples. This is what we can do. And this also transfers problem from a discrete optimization problem to continuous optimization problem, so we can try to adjust it. And basically, this idea is followed by another one that allow us to do practically the same thing, but for machine translation model. Basically, we try to find the change in the embedding space that leads to, okay, small change of the input, but a significant change in the output. So we look at this gradient, the scalar product of the gradient of the adversarial loss and our embedding. We try to find the embedding that is good, and using this embedding, we generate back, decode the adversarial sequence, and also change, we hope that we will change significantly the output. And this we can proceed in different ways. For example, we can say that, okay, we have another, we have this loss function, and we focus on predicting blur, and blur for the initial sequence should be high, so we should not change x significantly. But if we look at blur for a pair of y and the adversarial translation y prime, should be significantly different, and we can directly organize flow of the gradients in all parts of this model and train it to generate, to find good candidates for adversarial attack. So it seems like a very natural approach, but does it work? Let's look at the results for classification problem. Can we change with our generated Dilma model the input and obtain good results? And the thing is that yes, we can. And what we're looking for in this table. We have 4 problems, and we have the accuracy for these problems. Before attack, the scores of the accuracy is pretty high. It's like, for example, for AG is 0.95 here. But what's going on next? After different attacks, there are some SOTA attacks, and the last 2 approaches are different variants of our attack. And we see that if we use our top performing attack Dilma with deep Levenstein distance, we have for some problems almost 0.5 accuracy. That means that we can almost broke the model here and here and significantly decrease the quality of the model for AG and RT problems. And so what else we can look? What we usually should check as well is that our change in the meaning is pretty small, and we don't change much the semantics of the sentence. And we can try to achieve this by looking at the scores of this right part. This is the score of a discriminator. So what is discriminator classifier? We generate a sample of adversarial examples, adversarial sentences, and we have a label that it is an adversarial sequence, a label 1. Also, we can check for label 0 for common natural sentences from our sample, and we can try to train the classifier, and we see that in many cases this classifier are not very good for our attacks. It means that this discriminator, even after training, can distinguish adversarial examples and normal examples. It means that our generative model and our generative attack works pretty well if we try to solve the classification problem. But let's go to the main goal of the paper. Let's try to check if we can do this for adversarial attack on machine translation models. And basically, what we do, we run the attack with different hyperparameter value that corresponds to the power of attack, how much we should corrupt the output or an input, because it's definitely these two correlated things, how we change the input and the output. Okay, that what next we can do, we try to assess the quality of what we are doing of the attack. So we basically look at some similarity score for the initial sentence, the changed sentence X prime after an attack, and the original translation, and the translation after an attack. So we want this guy similarity to be large, and this similarity to be small for a successful attack. So basically we need to plot both of them. So let's do this and look at what's going on. So we tried different sort of attacks, and see actually what's going on. So each point here is a different hyperparameters setting, different colors corresponds to different sort of attacks. And basically where we want to be here, where we have a similarity between initial BERT and for initial sequence X and X prime attacked, but low similarity between the translation after the attack, so between the Y translated and Y translated after the attack. And as you can see, for all metrics, despite we want to be here, we have small improvement. I would say that, for all class of methods, we have, significantly lower the diagonal, which means that we slightly lower the diagonal, which means that we slightly change the change in the input and the output are pretty much the same. And also an additional experiment shows that in sometimes we still can be pretty successful. We added another type of attacks that's called character-based attacks. We swapped characters, and also we combine this with the gradients, and we can see a new group of points here that again corresponds to the different for the different parameters. And generally we see that we change the input less than we change the output. It means that in this case we can attack machine translation models. Basically, we think that this effect comes from the idea that we need to find some weak spots of deep translation models. And basically, it's not an easy task. And we should focus on something that lies outside of a training sample of such models. And swaps of characters make us to get here and to improve over the baselines. So basically, it means that if you want to change the classification label, we still can try to find some change in the input to get change of this label with very small perturbation of the input. If you look at machine translation models, the situation is different. Typical approaches doesn't work here, and what we can do is try to go to the character level, and in this case, we are pretty much successful. So we can say that machine translation models are pretty strong, like many other sequence-to-sequence models that we think. So that's all about my talk. Do you have any questions?
Any questions? Okay, we don't have question in the audience. Oh, we have one question in the audience.
I don't know if I understood you right, but do you check that the sentence that you change, for example, about the review that you showed in the beginning,
Yes.
do you check that the actual meaning of it stayed negative, but the label changed? So,
Yes, yes, I can try to show some examples from the paper. And you can see that typically, okay, the change is pretty small. And if we show this to a human, we would say that it still would identify something like this. Okay, the first example maybe says that this changes to something that's not very meaningful. Here we say that, okay, human can say, okay, it's a misprint, but definitely it's a gallon. But after translation, we see that, okay, the translation is pretty different, and the meaning is not the same for even machine translation, for kind of some successful examples.
so you check that the meaning stays the same while the label changes,
Yes,
right?
yes. Actually, okay, if you're talking about the first paper, we even did some human evaluation, and they say that in most cases, the meaning is pretty same.
Okay, thank you.
You're welcome.
Okay, let's thank the speaker again. And
Okay,
the next
thank
talks
you.
also will be online.
Okay, hello everyone. So let me share my screen just a second.
Let's hope it will be better than last time.
Yeah, here. So can you see my screen? Yeah. Can you hear me?
Yes, we can hear you.
Yeah.
See the screen.
Super. So, good day, everyone. Let us start. So the prevalence of online shopping has made it the foremost method for purchasing various goods. The online customer reviews play a crucial role in providing valuable insights into customers' interests and knowledge of the product. But how can we discover these insights automatically and formulate them? Our paper, User Review Summarization in Russian, researches this question. So, what is user review summarization? The logical extension of text summarization is multi-document summarization, where we summarize multi-documents. But from the multi-document summarization stems the opinion or user review summarization, which uses the specifics of human opinion presentation in various sources on the internet. Here on the slide, you can see an example of user review summarization. The input consists of reviews covering different features of the entity in different colors, and the summarization model should analyze given reviews and produce a summary which should cover all the reviewers' opinions. So the researchers in the field explore both supervised and unsupervised settings, but while supervised setting is widely used due to its effectiveness, it's obvious, it requires golden summaries for training, which can be extremely difficult and resource intensive to produce. Moreover, actually the majority of the existing studies focus solely on the English data and neglect non-English languages because they lack publicly accessible resources. This hampers the opportunity for broadening our understanding of cross-linguistic properties of our summarization, and we try to change it to collect the data set. In recent years, the researchers suggested a lot of methods for opinion summarization. Some of them suggest using automatic data aggregation, while others use weak supervision in the form of seed words for further major topics identification. Some articles suggest using information about such topics or aspects to model summary generation. During our work on the project, we experimented with the best performing contemporary abstractive and extractive models from the articles on the screen. We employ different methods which use sentiment and aspect information to create a summary. As our work focuses generally on the data and training and not on the architectures, let us overview only the main ideas of these methods. The first method that we will be reviewing is plan sum. It extracts sentiment and aspects distribution from the data and then fuses these distributions and token embeddings. The result of the fusion are then fed into LSTM decoder with attention, which composes the actual summary. Another method, AIST', does not have a colorful scheme, but mainly it uses multiple instance learning model from the previous works of the authors to induce aspect controllers and then feed them into the transformer model, the original transformer model. The controllers are actually calculated using with supervision in the form of manually collected seed words. Another method is quantized transformer, which uses transformer encoder and decoder to quantize the sentences of the reviews to find the average opinions, so as valuable aspects, and formulate it with the existing using the existing sentences. And the last work which we review in this project is the semantic autoencoder, which continues the work of quantized transformer, but creates the distribution of aspects and ranks them and chooses the top elements as the basis of the summary. So let's talk about the data. The standard data sets for opinion summarization in English language are Rotten Tomatoes, Yelp, Amazon, Opposum, and Space datasets, each presenting data in different domains. Unfortunately, from our knowledge, there are no publicly available datasets for user review summarization in Russian, and the majority of Russian online services do not allow to use their data. Therefore, the data was collected from the open internet source tripadvisor.ru with the help of web scraping. Resembling the collection of Space dataset, we collected around 1 million reviews of hotels from 11 cities and structured the data in a convenient way. As requested by one of the reviewers, which also show the statistics of the collected datasets, some of the data distributions, but as you can see, the statistics are fairly similar among the train, test, and validation splits. The labeling process for the validation and test splits of our datasets involved manual annotation by us, the authors. Similar to Space datasets 25 summaries per split, we created 28 summaries per split. We wanted to compare the performance of the models trained on the collected Russian data and the existing English datasets, which is why we followed the annotation of Space dataset. The set of aspects was taken from AIST' paper, translated to Russian and fixed for manual summary construction. Every hotel was labeled based on 50 reviews stratified by rating to ensure that both low and high rating reviews are present in the data. We manually filtered the concepts and phrases corresponding to specific aspects and chose the most repetitive of them as a summary basis. We admit that the human written summaries might provide some restrictions on the operation of models and leave this for further research. We choose models with the highest metric values on Space and Amazon datasets, which utilize aspects information for the correct comparison on the Russian language dataset. During our experiments, we tried abstractive and extractive methods and compare their performance. Some methods were not taken into consideration because they either utilize self-supervised learning apart from unsupervised learning in these methods, or propose novel algorithms which do not consider sentiment and aspects information. For our experiments, we employed the Rouge metric because it's a standard metric in this area. We also experimented with changing methods pre-processing and seed words extraction steps, but as this did not lead to any improvements, we wouldn't stop on this. Here you can see the results of different models evaluation. All the models were trained on the collected data, but the models with FT postfix were additionally fine-tuned on the small part of translated Space dataset. While the evaluation on the collected dataset shows clear dominance of fine-tuned AIST', evaluation on the Space dataset shows several well-performing models, among them fine-tuned AIST', which shows the highest bigram Rouge metric, and variations of planned sum, which show higher unigram and longest common subsequence metrics. Having conducted a manual analysis of the produced summaries, which can be also found in the paper, we found out that abstractive summaries contain more specifics from the reviews. extractive summaries contain more general information. But on the other hand, quantized transformer and semantic autoencoders, so as extractive summarizers, included personal information in their summaries. And PlenSum, which produces more human-readable texts, catches in direct relation to aspects, while AIST'' described the fixed aspects more precisely, but with limited lexical variety. So in this work, we explore the application of modern solutions to the Russian language user review summarization. We managed to collect around 1 million reviews of hotels and annotated parts of the data for evaluation. We compared models from unsupervised and weakly supervised settings. The best performing models among the approaches were adapted for the Russian language analysis and trained and fine-tuned to summarize the opinions in the hotel domain. Our conclusion is that abstractive approaches outperform extractive approaches on the collected Russian dataset, in contrast to findings for English data presented in the recent article proposing the semantic autoencoder model. So specifically, the best performing model on our data is AIST', and on the space dataset are PlenSum variations. Further research may focus on the stylistic limitations of human written summaries for better model performance, coherence and readability analysis of the summaries and ways to improve them, researching the self-supervised methods, which are actually excluded from the comparison, as some of the well-performing models on the standard datasets. So thank you very much for your attention. If you have any questions, you're welcome.
We have one question.
Hello. Thank you for the talk. I think about 3 slides ago, you've provided quite a cool, this one, quite a cool summary of the specifics of each models and of their performance on the reviews you've collected. And I wonder, is it possible to, well, some of these specifics clearly are, but is it possible to measure all of these effects? Were you, I don't know, going to do that?
It's actually, first of all, these are the findings of the work we've done, so it may differ from more general information, but that's what we found out. And secondly, it was measured manually, as I mentioned before, because the test and validation splits are actually not that big, so we managed to measure it manually.
I see. Could you please remind me what was the size of, the data sets based, the size of the part of the data set that you were, making the conclusions on, based on?
Okay, so we followed the annotation of space dataset, which actually achieves some kind of good results. They had 25 hotel summaries. So for every hotel, we have a review set around 100 or 200 of reviews. And for each of the hotel, we create a summary. So they had 25 summaries for validation split and for taste split. So overall 50 summaries. And we had 28 summaries for both splits. So 56 summaries in total.
I see. Thank you.
You're welcome.
Thank you very much for your talk. I was wondering, do you consider now only the hotel reviews, or do you plan to do more on other topics, or it's just hotels now? I'm kind of missed it from the talk.
As you can see, the standard data sets, you can see it, but anyway, the standard data sets review the different domains, but we chose the space data set because it states the most clearly the procedure of collecting and annotating the reviews, and it was the easiest domain to start from. But of course, it is a bright prospect of the research to try with different domains, which were actually done in English data in different articles. So yes, the answer is yes.
Thank you.
Okay, more questions? We don't have questions in the audience. Zoom part? Okay, I guess we don't have questions on the Zoom.
Well, we do have questions on the Zoom.
We have? Okay.
Yes. So yeah, just a quick question. Thanks for the talk. And as far as I understand, you annotated the reviews. Well, you wrote the summaries for the reviews based on a set of aspects taken from like one of the prior works, right? And of course, this choice of the aspects influenced the resulting summaries quite a lot. So do you think if you choose another set of aspects, your findings would be much different?
About this, we actually explored this avenue. So we tried to find the seedword extraction methods in order to comprise a different set of aspects, different from the aspects from AIST'. And we tried all the different word embeddings, all the different methods described in different papers, but actually it didn't produce any better metrics according to like summarization metrics rule, which is why we stick to the AIST' set of aspects. But if anyone could find a better way to extract aspects, that could be another avenue of the research.
Yeah, I guess it was not exactly what my question was about, because you evaluate your model on the summaries which are written by humans, taking into account some set of aspects. So your gold standard will be different if the aspects are different, right?
Yes, of course. So yes, the production of summaries was based on the given set of aspects. The set of aspects was taken from the AIST' method, and they actually like provided it because they collected it manually from a great from a great experience, human written, and they extracted the most valuable aspects. But if we had another aspects, we could also experiment with that.
Yeah, so my question was about your expectations. So if, for example, your current set of aspects includes things like cleanliness of the apartment, I don't know, like the food quality, etc. But if you choose some completely different set of aspects, I don't know, just like the easiness of finding the hotel or something like that, do you think that your ranking, like your results will still be the same? What is your expectation? I'm not sure whether you did these experiments or not. Just
I understand now. It is quite difficult because the model generates generates the summary based on what it was trained on. So I guess it can find different aspects, and it would give even lower quality, but better summary, if that makes sense. So probably Rouge for that purpose is not the best metric, but the one that we used because we had the fixed set of aspects.
Okay, thanks.
Thank you.
Have a lunch break.
Yeah, and I guess we should announce that. Please don't forget that we will announce the best paper during the closing session. So please make sure to attend it so as to learn what is the best paper in the NLP track.
Yes, it's true. See you soon after the lunch break.
See you.
Thank you.
Բարև ձեզ, կասեք ձեր անունը։ Մի հատ անգլերեն։
Բավական երկի ելը։ Նայ հասնիկ։
Բարև ձեզ, կասեք ձեր անունը։
Հասնիկ յոտկը երկի։ Սա մի հատ ABCD երկի։ Դովայ։ AB։ Հետո սվարկես էլի։ Սա դու երկի, դավայ։ Երկես բաբարդ։ Չէ, չէ, բարի։ Ասա, եթե ստեղ լավ երկես, հանելու եմ այն ամբիոնից է երկես։ Դավայ, երկին անդերից են։ Դավայ։
A B C D E F G H I J K L M N O P Q R S T U V W X Y and Z. No, I know A B C. Next time, won't you sing with me?
High five. Դրանք ամբիոնից է երկես մի հատ հետո գնաս դավայ։ Մենակ մեկ եք, մարդ չկա։ Նա հիմա ես երկեմ։ Waka waka waka։ Արի։ Սոմիկ խնդրում է։
Արի շուտ պապան զանգեց, պիտի գնանք արդեն։
Հա։ Հա, լավ, ABCD, բայց ուզում ենք waka։
Դա վակա երկի։
A B C D E Samana waka waka Samana sangarewa. It's time for Africa. Samana waka waka Samana sangarewa. It's time for Africa. Samana waka waka Samana sangarewa.
Դուր եկավ։
Բարև Սամվել ջան։
Բարև։
Ո՞նց ես։
Լավ։
Ա դու։ Սամվել ջան, ո՞րն է քո սիրելի մեքենան։ Ես գիտեմ, որ դու մեքենաներ շատ ունես, չէ՞։
Հա։
Ո՞րն է BMW։ Porsche։
Հա։
Porsche թե BMW։
Porsche։
Porsche ո՞ր գույն է։
Կարմիր։
Սամիկ։ Էլի կգաս չէ մեր մոտ։
Ահա։
Սամիկ վերջես դու։
Ես ասա, սրտիդ խոսքը ամերիկյան համալսարանի ասա։ Մի հատ պատմի։
Բարև ձեզ, ձեր անունը ի՞նչ է։
Բարև ձեզ, ես Հասմիկն եմ։
Իսկ ձեր։
Որմից դուխտ։ Ասացի, որմից դուխտ։
Իսկ ձեր։
Մաչական։
Իմը Սամվել։ Լավ։ Մենք Սամվելն ենք։ Մենք ապրում ենք ամերիկան համալսարանում, չէ՞։ Դե գնացեք նստեք։ Ամայան ուր կնա։ Ես գնում եմ աշուն, ես քեզ շատ եմ սիրում, աշուն, ես ձմեռ եմ սիրում գնալ, ես ուզում եմ գնամ ձմեռ, որ շուտ անցնի աշունը, չեմ երկե, չեմ պատսել։ Լավ։ մեր թանկ, տուր մեզ բանկություն, որ վաղը կերտենք մի նոր պատմություն։ Բեմը դարձել է շքեղ, տոնական, դահլիճը մտել շքերտ մանկական։ Բարև ձեզ։ Որ? Բարև ձեզ։ Լավ, երգում եմ։ Սամնամնա եկերվա։ Սամնամնա waka waka Samenamena Sangarewa is time for Africa. Samenamena waka waka
Sami, gehst du nun dünya program çevir tatlı sukas olsun.
Hello? Hello, Artyom, can you hear us? Artyom, can you hear us?
Hello. Hello, hello.
Yeah, we can hear you. Can you try to share the screen?
Yeah.
Okay, perfect. So we can see you. Okay. But, okay. Okay, so we can see your presentation. I think it's time. So are you ready to start? Okay, so let me just first introduce you. So
yeah, sure.
Thank you for coming. So Artyom was supposed to be here, but unfortunately for some personal reasons had to cancel his trip last minute. Nevertheless, it's a great pleasure to me to present another very interesting speaker from Emirates today. Artyom, I know him since 2019, and I should say that he always amazed me by his energy, dedication to NLP research, and to dedication to the topic as well, which he's going to present today. Over this years, so I've seen how Artyom emerged into really a leader in this topic, in this field. He studied a lot on active learning, uncertainty estimation techniques, and published extensively at the very top conferences and continue to do so. So his record track in NLP is really impressive. And today we will learn about this very important, I think, topic, uncertainty quantification and generation for NLP, and more specifically for LLMs. So without further ado, Artyom, please go ahead.
Yeah, thank you very much for the kind words. I'm very apologize that I cannot be there in person because of health issues. But never mind. I mean, let's dive into very interesting topic. Currently, I mostly work on safety of NLP models in several ways. And yeah, let's go ahead. So we'll have some introduction, uncertainty estimation background. Yeah, this topic will be more focused on uncertainty estimation and especially on uncertainty estimation for language models. I will also present our last effort regarding, summarizing and systemizing these diverse works on uncertainty estimation for language models in one package, in one Python library. And finally, we will conclude with some suggestions. All right, so first thing first, we know that language models are very good, becoming very good in multiple tasks. And basically, regardless of what task you will pick up, you'll find something like that on the papers with code that we approach or exceed the human baseline. You can see that, well, mostly every task might be considered as solved, or maybe most of them middle complexity tasks are solved. But plain performance as accuracy is not the only thing that we want to pursue. There also safety, and this safety is related to two other aspects. First of all, it's bias and reliability. So let's start with bias. So what do we usually have? We have some, data with some problems, with maybe some garbage, and maybe some biases, some, biases, spurious correlation between target variables and some, some feature that shouldn't be really be taken into account. And we train a model, and we get, of course, a bias model that picks up on these particular dependencies and use them to do these predictions. which is, of course, not good. Because, well, we can think about many biases. For example, one of bias, like if you classify a mood person by a picture and you pick up like a color of his eyes as a feature, that's probably one example for bias which you shouldn't take into account, because of course, like the color of the eyes doesn't make any sense for predicting the mood. But due to your data, you can pick it up as a viable feature and use it in the future. So what we want to do is, in debiasing in fairness, we have like a garbage data with some biases and eventually getting an unbiased good model. So how we can do this? Yeah, one important case of bias in NLP, which is usually considered, is social biases and stereotypes, like depending on gender, race, age. And here's one example where we try to determine the profession of a person, where we try to determine the occupation of a person, want to determine whether a person will be a surgeon or a nurse. And we can find out that sometimes classifiers just look at the gender of the person and just put all women to nurses category and all males to the surgeon category, which is completely unfair and should be avoided, of course, in practice, because if we do this, we will facilitate biases in the data in our society, the stereotypes. So how we can deal with this? Well, there are a few techniques that we can apply to our models. These debiasing techniques that reduce the importance, reduce the effect of bias in the original training data. First, we can reweight instances in the training data. So the signal from the loss, from the training loss, will not bring this spurious correlation between protected attribute and the target variable. Another case is when we try to unlearn or forget about some protected attributes in our representations, future representations. And here, for example, we have this additional loss component that help us to forget about like gender, race, and other stuff. So the model cannot predict from the feature representations these protected features. So eventually it becomes less biased, more balanced. All right, that's how we deal with bias. Now let's go to reliability. Okay, so what is reliability and why we should care? First of all, let's look at this an example. As you can see, there's like a banking application where a person asks for his balance. Well, this banking application works perfectly fine when the questions are related to the topic. But when a person asks something unrelated, like from the sports, it tries to answer his request in the way it was trained to do, and it fails because it answers gibberish, something which shouldn't be answered. And that is an example of out of distribution question, where the person asks something from the domain which is not part of the training domain of the model. So instead, it should be probably saying that, okay, sorry, I can't answer your question because it is not my type of concern, not my type of domain knowledge. So, all right, so that's one of the example of out of distribution input. Another example, well, a little bit more critical, safe critical application, diagnosis in medicine, where we have, for example, some symptoms, input symptoms, or maybe anamnesis of a person, and your model has to make a diagnosis which might affect the treatment of the person of the patient in the future. And of course, there might be some out of domain questions, like it should try to avoid, try to ask a person for the help. But it also can be some situations where we have something like very close diseases like SARS and COVID, and it's very difficult to distinguish between them with this particular amount of information you have. So you probably should try to ask for a physician or a real person or another more complex system to make a decision for that, instead of like making a diagnosis that probably can harm the patient in the future. So that's two examples. Let's go ahead. So what we have in reliability, we have to always remember that model capabilities are very limited. First, due to limited amount of data it was trained on, there's always like a training data set and it's limited. And going beyond this data set always has a risk of, making model answers completely unreliable. And it's also a situation when our task has ambiguities, like in SARS and COVID, where it's very difficult to distinguish these two diseases with a lack of information, lack of features. So this second thing, ambiguity in the task, is another concern. We have to spot these areas of ambiguity and also try to abstain from making any decisions in these. So what we need to do to achieve reliability is to develop mechanisms that take into account these limitations when the model is deployed. And reliability is basically a capability of our system to apply this mechanism in a perfect way to detect out-of-distribution instances, detect ambiguity, and many other stuff, like maybe adversarial attack detection. So, okay, so how to handle reliability, how to make your model reliable. This slide is a little bit marketing here because basically we're promoting here some our work, which was published in ACL in 2022, in 2023, and other conferences actually. There are some, solutions to reliability problem in terms of selective classification and auto detection. The last one will be published in ACL this year. It is intersection between bias, debiasing, and uncertainty. But of course, there'll be a lot of, there are many more works in NLP and uncertainty for NLP, and we will discuss them later. Just a small slide here about our work. Okay, so our new concerns, what we have today. Today we have generative AI era, and in generative AI era, models can generate something inappropriate, something that shouldn't be generated. And in particular case with ChatGPT here, is a case where it gives an incorrect answer. Here we can see that we're asking how many letters in the word 19, and it's incorrect. Then we ask when we try confuse model even more, and it becomes even more confused. So yeah, this happens all the time with language models. And be sure I check this example for this lecture. And well, the first one was fixed, but the second one is not fixed. You can still confuse the model into thinking that there are like any number of letters in the word 19. Another example, I apologize before Alex Panchenko for that, but this is a question about his biography, like tell me about Alex Panchenko, and the model also hallucinates some facts about his biography and very confidently say that he's a professor. I mean, like he will be probably in the near future, but right now he's not a full professor in Hamburg, but it's pretty convincing in saying that, saying some false facts about Alex. And that happens all the time with such kind of models. So what concerns we have in the era of generative AI? So models can generate unacceptable output, and we should first consider the hallucinations, like the false facts that they generate. We also should consider something like toxicity, because the model can be trained on, can have some leaks of toxic text, and we should avoid that. We also should care about truthfulness, because sometimes model cannot do the task, and it should be quite explicit about that. I cannot do this. It should be truthful. And also one thing which is commonly put into consideration is personality, that the model should not pretend somebody else. It should be explicit about its personality, that it is a model, it is like assistant, it's not some sort of like a human professor, etc., giving you this answer. So how to deal with these problems? In general, there are a few ways to do this already, and people are applying currently to all this language models, YandexGPT, ChatGPT, and others. It's reinforcement learning, of course, where models is trained on a big amount of scores of assessors and these scores are essentially aim to reduce bias, reduce toxicity, reduce many other issues with the model. There are other approaches to this problem, like contrastive learning. You can also just fine-tune on some good answers that people craft by themselves. Also, you can do some filtering of the input data or output results with a stop list and other stuff. One of the colleagues that were visiting MBCI was from Microsoft Turing and said he like stop list is a way to go with the language models. Very good thing. It works much better than anything else. Fact checking and another stream of work where people try to look at the output of the model and do some, fact checking with the databases. And finally, which is I think one of the most important and most interesting for me, is uncertainty estimation. Can we apply uncertainty estimation for language models? Right. First of all, let's just go through uncertainty estimation background. I hope pretty fast. Again, let's consider one small example here. Consider we have a classifier that is trained to distinguish cats and dogs, and it works perfectly when it has perfect picture of cat and perfect picture of a dog. It works good. It predicts what it was intended to do. But what we have here is something weird, which cannot be classified into a cat or dog class. Here probably model should output something around 0.5, like something 0.49 or 0.459 to demonstrate that it's something weird, it's something super uncertain, and maybe we should call a person or something else to work with this image. But unfortunately, this probability scores that obtained through softmax classifiers are not very good. The reason is here. The softmax probability it can be used as a uncertainty estimation score, but unfortunately it gives you uncertainty like this. So in most of the area, you are completely certain here and here, and you only uncertain in this small decision area between two classes. And that's what we get from a softmax classifier. But in case of our example with the cat and dog, this cat and dog image can appear like anywhere. It might appear something like here, here, and of course, in these areas, we'll be completely certain and we will predict a particular class. So overconfidence is a problem of softmax probability uncertainty estimation. So what we really want to have is something like on the right picture where everywhere we don't have any particular evidence and we don't have any training data, we are uncertain, and also we are uncertain in the area between two classes. That's what we want to have. All right, so that's why we cannot use softmax probabilities. Well, we can, but sometimes it doesn't really what we want to. Okay, so what is uncertainty in particular? Well, there's no unified way of specifying uncertainty scores. It can be anything which works very well for us for our task, like OD detection or selective classification. It might be like some sort of distances, probabilities, entropy, of course, or error, estimation of an error. But well, in biasing theory, there's a particular way of defining uncertainty, and this is basically entropy of a probability distribution. Consider we have a training data, and we can say that uncertainty is basically an entropy of predictive distribution, and this predictive distribution can be parameterized with a neural network. And of course, if we are Bayesian, we probably would like to put some sort of like prior on our parameters, so they have also some sort of distribution. And then we can rewrite our predictive distribution in this way. So we have this formula which we can put it into the predictive entropy formula and get something like this. But of course, I mean, we could do this in a Bayesian way. We could try to estimate everything correctly using some sort of approach from the Bayesian theory. We can do some variational inference, etc. But usually we don't have a way to do this. Usually the Bayesian neural networks is very hard to train, and they usually very difficult. They also have several drawbacks, like storing additional weights and other stuff. So let's go back to types of uncertainty and look at our classifier again. Here we have a situation where we have a lot of information, a lot of data, and we have a lineal classifier that tries to distinguish two classes. But unfortunately, in this area, small area between classes, these classes overlap. This is an example of high aleatoric uncertainty, where we have noise in the data, where we cannot easily distinguish between two classes just simply by drawing a line. So in this situation, we are saying that we have high aleatoric uncertainty, which is related to noise and ambiguity in the data. Another situation where we have lack of data, and we have some sort of freedom to draw this linear classifier in various ways, and it will, perfectly, distinguish two classes. But eventually, the situation here is ambiguous for us because, again, this might be a training set, but in the real situation, some data can be located here, and this data can be attributed to one of these classes. So in this case, we say that we have high epistemic uncertainty, which is related to lack of knowledge. So we don't have enough information, not enough data to draw this classification boundary. All right. So by definition, the whole predictive uncertainty is basically a sum of epistemic and aleatoric uncertainty. And then what we can do is to write some, I would say, from the previous formulas, we can derive several formulas for epistemic uncertainty and for aleatoric uncertainty. First of all, let's look at epistemic uncertainty. Epistemic uncertainty is basically, as I said, as a lack of information. So what we here define epistemic uncertainty as information that we get about model parameters after we see the target variable y for the object x. So this is how our knowledge about model parameters change after we get information about this particular instance. So if we rewrite this formula a little bit, we eventually get this formula where we subtract our predictive uncertainty from this term, which is basically an expectation of entropy for each particular realization of model parameters. All right, and okay, so what is aleatoric uncertainty then? Well, by definition, we have that predictive uncertainty is the sum of epistemic uncertainty, aleatoric uncertainty. So simply we can derive a formula for aleatoric uncertainty here. So this is basically this expectation of entropy of predictive distribution for each realization of model parameters. So again, in Bayesian theory, we have perfect formulas for these things, but in reality, we cannot estimate them directly. It's quite difficult. There are several ways to do that in Bayesian modeling, of course, like Bayesian backprop, variation inference, etc., etc. But usually people don't do this because it's a little bit more complicated and a little bit more overhead to do that, and it's very hard to train Bayesian models right now. Again, let's look at this formula. So predictive uncertainty is a sum of epistemic and aleatoric uncertainty. We can see that epistemic uncertainty is a mutual information between model parameters and target variable, and aleatoric uncertainty is an expectation of this entropy of each realization of model parameters. And again, let's look at how uncertainties look on the charts. We have some sort of two moons data set. Aleatoric uncertainty will be basically this line between two classes. This is a decision boundary. Epistemic uncertainty is basically all area around this training data set. And then we sum these two uncertainties together, so we get this predictive uncertainty. So we have both certain areas in the area without training data and between these two classes. Some words about where we apply different types of uncertainties. Electronic uncertainty usually can be used for cleaning data. We can spot some noise in the data sets. Like epistemic uncertainty here can be used to detect outliers. Of course, it can be used for adversarial attack detection, and there's also a possibility to use it as a criteria for active learning, for selection criteria in active learning. Total uncertainty is used for selective classification, and that is kind of the most critical thing for safe critical applications, where we need to abstain from making a decision. Somewhere, for example, in medical applications. All right, let's just have a very broad overview of methods for uncertainty estimation. We'll get to, in particular, realizations of these methods where we discuss particular methods for language models. So in general, very strong approach to uncertainty estimation is basically using ensemble of models and look at the diversity of predictions of these ensembles, of this ensemble elements. So if, while the diversity is high, the uncertainty is high. The same thing you can do with the Monte Carlo dropout. Monte Carlo dropout is a technique where you make not one prediction, but multiple predictions, but you enable your dropout layer. So each prediction becomes a little bit different from one another. And you can assume it as a cheaper version of ensemble where you don't need to train multiple models, but you just have like one model, but you apply different dropout masks and get a little bit different predictions. And again, like we are looking at diversity of predictions. If diversity is high, then uncertainty is high. There's also density-based methods where we try to approximate our training distribution with some models based on the latent feature representation. So we just try to create a training data distribution and analyze whether our instance belongs to the training distribution or not. And finally, there are some techniques related to training loss regularization. Training loss regularization, you add a regularizer to the loss. It helps you to calibrate your model a little bit. Sometimes it also can be helpful in selective classification. Okay, so why uncertainty estimation for language models is hard? Well, first of all, we have not one, but multiple predictions in a sequence. These decisions are based on various sampling algorithms. We also can get the final sequence, not just like simply looking at the maximum probability token, but have a multiple beams and select the beam in the end. And of course, we should remember that predictions of language models it's hard to normalize them because again, each sequence, you can generate infinite number of possible sequences and how to estimate the probability of each of these sequences and how to normalize them. So this is basically a very hot topic for hot ongoing research topic right now. Okay, finally, we get to the uncertainty estimation for language models. Let's look at what we have. Again, the simplest techniques are very similar to what we have for the standard classification models. We can look, for example, on maximum sequence probability here. It's basically, we can estimate the probability of a sequence by just multiplying the probabilities of each decision in a sequence and subtract it and get our uncertainty score. There's also like a very common thing is to have an average of log probabilities of our tokens. Sometimes it is called perplexity, sometimes it's called length normalized log probability. Again, it depends on whether you do exponentiation or not. And also you can simply just calculate entropy for each particular token and average it. And there are many other, you can figure out, you can think about many other ways of aggregating individual predictions for each individual token, but these are just the most common ones in the literature. Okay, a little bit more complicated stuff. I mean, not the complicated stuff, but a little bit more, interesting stuff. It's pointwise mutual information. Here, for example, it's a way of addressing. It's a way of addressing that sometimes model outputs generic stuff, and basically maybe uncertainty of this generic stuff is not that crucial. So I mean, like if it outputs something very generic, maybe we shouldn't be that much uncertain about that. So there's a approach to correct things with this additional term, where we simply run the model with some query and run the model without query. And so we look at how the model, how the sequence, what is the probability of sequence without any particular input, how generic it is. A little bit more complicated way of doing this is conditional pointwise mutual information. This is an idea where we basically fall back to the simple perplexity, but sometimes where we are very uncertain, we look at the probability of the generic sequence. So this is basically it. So most of the time we are using this term, but sometimes if this entropy is high enough, we also add this term with the generic model. It's a little bit faster than this one, and works also a little bit better. Okay, ensembling. I will not spend a lot of time on ensembling here. Unfortunately, compared to like classification, ensembling in generation work not that good. I mean, classification is one of very reliable algorithms. Ensembling, usually, if ensemble doesn't give you any improvements, probably nothing will do. But in sequence generation, ensembles, according to our experiments, do not perform that well. Anyways, so for assembly, we can do the same stuff as before. We can just look at the average probability from each of the ensemble element. We also can look at the average log probability, of course, and there's also not more stronger technique, which was suggested by Malini and Gels, is a reverse mutual information, where we look at the logarithms also of each realization of each individual ensemble element. Note that we also could use some sort of like Monte Carlo dropout here, but Monte Carlo dropout in sequence generation works a little bit worse again. And note that you probably need to keep the same dropout masks across multiple sequence generations to keep your scores good enough. Yeah, right. So density-based methods, these are quite strong methods, especially for out-of-distribution detection. Here are two papers that propose these techniques for OD detection in sequence duration tasks. This is our work, which was published on ACL in 2023, and very concurrent work, which was published on iClear in 2023 also. Basically, this is the idea of using the density-based techniques in sequence duration. It's basically the same stuff. In classification, we use so-called Mathematical distance as a certainty estimation metric, a certainty estimation score, and you compute it like this. So the idea behind that is that you estimate the probability of, you estimate the conditional probability of your particular instance belonging to some sort of class in your training data. Like, for example, here we are looking at the probability of X belonging to yellow class. And we say that, well, this probability is basically a normal distribution with a centroid, with a parameter M in the center of this class, with the covariance matrix sigma, which might be computed just looking at this particular class or at the whole data set. There's just different ways of computing Mahomes distance. So if you do the durations correctly, you will eventually get this Mahomes distance score. So uncertainty will be basically the distance between the centroid of your class to your data point, which you are trying to estimate uncertainty for. And the higher this distance is, the more uncertain you are. So because your point is lying far away from the training data. And well, of course, in sequence generation tasks, we don't have particular classes. So basically, in sequence generation, we have only one single class where you have all the training data in one single class. You compute this centroid, you compute the covariance matrix, and then you can estimate the distances between centroid and your instance in question. Okay, so how do we, so what is H here? H is a representation of our instances, and in sequence-to-sequence models, we have two options here. We have encoder and decoder, and we tested both of them, and they work pretty well. You can take the representations of each of the input sequence and average them, and you have an embedding of the input question, input query. But you also can do the same thing with the output. You can get the embeddings of all output tokens and also average them and get this embedding of the output sequence. So then we can compute this Mahomes, we can compute the covariance matrix, we can compute the centroids, of course, using our training data, and determine whether whether this instance is out of distribution or not. Pretty simple. All right, there are two modifications of that. One is based on, is basically Mahomes distance plus PCA plus minimal covariance determinant. PCA helps us to reduce the dimensionality of our representations and reduce the effect of outliers. The same thing goes with the minimum covariance determinant. It helps to filter out some noise when we compute the covariance matrix. Okay, there's another option is relative Mahomes distance, where we calculate Mahomes distance of for our particular point, and we subtract the distance to some sort of like global central, the centroid of the background collection. In this case, we have a big background collection, like maybe C4 data set. We calculate the centroid for the C4 data set and look how close our instance to this centroid. And this idea is just like that. We don't want to be high and certain for very common sequences to very common queries to very common outputs. So we are, in this case, we are uncertain only when we are both far away from the training data and far away from like the pre-training data set. Okay. All right, semantic entropy. This is one. Okay, so let me reiterate with density-based methods. These methods are very good for audit detection, and they are type of epistemic uncertainty estimation techniques. So if you have, even especially sequence-to-sequence models, they're showing pretty good at tasks for machine translation, summarization, question answering. And you can find some experiments in our paper and the paper of our colleagues in the concurrent work. All right, semantic entropy is a more interesting stuff. You know probably that model can generate multiple similar sequences in terms of meaning, but very different in terms of surface realizations. Like you can ask who is the president of United States, and for example, like a model can answer like George Bush, or the president of the United States, George Bush, or George Bush is the United States president, etc., etc. This will be essentially the same thing. And we want to take into account the similarities, and semantic entropy does exactly that. It samples several predictions from the language model, like A1 till AM. Then it clusters into meanings, like meaning clusters, and then it estimates a certain entropy on top of these meanings, not the particular sequences. So, and each meaning can contain multiple generations, like, again, regarding this president, they all basically can be put into one single cluster. To calculate the probability for each meaning, the author just simply sum the probabilities for each individual sequence, and then basically calculate the standard entropy formula on top of the probabilities of these meanings. Well, this works pretty well, but surprisingly, that black box methods work even better. So, in semantic entropy, we need an access to logits and probabilities of the output language models. But sometimes, or even actually usually, some models like ChatGPT, GPT-4, and many other APIs don't provide you an access neither to embeddings nor to logits of the models. And then you probably need to what you can do only is to analyze its outputs. So what you do here, you again sample multiple outputs from the language model. Then you can calculate, get pairwise similarity between these responses. And then you can compute a sort of certainty summation metric on top of that. First, what these authors of this paper tried, they tried multiple similarity, pairwise similarity scores. One of them is basically Jacquard similarity, where they simply look at the bag of words of two answers. Surprisingly, it worked. And another thing which is more elaborative is to use off-the-shelf NLI DeBerta model for NLP entailment. So the idea is just to look at two outputs and analyze them with DeBerta and determine whether one is an entailment of another. So if one is basically entailment of another and another is entailment of the first one, you say that they are essentially the same thing. So they're similar. So this is the second way of computing similarity, which is more effective. So now let's get to uncertainty scores. Again, surprisingly, very simple score. Uncertainty score here is a number of semantic sets. Here you calculate these pairwise similarities. You basically cluster them into semantic clusters and calculate the number of these clusters. And if the number is high, then you're uncertain. If the number is clusters is low, then you're certain. That's basically it. Again, this works, but there are some better versions of that. The second version is to compute, basically doing the spectral clustering on top of these similarities. So instead of like just trying to create this hard adjacency matrix, you create like I would say soft adjacency matrix where you you have an adjacency matrix with scores of similarity of each output sequence to each other. And then you can do some sort of spectral clustering where you can basically look at the number of these spectral clusters. So essentially this method does this. Another more simpler method, but actually from our experience a little bit more effective, is basically looking at average pairwise distance. Again, we can construct this matrix and we can just look at sum of pairwise similarities between output sequences. And then we can just average that and get the uncertainty score. So again, if the average pairwise distance is high, then we are uncertain. If average pairwise distance is low, we are certain. Yeah, so these two things work actually pretty good. So and moreover, I want to again emphasize that for this particular case, you don't need anything. You don't need an access to the model. You can just do this you can apply these methods to ChatGPT, GPT-4, anything that has an API. All right. Finally, the method is called P2 from the Anthropic paper, which basically says, well, why not we can ask the model directly? And they did. They just did this stuff. They evaluated the question, multiple choice question answering. They provided the question and the answer of the model, and then ask it whether it's true or not. And surprisingly, that the model, as you can see here, its answers to the second question, like whether it's true or not, can be used as a proxy metric for uncertainty for its original answer. As you can see that for the wrong answers, the model is usually uncertain, like the scores are below 0.5, closer to 0.4. And for the right answers, it's pretty confident. It has this distribution, as you can see. So this interesting way of looking at uncertainty, like, again, asking the model directly itself, it's probably also interesting direction for the future work. But again, I want to emphasize that this, despite it works in this particular case in the work of these researchers, in our experiments and experiments of other people, that didn't work really well. Like, for example, for machine translation or for other stuff, for question answering also, sometimes it doesn't really work. All right, so let's do some sort of summary, what works and what doesn't. For audio detection, I was just going with the density-based methods, of course, and I was just consider robust density estimation first. For selective classification, I would look at the black box method, its average pairwise distance, and lexical similarity also. Yeah, and also probably it's a good way to combine density-based methods and perplexity that was shown in some in one work, on iClear work, that it helps. We also get experiments where it helps, but in text classification. Current, this P2 method sometimes doesn't work, and ensembles also sometimes fail. Right, now let's get to the final part of this talk, to our program framework, LM Polygraph. So it basically helps you to know what LLMs do not tell you. So LM Polygraph is basically a Python library which accumulates a state-of-the-art uncertainty estimation techniques. It supports state-of-the-art models, sec-to-sec models, GPT-like models. It has wrappers for ChatGPT, for Hugging Face API. You can just use a very small number of, just a few lines of code to add uncertainty to your language model. It also provides a benchmark to evaluate novel method uncertainty estimation techniques, maybe on your data, etc. We also will provide a live demo, I hope soon, maybe on NLP, maybe on AAAI. All right, some demonstration examples with LM Polygraph in our demo. For example, here we asking model to translate some sort of non-existent language, like translate into Wajabian language, and you can see that model is completely uncertain because of our uncertainty estimation metric is 0. And like for French, it's pretty easy. As you can see, model is completely certain about its output. Another example with the knowledge of the model, like as we can see, the model doesn't know Russian songs from Russian artists, from Russian singers, but it knows pretty well the songs of British of Beatles. And as you can see, it tries to, in the Russian case, it tries to imagine something, like it tries to predict something like Irina Allegrovna. So it tries to predict something similar, but essentially it fails. And now we can detect that it fails. Another example is like asking some simple and complex questions. If we ask a complex question, like how we can cure a dinosaur, consider like dinosaurs came from Earth, we can cure them there from pneumonia. And despite it provides some, a list of suggestions about how to cure pneumonia of a dinosaur, we can see that it's completely uncertain. But when we ask the same thing for the human, well, it it shows pretty decent confidence. The same thing with how to perform a kidney surgery. Well, and surprisingly, the model gives you a pretty good plan for a kidney surgery to perform with high confidence. But if we ask how to perform a kidney surgery with only one arm, and now the model is completely uncertain about that. Yeah, it also notes that doing a kidney surgery with one arm is not very good, but you see that uncertainty estimation scores works here, that it shows that this is an unreliable answer. So finally, some words about our team. I want to acknowledge our great team for making this library, for developing stuff. I want to acknowledge Maxim Panov, who's at the conference. I want to acknowledge Alexander Panchenko, who's also was a part of this initiative. Here's our many authors. They are from different organizations. There are many others, but these are the main organizations of our work. So in conclusion, let's look at some takeaways. Okay, so there are several things that we should consider beyond just accuracy, beyond just performance metrics. These are debasing, fairness, and reliability. Uncertainty estimation is a crucial component of machine learning systems, including language models. And for OD, consider density-based methods, right, like robust density estimation. For selective generation, try black box methods because they work very well, and maybe you can also try combination of density-based methods and perplexity. Well, overall, don't trust LLMs. Try LM polygraph and to reveal what LLMs do not tell you. I want to also note that we have a very strong team at MPGI that work on debasing fairness, which is led by Professor Tim Baldwin, and I'm have an honor to be one of his colleagues in his group. Regarding fact-checking, we have also a very strong team, which is led by Professor Preslav Nakov. And I'm working also in both in the direction and also in uncertainty estimation. Also, I would note that Maxim Panov is also one of the colleagues who's working on uncertainty estimation right now. All right, so that's it. Thank you very much for your patience. If you have any questions, I'll be happy to answer. Again, here's my contact. Again, here's our GitHub link. Please give us some feedback. It's still I would say even alpha maybe version, but anyways, let's see how it goes.
Artem, thank you very much for this most insightful talk. So first of all, I would like to ask if there is any questions from audience. If yes, you can come here or go to the mic. Anybody? Okay. Okay. Come.
Thank you, Artem, for the very nice talk. Okay. So my question is just maybe clarifying some things maybe I'm not understanding. Have you tried to analyze how the uncertainty of the model may be correlating with the error rate or the wrong decisions that made by the model? As I understand, it's a different thing, right?
Well, actually, this is a task of selective classification where we want to all uncertain instances to be incorrect and all certain instances to be correct. So we want to sort our data set in this way. So all very uncertain instances have more errors, and all instances that have correct answers are confident. So when we maybe do some abstention, like 10%, we abstain from making prediction for 10% and give these instances to human expert or another system, we get a better boost, we get a better outcome out of that. So yeah, we did this. We have a couple of papers regarding text classification, and we also have a paper regarding selective generation, where, for example, we solve question answering task with multiple choice question answering. So we analyze the quality of uncertainty by looking at how good, for example, it in multiple choice question answering. which answers are certain, which are not.
Okay, thank you. And a short question about just a funny question. Have you tried this LM polygraph to real humans, what they generate, and is it possible to maybe to analyze what humans generate?
Well, unfortunately, we cannot ask a human and ask him to write the answer for the same question multiple times, right? And it's polygraph for language models. It's not for human.
Yeah.
It's about how we can analyze the distribution of predictions of language model, not a human. Unfortunately, for human, we have the common polygraph, right? So
Artem, I would not agree with you, because if you ever making the sociological tests, you know, like in companies, this is what they do. They ask you again and again the same question, and actually they kind of sample and see whether they. So actually that works.
But we haven't tried that.
How frequent human uncertain, how frequent LM uncertain actually?
Yeah, they have like 100 questions, but then it's just repeating more or less the same question, different paraphrasing, and then they basically just check whether you answer the same way. So actually, that's not that far from how they do it.
Okay, thank you.
Okay, more questions from audience. Okay, Artem, maybe let me ask you this question, like, really, the fact that ensembling doesn't work in black box works so well is what has been empirically discovered, but do you have some generic explanation or some insight why is this so for LLMs and why it works so differently from some other machine learning setups?
Well, maybe we haven't designed ensembles very well. I mean, there are several ways to design ensembles. We can just train them on different data sets. We can apply multiple seeds to them. But essentially, if they are pre-trained, they are very, very similar. So that's a problem. So they're very, very similar. And maybe if we look at ensemble of multiple different models, like, for example, or we apply some techniques for building an ensemble, like in LLM Blender, for example, that will help us to help us a little bit. So I think we need to add more diversity to ensemble in this case. I think that this is the answer, but maybe there are some other issues. Maybe there are some other caveats in assembling.
So I am understanding your answer correctly that the variation in, let's say, a function of decoder mechanism, current typical decoder mechanism is like less than variation in ensembles of some classifiers as run through Monte Carlo dropout, something like this.
Well, I mean, in simple text classification models, you can build an ensemble just by using different random seeds, right? And they will be a little bit different. They'll be different enough. In language modeling, pre-training is probably even you pre-train models even harder. I mean, like they pre-trained on bigger data set. So if you fine-tune them on small data set, probably they will not be that different from each other. That's the problem. So the more data is in pre-training, the more similar will be the ensemble elements in your ensemble. And the more similar answers they will give you. I think this is one of the possible answers to this question.
Thank you. Any more follow-up questions from audience? Okay, maybe let me ask one last but short question. So you presented this approach when you just ask language model whether the answer is correct. That's interesting, but whether people tried some kind of a chain of thought elaboration of this idea. Let's say you answer multiple times and then you kind of sample several responses, or you repeat again the question about certainty or correctness in different ways, not just once. This way obtaining also some kind of a sampling, but in this dialogue way style.
Yeah, I think that the way the reflexive power of language models is very strong tool. and I saw a work where, of course, chain of thought was used to improve the quality of the answer. Of course, we know that the chain of thought improves the quality of the answer, or the chain of, well, when the model assesses its answer by itself and it says that it's not good an answer, is also been used in some works. I think there was a paper just a few days ago, I saw this idea. I thought, okay, well, it's pretty fast how people, get to this ideas. Yeah, so if you, unfortunately, I don't remember the title exactly, but the idea was essentially similar. They queried it multiple times, they assessed the output by the model, and then tried to correct it multiple times.
Really great. We live in an interesting age, and if you're interested in this research, yeah, get in touch with Artem or me, and for your research, you might get involved as well. As you see, there is a lot of room for improvement. Okay, so we are very out of time now, unfortunately. Artem, thank you very much for your insightful talk, and now we need
thank you very much
switch
for
the gears to the next speaker.
Thank you.
Thanks. Okay, can you just...
He's now on. Maybe you can ask him to turn
Okay. Mohammed, hello, can you hear?
Yes, I can hear you. Can you hear me?
Perfect. Yes, we can perfectly hear you. Can you turn on your video and try to share your slides?
Okay, wait.
Fine, I can see you. Oh. Okay. Now we just, okay.
Can you see my slides?
Yes, yes, thank you very much. So now we're switching the gears, and we're having a next speaker, Dr. Mohammed Malik. He is a postdoc fellow at High School of Economics in Moscow now at Computer Science faculty. And he's also a former assistant professor at Islamabad in Pakistan. He has an extensive research experience with both teaching and research contributions spanning almost 20 years. And today he will be speaking about threatening content and target identification in low resource languages. So, and that's another NLP talk today. Mohammed, without further ado, please start.
Okay, thank you so much. Good afternoon, everybody. Thank you so much for organizing committee for providing me this opportunity to deliver a talk on this social media mining topic and to share my findings with you. So let me introduce you that the title of the talk, that is Threatening Content and Target Identification in Low Resource Languages Using NLP Techniques. That is the outline of my talk. In the first start, I want to introduce some terms and terminologies related to this domain, then the challenges, and then after that, the problem definition related to my contribution in this domain regarding Urdu language. I will discuss a case study with the results, and then I will conclude my talk by summarizing the findings and then future prospects. Okay, coming to the first point, that is what is hate speech? In literature, there are several definitions of hate speech exist because researchers tried to define the hate speech according to their understanding, their knowledge, their vocabulary, and their thinking perspective. So these are few hate speech definitions I added, and the references are also added. You can see these definitions slightly vary according to their own thinking perspective and their understanding. But let me introduce you the most common and most, you can say the majority of the researchers have a consensus on this definition of hate speech. That is, it is a toxic speech attack on a person's individuality and likely to result in violence. When targeted against groups based on specific grounds like ethnicity, religion, race, place of birth, personal background, language, residence, caste, community, and etc. So when there is a hate speech, there is some target, because hate speech always targets someone. So this is the basic conclusion which we can conclude by understanding this definition of hate speech. The next point which I want to describe is what are the various forms of hate speech, how hate speech can be delivered, how hate speech can be formulated. There are a few common and few famous terminologies presented here, like cyberbullying can be used to describe to define the hate speech, flaming, profanity, abusive language, discrimination, and toxic comments. So these are few forms of hate speech. Let me share with you the definitions of these forms, and then we can also distinct between their definitions and the general hate speech. What is the difference between them? For example, if I consider the abusive language, as you can see, the term abusive language seeks to diminish or humiliate some person or group. And when we see the hate speech is a type of abusive language. So abusive language could be the parent of hate speech, means hate speech is at least, we can say that hate speech is at least abusive language. And the other way we can say that the abusive language is a form of hate speech. Similarly, toxic language. If we consider toxic language, let me share you. Oh, sorry. Okay, so the toxic language, as far as its definition is concerned, the toxic language is conveying content that is disrespectful, abusive, unpleasant, and harmful. And when we see the definition of hate speech, not all toxic comments contain hate speech. Means toxic comments could be general without targeting anyone. We can analyze and we can understand this concept of toxic language, that some people have a habit of using toxic style of using language. Usually they use some words which are not directly targeting someone, but they have a habit of using these words. So that is a type of toxic language that is without hate speech. In hate speech, when there is when we talk about the hate speech, there must be a target. Okay, so considering the next point, that is the famous 12 languages landscape presented here, that is shared by the Washington Post in 2022. The landscape described the proportion of speakers related to that particular language. Here we can see the Chinese language dominate, which have a 1.39 billion speakers worldwide, including all dialects of the Chinese language, means the all script. Some languages have more than one script. Similarly, Urdu language also has more than one script, Arabic and in Hindi language also. As far as Urdu and Hindi languages are concerned, we can see the population of the people globally, that 588 million people are basically using Hindi and Urdu language for their communication. As far as Arabic language is concerned, the statistics are there. The proportion of speakers for Bengali language and for Russian language is almost equal. And we can see that the Italian language has lowest number of speakers according to this landscape. So here, Hindi, Urdu, Chinese, Arabic, Bengali, Russian, Italian, Portuguese, German, Japanese, these are low resource languages. So coming to the next point, what are the challenges with these low resource languages while designing some identification, some detection system dealing with these low resource languages? The first challenge, that is the very basic challenge, is the lack of annotated data set. We have to crawl the information and collect, clean the information, and then we have to annotate, go for annotation process. This is the basic and the first challenge. The other, the next challenge is for some low resource languages, like for Urdu, for Arabic, even for Russian and Bengali language, which I know because I work on these languages. There are some essential resources and accurate text processing toolkits are not available, or sometimes they are missing as compared to other high resource languages, for example, for English. So that is that is another challenge related to the resources and pre-processing toolkits. The third challenge is some languages use multiple scripts. For example, Urdu use 2 scripts. People use either Arabic style, that is also called Nastaliq style, or Roman style, Roman Urdu or Arabic Urdu. Similarly, for Arabic language, there are also 2 styles. Hindi language, there are also 2 styles. But for English, there is only 1 style, that is in Roman style. Social media users usually use multiple scripts. For example, if I talk about the Urdu language, the user usually use both scripts while sharing their opinion. They use Arabic style and Roman style at the same time. So that is the problem of code mixing. That is another issue, another challenge with low resource languages. And the last challenge which I enlisted here, these are not all challenges. There are also other challenges, but I listed few to describe the challenges, to highlight the challenges related to low resource languages. The pertinent, famous, we can say the latest language models that are already pre-trained models are hardly available. Not every model support the low resource languages. So that is another challenge or issue. Coming to the problem definition, which I want to, the problem and the task which on which I want to deliver a talk and want to discuss the proposed methodology and then the results and the finding. That problem definition is given on the left side of the presentation. Here we can see on the top, abusive language, then hate speech, that is journal hate speech. So that journal hate speech could be categorized into threatening content, could be categorized into violence incitation and other categories. So today I am discussing the type of journal hate speech that is threatening content identification in the Nastaliq script or Arabic style. So on the right side, the hierarchical classification of the problem is provided, that the tweet or the comment of social media is going to be categorized into two labels, that one is threatening and the other is non-threatening. Then the threatening contents are further considered for target identification, that either individual is being victimized, targeted in the threatening post or threatening tweet, or the group. The difference between the individual and group class label, or we can say the category, is that when an individual person is being addressed, then we say that it is related to the individual class. When more than one person are being targeted, we categorize it into the group class label. Well, my contribution handling the only Urdu language, not Russian, because I am also working on Russian language and another low resource language. So for Urdu language, I have these contributions. First, I have a contribution in 2022 related to the offensive content identification in Urdu. One paper was already published, and the next paper is in the write-up stage. Then hate speech and targeted community detection, that is related to the community. Today, I am just going to describe the framework related to the general target, that is individual or group. But in this hate speech and targeted community detection concept or topic, we are going to basically target the community, that either it's a religious community, political community, it's a media community, it's a judiciary community, it's a army or uniform person community that who are being targeted in the hate speech. Then threatening content and target identification is today's topic. And also I have a contribution in multilingual model for threatening text identification in English and Urdu language. So today I want to share the design of the methodology related to the Urdu language concerning the topic of threatening content and target identification. So here the question arises that why there is a need to design a Urdu identification system for Urdu language, because Urdu is a national language of Pakistan, and if we consider the Asian region, then around 170 million people are basically speaking and expressing their opinions and views in Urdu language on social media. Then at the same time, if we consider the global perspective, then around 300 million people are there related to the Urdu language, those are speakers. And Urdu language is not only being spoken in Asia, in the southern part of the Asia, but also in the USA, in the UK, and in the Canada region. So that's why there is a need to design identification framework related to threatening content and target identification in Urdu language. On the right side, I have added the alphabets. These are the 39 alphabets used in Urdu language to design the words and sentences to describe opinion or concept. So Urdu language is more similar to Arabic language and Persian language as compared to any other language. What was the objective which was addressed while designing the framework for Urdu language? The first one is to design an automated identification system for Twitter data and to classify them as a threatening versus non-threatening accurately. The second objective was for threatening tweets, only for threatening tweets, design an effective framework to identify the type of target, that either individual is being targeted or a group is being targeted. The third objective was, that was the preliminary requirement which we assumed, which we set to start the design, that the proposed framework should be based on the automated feature generation technique in contrast or instead of handcrafted features. So it should be automated feature generation technique. It should be based on. Now coming to the proposed methodology, here block diagram is added. We can see that the tweets were collected from the Pakistani Twitter accounts, because the users of Pakistani Twitter accounts, Twitter users were considered because in Pakistan, Urdu is the national language, and we have a chances of very big corpus. We can design a big corpus of data. So after that, the pre-processing techniques, I will describe these steps individually in next slide. Just here, I want to give an overview. Then pre-processing techniques were applied, then feature extractions. Here we can see the different types of feature extraction techniques were applied, like word n-gram, character n-gram, semantic techniques, word embedding technique, FastX, topic model, latent semantic analysis, and language models were also applied. After that, the machine learning and fine-tuning process of the Roberta. It's basically not word, it's a Roberta, Urdu Roberta. It's a mistake here. So at the first level, the contents were classified into threatening versus non-threatening. Then at the second level, the threatening contents were considered for target identification into individual or group. Before applying the actual proposed methodology, we should have a data set, annotated data set. That is the first challenge which I described while discussing the challenges related to the low resource languages. So data sets, annotated data sets are always have a problem with low resource languages. So we crawl the data. Hello, is there any question? Okay, so we crawl relevant information, relevant tweets from the Twitters, and then process those tweets. Then after that, we annotate the data sets according to the designed annotated guidelines. Before starting the crawling of the data, whenever we in NLP, whenever we want to crawl a data related to specific topics, specific research area, we need to design a lexicon, because without this lexicon, without this seed word lexicon, we could not crawl the relevant data. Because if we crawl all the data, then how we can choose and identify that this data is related to our domain, our topic, and this is not related to our domain or topic. So for designing the lexicon, we need to design this lexicon manually by looking the type of contents for which we are going to crawl the corpus. So this lexicon is also alternatively we can say that it's a seed word lexicon. So we also designed 250 keywords or lexicon keywords so that we can easily crawl the relevant tweets from the Twitter Urdu Twitter accounts. Here I have added the examples of a few keywords. You can see the Urdu part of the keyword and their translated part, unigram, bigram, and trigram, and also some keywords in 4gram. So after designing this lexicon, then everybody who are going to crawl the data is in a position to get the relevant comments, post, or whatever the social media platform they are going to crawl the information. So the next point is the time range. For which time we should consider the data crawling, because it depends upon the situation. For threatening content and target identification, we consider the time period of 24 months, ranging from August 2020 to August 2022, because in this time period, the political situation in Pakistan was very unstable. So people were very aggressive. People were very sometimes sad, worried, and they expressed their opinion on Twitter, on Facebook, and then we have a opportunity in this time period to get the relevant content so that we can design a better annotated data set. So by applying this lexicon and the time frame, we crawl the data for both types of content, threatening versus threatening. Then after that, we applied the process of cleaning, because the data should be clean before giving them to the annotators. If the data has inconsistency, then annotators will have a problem while they annotate the data set. So there are few steps enlisted here for related to the cleaning, removal of empty tweets, duplicate tweets, and those tweets that contain other language words. For example, if a tweet contains the Arabic word or sometimes a Hindi word, sometimes a Bengali word, so it is not possible manually to translate those words into the Urdu language, because it takes manual effort. So we remove those tweets. After that, we have a clean data set. Then we design the annotated guidelines for annotators so that they can easily annotate the data set. And for this annotation, we hired the services of Pakistani annotators because in Pakistan, Urdu is the national language, and people have a more advantage as compared to other countries. So the basic criteria for choosing the annotators was they should be native Urdu speaker, and they should have at least master's level education and have a prior experience of annotating Urdu data. Because the annotation is not only for one level. There are two levels of annotation. First, they have to categorize it into threatening versus non-threatening. And then in the second level, the threatening contents will be considered for individual or group category. So after annotation, we have data. We compile the data and compute the inter-annotator agreement. That is more than 80. Exactly, that is 83%. Here I added few samples of the annotated data set. We can see the first, second are the threatening tweets, and on the second level, the individual or group is being targeted. In this column, the Urdu part is mentioned, and in the beside column, the translated version is mentioned. If you see the third and fourth tweet, it is obvious and it is clear that for non-threatening tweets, we do not need to consider the second level, because we are interested for threatening, and then for threatening, who is being threatened, individual or group. So that's why here this level of annotation is not applied. But here, the fourth tweet, you can see that is not threatening, but that is abusive or toxic content, because it's the person is being referred with the dog tail. So it's not threatening. It's not exactly threatening, but it is abusive. The person is being abused, being insulted, being disrespectful. And as I described earlier, the cleaning process was adopted before annotation. Then after annotation, when we have a final data set, we applied the process of pre-processing. Here, the main difficulty was with the stop words list, because with Urdu, the stop words are very difficult and very different, not in English like, because in Urdu, we have, if you see the style of writing Urdu, then for one type of stop word, there could be many options, many combinations of stop word. For example, the word here is ka, it is a stop word. It could be k, there could be multiple versions of this stop word. So that was a main obstacle, a hurdle with the stop words identification and removal. But we designed, there was already some stop words were available because the researchers did some work, but we compile a big lexicon and we shared it. Then at the same time, with the stop word removal, not for transformer model, for other feature engineering models, we also transform the emojis and emoticons which are present in the tweets, so that the context should be same. If we remove the emojis and emoticons from the tweets, then the context could be broken. So we adopt this option that we should translate these emojis into the corresponding text. And the other pre-processing techniques, these are already obvious, and people are familiar with them, that the other irrelevant information should be removed. Here, the demonstration of these pre-processing techniques are added. First, punctuation removal with the Urdu text, and then with the after removal, you can see, and that here the translated tweet is also added. For stop word, this is really interesting. You can see that the stop word when stop word is removed, the sentence, the behavior of the sentence, and the pronoun, how we pronounce, and how we read this sentence after stop word removal. And replacement of emojis, here is the example is also demonstrated, that here, in this tweet the person is angry, so we replace the corresponding text, and then after that the hashtag and the other irrelevant information are also removed. I also added in this slide some sample stop words so that we can get idea of what type of stop words are being used in Urdu. I added their corresponding translation also. You can see these are few stop words used in Urdu language. Here the word count and cloud representation is presented, so that we can get the most dominating words, keywords that are being used to threaten somebody. Now let me introduce you about the proposed methodology related to the feature engineering and then the machine learning part of the framework. We search the latest and the already pre-trained language model that are available in Urdu. So after doing an exhaustive search, we found only two transformer models that are pre-trained in Urdu. One is Urdu Roberta, that the other is BERT Small. So we applied both models for feature engineering, but in this talk I added only this Urdu Roberta model, because this model, the performance is very effective and very promising. So here we have a transformer model that is pre-trained on a big corpus. If we want to use this transformer model for our specific task in Urdu, although it is already pre-trained in Urdu, we need to fine-tune carefully with important hyperparameters. So with fine-tuning, it's not easy task. If we blindly fine-tune our pre-trained model, it could even lose the prior knowledge. So we have two issues while fine-tuning any transformer model. When we fine-tune, we have these two issues. One is catastrophic forgetting, and the other one is overfitting. Catastrophic forgetting means the models already learned knowledge by pre-training, and if we fine-tune it on another corpus, then if I do not deal it properly, then it could lose the previous learning. So we have to, because we unfreeze the all layers of the transformer model, and then for learning new knowledge by fine-tuning, and so it could lose the previous learning. The other problem is overfitting, and that is also related with deep learning domain, that choosing the number of epochs for training a model is a common issue. So if we choose very few epochs, it could result in underfitting. And if we choose too many epochs, it could result in overfitting. So we deal these two problems appropriately, the catastrophic forgetting and overfitting. These are this is the list of hyperparameters which we use for fine-tuning the Urdu Roberta model. You can see the list of the parameters and their ranges. We applied the grid search methodology to find the optimum values of the parameters so that we can get the best performance from fine-tuning. While overfitting problem was dealt, we use the validation law because we when we split the data, we split it into three parts: training, validation, and test part. And it's the technique mentioned here. It's a very common technique, and majority of the researcher applied this technique for fine-tuning, that the 80% data should be used for the training purposes and 20% is used for testing purposes. And from the 80%, 90% is actually used for training and 10% is used for validation. So we use the validation part of the data set to analyze the validation loss on the because when we apply the train model on the validation part of the data set, we generate the validation loss and we monitor the validation loss and see when validation loss decreases and when it is going to increase and continuously increasing. So we concluded on this matter of overfitting that 5 to 6 epochs are enough for this problem. I will describe this matter in the next slides, and that how it is possible. So fine-tuning process, it is common that we need to apply the tokenization, then training any transformer model with a classification layer. As far as catastrophic forgetting is concerned, I already described that when we unfreeze the layers of the transformer model while fine-tuning, we have to carefully monitor the learning of the model that it already learned. So we finalize the starting learning rate, that from which learning rate we should start our model fine-tuning so that it could keep the previous learning and also will be able to learn new knowledge that is related to threatening content and target identification. So we tried several learning rates, and those are given here, 3e⁴ and above. But while applying the learning rate, we reach on a conclusion that the fine-tuning of the Urdu Roberta leads to conversion failure. So we obtain the best performance with the 2e⁻⁻5 learning rate that is helpful to handle the problem of catastrophic forgetting. The next point is which baselines and comparable models we use to compare our proposed methodology, so that we can compare fairly that how our proposed model is performing. So there was only one study exists in the prior approaches that also address the same problem of threatening content and threatening content and target identification. But with this approach, the problem was with their annotated data set. Their data set was actually not threatening and unthreatening. Those were basically the data set was actually offensive data set, and they use it for the threatening identification problem. So we, as I already described, that we designed the new data set, annotated it on the two level, threatening versus non-threatening and target identification. But for this previous benchmark or baseline, we regenerate their results on our data set to compare it fairly with our proposed methodology. And we also design our new comparable models so that we must compare our proposed methodology with enough comparables. So latent semantic analysis and bag of word approaches feature engineering approaches were considered. In the benchmark, word n-gram, character n-gram, fast tag embeddings, these feature engineering approaches were present. And we also utilize these state-of-the-art machine learning models. So because these models already demonstrated significant performance in related NLP tasks. And these are the performance measures to evaluate the performance of the classifiers. Coming to the next point. Okay, so here I added the training and validation results obtained by fine-tuning the Urdu Roberta for threatening versus non-threatening task. Here you can see the two sequence lengths for the upright 64 and 128 with 3 batch sizes 8, 16, and 32. And 5 epochs results are added here. The data related to the validation loss, training loss, validation accuracy, and their time. We can see that the training loss is continuously decreasing. It means when we train the model, it continuously trains. But when we applied the train model on the validation part, we can see that in the first three instances, for first 3 epochs, the model we behave appropriately. Then after that, the validation loss start increasing. This is the common behavior of train model on with all combinations. So if we see this behavior of validation and training loss individually, we can see that the behavior of the training loss is continuously decreasing. And we can see with different sequence length and different batch sizes, with sequence length of 64 and batch size of 8, 16, and 32, and for sequence length of 128, 8, 16, and 32 batch size. The training loss is continuously decreasing. It means on every epoch, the model is continuously learning. But when we applied that trained model on the validation part of the data set, we can see that for the first 3 epochs, the model behavior is that the model is basically performing very well. And then after that, the validation loss start increasing up to the 5 epochs. So we reach on the conclusion that 5 epochs are enough. Even 4 epochs are also enough to test this model on the test part of the data set, because after this, the validation loss is continuously increasing, and there is no because if we try more epochs, then our model could overfit. Maybe it could give better results, but it could overfit on the validation part of the data set, and then when we try it on the test part, it will perform very badly. So we did not apply we only apply the 5 epochs. The reason is I already described with you. That is for threatening, not threatening task. So before coming to the this validated, first we trained, then validated, and then tested. This validated fine-tuned Roberta model for testing part of the data set. Let me describe you the results obtained from the baseline and from the comparable models. Here you can see that because there are 5 machine learning algorithms we applied: linear regression, logistic regression, random forest, SVM, k-nearest neighbor, and naive Bayes. So these 5 machine learning models were applied for each type of features: a word unigram, bigram, trigram, and their combined effect. Then character unigram, bigram, trigram. I just added only those results which are at least some which crosses some threshold. So also we can see the fast text performance, bag of word, latent semantic analysis. Here we can see that the logistic regression as compared to the other machine learning models, applied machine learning model, outperform, it gives the best performance. So this is one of the findings related to the baseline and comparable model. And the other point is, as far as threatening versus non-threatening classification is concerned, in baseline and comparable model, we got the best performance with character 5 gram. Here we can see the performance, because this performance is in accuracy. And our data set is balanced data set. In addition, we also compute other metrics, that is precision, recall, and macro F1. So here the comparison of the proposed methodology, proposed framework for threatening versus non-threatening, and the baseline were compared. We can see the performance of the various classification models. And in proposed section, we can see that we got the best performance with 64 sequence length and with 8 batch size. And the performance is 87.5% accuracy. And if we consider the micro F1, that is 87.8%. And with character 5 gram, the performance is 85.83%. So the proposed framework that is based on not on handicraft features, but basically based on automated feature generation methodology, it outperformed the other comparable and even the baseline. The next part is the target identification of the threatening tweets, that which target is being addressed, either individual or group. So here I added again the training and validation results of fine-tuning Roberta model for target identification. We can see the performance of the training loss, validation accuracy, and the number of epochs. If we closely analyze the validation loss here, for threatening versus non-threatening tasks, the validation loss start increasing from third epoch. But here you can see that the validation loss means when we applied the train model on the validation part of the data set, the validation loss start increasing from the third epoch up to the 5 epoch. So that is the point related to the overfitting, that if we try more epochs, if we try 10 epochs, then our model will definitely overfit, because validation loss is not decreasing. Then the comparison of the baseline and comparable model for target identification tasks with the proposed methodology. Here we can see that as compared to the threatening versus not threatening classification task, for target identification, the sequence length of 128 with batch size of 8 outperformed and provided 83.20% micro F1, and it outperformed.
Sorry, Mohammed. We just have a couple of few minutes, so if you can try to.
Yes, I am just going to wind
great,
up,
thanks.
because it's just two slides. Okay, so by concluding the talk, I can say that we designed the significant threatening and target identification framework using the contextual semantic embeddings that are basically designed using the pre-trained transformer model, but with fine-tuning to handle the ambiguity and the complexity issues of the Urdu language. The proposed framework demonstrated benchmark performance in comparison with the comparable and the baseline. On the top of all, the proposed framework is basically based on the automated feature generation technique, not on handcrafted features. And the transformer model can capture the actual context of the language being used to threat someone. So the finding of this research could be helpful for law and enforcement organization for identification of this type of unwanted material, that is threatening content and target identification in Urdu language. While talking about the future prospects, according to my point of view, I summarize the future prospects in 3 points. If we deal the interpretability of these trained models and these tested models for low resource languages, we will face the issue. For example, because each low resource language has a different way of creating context to describe an opinion. The next issue that could arise is that the definitions of these different form of hate speech, these definitions overlap. So we need an appropriate categorization of these various type of hate speech for low resource languages, because the definitions overlap, and then the classification system could not be effective or efficient. The third future prospect and the challenge would be that, as I described earlier, that people usually use multiple scripts for a single language to describe their opinion. So there must be a problem of code mixing, and if we are going to design an efficient code mix content identification problem, that is not an easy task. So that is also a challenging task. I am not talking about simple code mix content identification. I am talking about the efficient, that should be efficient. So that's all from my side. And any questions from the audience?
Mohammed, thank you very much for this nice presentation on very important topic, of course, for model NLP. First, I just would like to ask if there is any questions from audience. Okay, let me then just start. The formulation of your task is classification, right?
Yeah.
So you try to cast toxicity hate speech problem as a classification. But how about alternative formulations? Let's say you mentioned that hate speech always has a target. How about detecting precisely what is the target and what exactly insults or other aspects, particular hate speech attributes we used? Or how about a generation of hate speech using LLMs and preventing this? So could you comment on these alternative, let's say, directions of work?
I use the handcrafted features and also the language model to, basically the problem is not hate speech. It's a type of hate speech, that is the threatening content. So I applied both models, both type of model, handcrafted feature generation techniques.
Yes, that's what I mean. But the question is not about how do you solve the problem, but whether, okay, we need classifiers for hate speech, for toxicity, but then maybe these automatic systems, machine learning systems, should be also acting differently. Let's say being tagging systems, every token of systems. So tagging it not as classifiers, but maybe as sequence tagging, or rewriting toxic speech into something non-toxic, which would be kind of a machine translation or sequence to sequence. Yeah. So what do you think?
But my topic was just classification. I was not considering the sequence to sequence phenomena, and because that's why I use the annotated data set, so that the classifier have an opportunity to learn the exact context of the language, and that is the specifically language bound classifier, that is for Urdu Arabic style. That could not be, we could not say that this type of this particular classifier could be applied as it is for other low resource languages. For other low resource languages, we have to consider the language context. What are the opportunities? What are the pre-processing, and what are the other things are available? We have to consider them. And it's a monolingual approach. It's not a multilingual. Although I have designed a multilingual approach, but as far as low resource languages, usually monolingual approaches are designed. So it is just specifically related to the specific language and specific style. So
okay.
Yes.
Yes, I see. So I'm sorry to interrupt, cut you short, but we are really out of time because of some shift. So yeah, I suggest you just to show your contacts, and for those who are interested can contact you on this work and ask questions directly. Okay. Thank you very much. Let's thank Mohammed for his presentation and proceed for the talk chaired by Andrei.
Okay, thank you so much. And
thank
you for the organizing committee and Dr. Dimitri who provide me this opportunity.
Right. Hi, everyone. I'm not sure there are any people present on site at this NLP session. Because I am also participating remotely due to flight delays. So if there is anyone in Yerevan who is now sitting at the NLP track session and watching us, please maybe join the Zoom room so that we know that you are there, or turn on the camera, because yeah, it's a bit difficult to chair a session without knowing whether there is anyone there on site. Let's just wait a couple of minutes, maybe for some reaction.
Andrei, can you hear me?
Yes.
Andrei?
Yes,
Okay.
yes, I can.
So yeah, we had this shift now, but so the first talk is by Anna Marshalova, Elena Bruches, and Tatiana Batura. So somebody...
Yes, they're there. So my question was whether there is anyone in the room. I mean, on site.
I think the last session potentially was designed to be online. So I think we shall just...
Yes, all the speakers will be online. So yeah, that's fine, I guess.
Yeah, I'm not entirely sure, but I think yes.
I've checked. Yes, all the speakers are online.
Good. Yeah. Okay. Yes. Then let's just proceed.
Okay. So this is our fully remote session, and it's also streamed on YouTube. So it's not limited to only those present in Zoom. But yeah, so the first talk is about automatic aspect extraction from scientific texts by Anna Marshalova, Elena Bruches, and Tatiana Batura. And as far as I understand, Anna will be presenting. Is that true? Can you unmute yourself?
Yes. Can you hear me?
Thanks. Yes, yes. So the floor is yours. Can you try to share your screen?
Of course.
Yes, yes, we can see your screen. So yeah, you have 15 minutes, and the floor is yours.
So hello everyone. My name is Anna, and I'm going to present our paper, which is called Automatic Aspect Extraction from Scientific Texts. As the number of published research papers increases, there is a growing need in tools that automatically extract information from them. For example, we might need to extract such information as the task of the research, the author's contribution, the use methods, and the conclusion of the study. We suggest calling these main points of a paper its aspects. However, even though Russian is among the languages most commonly used in science, there is a sparse amount of aspect extraction tools for Russian, and most of them focus on certain domains such as medicine or computer science. To address this, in our research, we aim to create a cross-domain dataset of Russian language scientific texts and to propose a tool for automatic aspect extraction from Russian scientific texts of any domain. Let's start with the dataset. It contains 200 abstracts to papers of 10 scientific domains, namely psychology, physics, medicine, mathematics, computer science, linguistics, journalism, pedagogy, law, and history. In this text, we identified 4 types of aspects: task, contribution, method, and conclusion. Here's an example of an annotated text. As you can see, aspects do not cover the whole text, and aspects can be nested. For example, in this case, task and method are nested inside the contribution aspect. Overall, we identified 836 aspects, almost half of them being the contribution aspect. This might be due to the fact that abstracts are written to give an idea of the author's contribution. However, in some domains, the conclusion aspect prevails. For example, medicine with papers describing results of clinical studies, or history with papers describing results of archaeological expeditions. As for the task aspect, we discovered that in some domains, especially in humanities, we are not talking about the tasks themselves, but rather about some problematic issues or research objects. So it was decided to attribute them to the task aspect as well. And as for the method aspect, it is most usually mentioned in papers on natural and exact sciences. An average length of an aspect is 12 tokens, but it mostly depends on the aspect type. So task and method are rather short, and they are expressed in short terms or phrases, whereas conclusion and contribution are rather long, and they are expressed in full sentences or clauses. So let's move on to the algorithm. For this task, we fine-tuned a BERT model on a multi-class, multi-label token classification task. So for each token, we select up to 2 the most probable aspects, the probabilities of which are higher than the threshold. And if none of them are higher than the threshold, it means that the aspect is not assigned to any, the token is not assigned to any aspect at all. After that, the neighboring tokens assigned to one aspect are united into spans. And to these spans, we apply some heuristics to enhance aspect boundary detection. These heuristics usually remove unnecessary words or add missing ones to the extracted aspects. Finally, aspects expressed in nominal phrases are put into the nominative case. So here is what we get as a result. On the left, there is an example of automatic aspect extraction, and you can compare it to the manual annotation on the right. In this task, in this case, the model performed quite well, but not perfectly. For example, the extracted conclusion is rather incomplete, but it still expresses the main point. To find the best model, we conducted a number of experiments, which included using different pre-trained models and freezing weights and putting some layers on top. But the best results were shown by multilingual birds fine-tuned in our data with just a linear layer for classification. The fact that a multilingual model outperformed monolingual specialized models is quite surprising, but to find its reasons, some new experiments are needed, and we plan to conduct them in future. By now, these are the best metrics for the best model, and the best extracted aspect is contribution, as it is the most frequent aspect in the dataset. And the worst extracted aspect is task, which might be due to its heterogeneity. Apart from metrics for individual tokens, we used exact match ratio, which is lower than the other metrics. So we still have some problems with aspect boundary detection. Finally, we conducted cross-domain experiments to see how our model performs on unseen domains. For each experiment, we used 9 domains to train the model and 1 to test it. And the obtained results prove that our model is able to generalize to new domains. So as a result, in our study, we created a cross-domain dataset of Russian language scientific texts with manual aspect annotation and proposed a tool for automatic aspect extraction from Russian scientific texts of any domain. The code and the dataset are available by this link. And that is all. Thank you for your attention.
Yes, thanks a lot. So since I hear some applause from from Yerevan, I'm not sure, maybe there are some questions from the audience on site before we get to questions from the audience online. So at least I do have a question.
You can proceed first.
Okay, right. So again, thanks for the talk. And my question is mostly related to the data set that you created, especially these aspects that you chose to use. So for example, it's not like I'm looking at the data set right now in your GitHub repository, and it's not quite clear what's the difference, for example, between contributions and conclusions, because it's obvious that sometimes, well, even not sometimes, but often the conclusion of the paper contains the contributions, right? And I'm looking at some examples where I myself would not be entirely sure whether this is a contribution or a conclusion. So how did you like choose between these two labels when annotating? I mean,
we mostly identified as contribution something that authors have done, and when they write that we have proposed something, researched something, or something like that. And we identified conclusion when they write about the exact conclusion that was reached during their research.
Okay, so yeah, like one of the examples from the linguistics subset. So the sentence: идиомы рассматриваются как промежуточные языковые образования между словосочетаниями и словами, состоящие из особых единиц, чьи свойства позволяют относить их к определенному уровню. This is labeled as contribution. And then comes a sentence labeled as conclusion, and the sentence is: показывается наличие диффузии уровней, континуальность перехода от одного уровня к другому, существование промежуточных уровней, которые располагаются единицы. So like the authors have shown something, and this is labeled as conclusion. And then another sort of description of what the authors have done is labeled as contribution.
For the conclusion aspect, we also used some word markers like показано, доказано, and so on. And we mostly identified as conclusion the clause which follows such the main sentence, which is показано, доказано. So, I mean, in this case, it is more obvious that this is a conclusion. And when we are talking about something like the first sentence you mentioned, so how I see it, in this sentence, they write that they propose to consider this problem in this way.
So yeah, and you report the average inter-rater agreement in the paper, but do you maybe remember what was the agreement for these two aspects? I mean, contribution and conclusion.
We did not measure agreement for pairs of aspects. It was just measured for the whole dataset.
Yes, but I guess you have the numbers for every specific aspect because you report the average inter-rater agreement over all 4 aspects. So if you average it, then it means that you have four estimations. I mean, 4 values.
Well, yeah. I guess I haven't, but I don't think that I paid attention to the intermediate results. It was just counted. It was just averaged, and I did not. Maybe I should have paid attention because I think there might be some interesting discoveries about which pairs of aspects are most usually confused.
Okay, I see. Thanks. And yeah, I believe the data set that you released definitely is going to be very useful. Okay, anyway, any questions from from Yerevan?
Last chance.
Yeah, I guess you can just come to the microphone and start speaking because I don't see you anyway. Oh, well, I see something.
Okay, but can you hear me?
Well, if you come to the microphone, it will be better, I guess.
Yeah. No, you can proceed. There is no question from the audience for this one. So.
Okay, then let's thank the speakers again.
Thank you.
Hey, thanks a lot. So yeah, the next talk is supposed to be prompt tuning for targeted sentiment analysis in Russian by Yuliana Solomatina and Natalia Lukashevich.
Hello everyone. Yeah, I'm going to present this online or offline.
Offline, perfect.
Yeah. I think I'm gonna need some help with my presentation on this laptop.
So I guess the local team usually changes the setup so that the slides are shown in addition to the video stream. So if Alexander could help, it would be great. Unfortunately, I definitely cannot fix it remotely. But you do have the slides on the laptop, right?
The help is on its way.
Oh, perfect.
Julia. Okay, I'm going to present our paper, which is called Prompt Tuning for Targeted Sentiment Analysis in Russian. And first of all, we need to define what targeted sentiment analysis is and how it is different from general sentiment analysis. In fact, it is often important to take into account the relationships between the participants of the situation. For example, X offended Y, and so on. This is what targeted sentiment analysis is. So we have a target and we have some attitude that is being expressed towards it. There are very few studies on this topic using Russian language material. And also it is important to mention that targeted sentiment analysis is particularly relevant for the news discourse. And news texts are more difficult to analyze in terms of sentiment as compared with reviews, for example, not because of this target topic, but also because of the predominance of neutral polarities, since journalists always try to be as neutral as possible. That's why some sentiments are expressed implicitly, which means there are no expressive sentiment words, but just some underlying meanings, some facts that can be defined as sentiments. And so earlier this year, the competition Rusent NE was organized, and the task was to deal with the targeted sentiment analysis on Russian data. And the current study suggests prompt-based learning for this task. And for the Blackbone model, we used Rurobet large model. The experiments were based on the question answering approach, which means that the task was formulated as a question in a natural language, and then it was fed into the model, and the expected output was the class label, positive, negative, or neutral. And it is important to mention that what worked best is fine-tuning and prompt tuning both. And I'm going to briefly overview the methods that we implemented during our experiments. And first of all, we are all very familiar with the fine-tuning approach, but there is also a prompting approach that was recently suggested. The idea behind that is that when we fine-tune the model for the downstream task, we can formulate a prompt in such a manner that the downstream task will be very similar to the pre-training task, and this can boost the model's performance. And another problem with this kind of tuning is that it is hard to choose the prompt manually, because we can change one token in this prompt, and this can significantly affect the result. And that's why we can tune the prompt just like we tune the whole model. Or if we deal with a very large model like GPT-3, we can tune the prompt instead of fine-tuning the model. And after that, many different modifications of this approach were suggested. For example, prompt tuning with rules. It means that we can mask not only the class label, but also some subprompts, some other tokens that help explain the task to the model better. And then we can aggregate the predictions via conjunctive normal form and get the final class label. Another approach is knowledgeable prompt tuning. It deals with the verbalizer. Verbalizer is basically a list of class names which are then mapped with the labels of the class, and these names are predicted during the language modeling block. And knowledgeable prompt tuning means that we can predict not only the labels of the class, but also some words related to them, which are extracted from some external linguistic research. So in this study, we implemented both manual prompting approach and prompt tuning approaches that I just described. And also we implemented the approach of mixed templates, which means some tokens in the prompt can be fixed and others can be tuned. And the data is Rusent and E-corpus, which was pre-labeled with named entities, and then it was labeled with sentiments and with relationships between the named entities. And for the competition, it was pre-processed. For example, there only used sentences with non-contradictory cases, which means that X is loved by Y but hated by Z. It is contradictory case, which in these cases were excluded. And also we only dealt with sentence level and not with document level. And for evaluation in this research, we first conducted threefold cross-validation, and then we tested our model on the Rusent and E split, which was provided by the organizers of the competition. And I would also like to say that the baseline model for the competition was RuBird without any modifications. And the results are presented on the slide. And the metrics which were used, apart from just the F-score, F1 score, also the F1 score that was averaged across only the positive and negative class, since these two classes are particularly interesting for this task. And also I would like to acknowledge the authors of this paper about open prompt, since they released a very helpful tool for implementing different prompt tuning strategies out of the box, which really helps using them for using any prompt tuning approach for the downstream task, just by loading the pre-trained model from Hugging Face and formulating the template of the prompt. And the first series of experiments is manual prompt-based experiments. And here we tested two variables, the prompt type and the way we handle class imbalance, since, as I already mentioned, news texts contain many neutral polarities and not many positive or negative ones. And we used a prompt as just a target word or a question to the target word about how do they feel about X. And for handling class imbalance, we first of all try to not use anything for this. Then we try to calculate class weights in the loss function, and also to augment data via back translation and replacing some tokens with contextually close other tokens. Then the mixed template is presented on the slide. Here the soft are the tunable tokens, and text are the fixed tokens, which were just the same during the whole training stage. And the verbalizer consists of just class names. And then we implemented prompt tuning with rules. And here we also tested how the initialization of the prompt can affect the result. And in the first template, we tried to focus on the fact that there is some participant of the situation mentioned in the sentence from which the model can derive the attitude. And in the second template, we emphasized the fact that the sentiment can be expressed both implicitly and explicitly. And the last approach is knowledgeable prompt tuning, and for this we utilized RU Sentilex and RU Sentiframes lexicons. And in the first strategy, we tried to collect words for the verbalizers in such a way that for both negative and positive sentiments, the classes could overlap, since there are some words that can have different meanings in different contexts and can have different sentiments in different contexts. And in the second strategy, we made sure that there are no overlapping and the positive class is always prioritized, since in the previous experiments we saw that the results for the positive class are always a bit worse than for the negative one. And so it means that, for example, some words like shame, murder have negative connotation. That's why it is negative class, and so on. And the results are presented here, and we can see, first of all, that no method to handle class imbalance showed good result. And some of them, like augmentation, are very time-consuming, and they do not give some performance boost. So they are not really suitable for the task. And prompting approach works much better. And the best model that showed the best result during our experiments is knowledgeable prompt tuning with the first strategy. And so we selected this best model and then evaluated it on the data split from the competition. And the results can be compared to the third place. However, the models from the top of the leaderboard leveraged its ensembling methods. And these methods are extremely computationally intensive, because they are ensembles of transformers. And so the prompting and prompt tuning approach works really good, not only in terms of the quality, but also in terms of the computational intensivity. And so in the current study, we researched the task of targeted sentiment analysis in Russian, and we tested different strategies for both hard prompts and soft prompts. And we also saw that prompt tuning, along with fine tuning, surpasses vanilla fine tuning and manual prompting. And the best model that showed really good results was the model based on knowledgeable prompt tuning. And that's it. Thank you for your attention. If you have any questions, please feel free to ask them.
Yes, thanks a lot, Juliana. So are there any questions in Zoom? So let's, for a change, start with the online audience. You can raise your hand or just unmute your microphone. And as I've said, if there are any questions in the on-site, from the on-site audience, yeah, just come up to the mic. Okay, meanwhile, just maybe a very silly question from me. Since you use prompting anyway, so why have you decided to use BERT-like encoder models and not generative decoder or encoder-decoder models. And don't you think that using generative models would improve the performance of your approach?
Thank you for your question. Yeah, I was considering that, but first I started with the Rupert model because this was before the whole thing with ChatGPT and so on, and BERT models were more suitable for classification tasks and also for the purposes of computational possibilities, and then the experiments showed that Roberta was given even better results, and then the ChatGPT appeared, and I also had some experiments with ChatGPT which were not very successful. And this is just a topic for another conversation, why they were not that successful. But yeah, I think that it is possible that decoder-only models, when prompt-tuned, can be very suitable for this task. But I also wonder, as far as I know, no one from the participants of the competition, no one used decoder models. Maybe they also conducted some experiments. But yeah, thank you. I think that there is room for improvement for other experiments on that.
Yeah, thanks. And what about encoder-decoder models like T5, etc.? You didn't try them either?
No, I didn't try them.
Okay.
Also.
Okay, thanks. Okay, thank you. I guess we are way out of time, so we probably should move on with the next talk. But yeah, thanks again, Idana. That was very interesting. And the next talk is supposed to be the battle of information representations, comparing sentiment and semantic features for forecasting market trends. Yeah, and I guess Andrei Zaychenko is here in Zoom.
Yes, can you hear me?
Yes, we can hear you and we can see your slides. So yeah, I guess please move on. You have 15 minutes. The floor is yours.
Greetings, everyone. Today, on behalf of my team, I will introduce to you our paper.
Something's happening.
Can you
Andrei,
hear me now?
are you still here? Yes, but we don't see your slides anymore.
I think.
Can you, Andrei? I guess he was disconnected. Andrei, are you here?
Yeah, I'm here. Sorry, yeah? The Zoom crashed for me. Yes.
Okay. May I also ask you to maybe turn on your camera, because it will be much better if you present, if we see your face when you're presenting, if it's possible.
Yeah, sorry, but I don't have access to my notebook. I'm presenting from the PC and it doesn't have a camera. Yeah.
All right. Yeah. Then yeah, just please share your screen, your slides. Yes. Okay. Let's start again.
Yeah. So again, greetings, everyone. I will introduce to you our paper comparing sentiment and semantic features for forecasting market trends. In recent years, several studies have applied deep learning and NLP techniques to financial data, including news articles, social media posts, and quarterly financial reports in order to predict price movements. Despite its significance, most researchers rely on sentiment analysis as the primary additional feature, leaving little exploration of the potential of semantics and context hidden in the text. In this paper, we aim to fill this gap in research by testing the hypothesis that semantic features are important for stock price prediction. Our approach uses sentence embeddings extracted from Twitter data to capture extra information and contextual relationships with financial market trends. And then we compare our approach to traditional sentiment-based solutions to evaluate its performance. In the introduction to the paper, we made a claim about existence of contextual information inside the text that can be utilized and retained using the embedding approach. To demonstrate the validity of this claim, we created a vector representation of the text using the state-of-the-art sentence transformer model, mapping our sentence to 384-dimensional dense vector space. After the creation of tweet embeddings, we proceeded with vector clustering and used a bird topic modeling technique to create a hierarchical cluster.
Just Andrei,
Yes.
is it supposed to be that you still show like the title slide only?
Oh, no. I think there is some problems with Zoom.
Because we only see the
Zoom
first
quit
slide with the title.
unexpectedly. It says Zoom quit unexpectedly. Maybe. Yes. Now I stopped the sharing.
Yes. Share again.
Can you see the slide?
Yes. Now
it works.
Okay.
Can you try to change the slides just to make sure that it works? Okay, now
I don't know. It crashes right when I switch the slides. The Zoom app. I don't know. I can do it. I try to share the screen. I try to share the PDF alone.
Yeah, can you maybe it's easier if you just send us the slides and then I, for example, will share the
Okay.
slides. And you will show me.
Can I send them in the chat? Yes.
Just
Yeah,
send
you
the
probably can.
file in the chat and then.
Okay.
Yeah.
It's the first time for me. I'm sorry.
That's fine, I guess. That's how things are going on with the hybrid conferences.
Yeah, I sent the presentation.
Yeah, just I'm downloading it. Let me just open the slides. Okay, so let's see. Yes, so these should be your slides, right?
Yes, correct.
Yeah, let me. Okay, just tell me when to go on to the next slide.
Okay. Currently we're on slide 3. Yes, you can see on the slide the resulting output of the topic clustering. In this case, you can see the results for the Google tweets. It produced a list of 20 topics denoted by the distinct circles, which were later grouped up into 4 main large clusters of the topics. So next slide. Now we will connect these topics and market data and observe multiple time periods with high and low user activity. During low activity period, we can see proportionally equal spikes of clustered topics reacting to volatility changes. And they are caused by just the tweet number increase. On the other hand, high user activity leads to great diversity in topic reactions. All of them have their peaks and lows, meaning that larger sample helps us make a distinction of topic trends, resulting in higher correlation that is at least twice as large as you can see in the tables below the graphs. This further speaks in favor of our ongoing hypothesis that great amount of extra information is hidden inside the text semantics that can be used to predict stock market volatility. Next slide. Now we proceed to an overview of overall scheme of conducted experiment. It consists of 4 main steps. First is data retrieval, a process where we collected a 5-year data set published on Kaggle. It was containing tweets regarding Tesla, Apple, Amazon, Google, and Microsoft companies. Then the data pre-processing. So we deduplicated some tweets in order to clean the data. Yes. Then the covariate segregation. Depending on the experiment, we either used binary sentiment score or created the embedding vector and used this as a feature. For the target variable, we chose the close price. Last step is model prediction. After covariates were fed into either TFT or nonlinear models, we train it and make a 3 or 5 step ahead historical prediction on validation data set dependent on the experiment. Next slide. In order to prevent overfitting and produce better results, we introduced a custom loss function, DMSE. It was built on top of one of the most popular loss functions for regression text, the mean square error. But we added directional component. It was done because MSE just focuses on the difference between true and predicted price. In terms of stock price prediction, the direction of the price movement is actually a more important factor than the value itself. That's why a custom loss was introduced. Next slide. Depending on the experiment, 3 main groups of past covariates were used, containing market, sentiment, and embedding features. Further, they will be denoted by the abbreviations, where H, L, O, V is market features, S denotes sentiment score, and E is for embedding vectors. Next slide. 2 models and 1 baseline approach were used during experiments to predict the closing stock price, the temporal fusion transformer, nonlinear, and naive seasonal approach. TFT is an encoder-decoder transform model. It makes use of multi-head attention, GRNs, and LSTM, while nonlinear is a more novel approach of a simple linear layer introduced in 2022 that outperformed multiple transformer models on time series benchmark datasets. That's why we used it as kind of a benchmark for our experiment. Next slide. During elaborate exploration of sentiment score, we achieved results confirming that the social network sentiment is a great indicator for stock price movement prediction. As you can see on figures on the left, we demonstrate stock price movement as well as sentiment score calculated in both ways. First, as a relation between negative and positive tweets, and second, as fraction of negative tweets in the total amount. Visually, we can observe a great amount of resemblance between price and sentiment variables. In this case, Apple, which is on above, has a lower correlation compared to Amazon below. For Apple, in this case, the correlation was around 20%, while Amazon has 40%. When we compare stock volatility with sentiment score in figures in the middle, we observe the same phenomena. Correlation is higher for Amazon by 52%. And actually for Apple, we can clearly see the time lag between public reaction and stock volatility. Volatility precedes public sentiment shift, but for Amazon, the situation is slightly different. We can see that sentiment changes are synchronized and even precede the volatility shift in some cases, making it a greater predictor of price movement. Using scatterplot, we can further observe linear dependence between sentiment and volatility for both companies, although for Amazon, the dependence is more prominent. We therefore claim that there is a clear statistical relationship between observed values. Next slide. Here we present a table of a resulting error score for symmetric mean absolute percentage error for all companies. Overall, TFT model performed better than in linear for all companies. The best performing model for Apple is TFT with embedding vectors as a feature. Comparing the closest instance, we observe at least a 30% decrease for SMAP. It is also important to point out that for Apple, using sentiment score actually didn't help to improve models' accuracy for both of the models. On the contrary, with Amazon, we observe different behavior of models' performance. Given the input features, both nLinear and TFT received performance boost with usage of sentiment score. An embedding vector actually yielded higher error values. Models with embedding vectors show the best accuracy only in 2 cases out of 5 for Apple and Microsoft, that were companies with the lowest correlation between volatility and sentiment, as we said in the previous experiments. For Amazon, Google, and Tesla, sentiment score outperformed our embedding vector approach. Next slide. The above results could not lead us to a complete conclusion, so we experimented further with a smaller prediction window of 3 days. Another approach was a different sentence embedding algorithm created by Microsoft, MPNet. It has twice the amount of dimensions compared with the approach mentioned previously, but the accuracy of closing price prediction dropped significantly for our model. In the table, we observe that for some metrics, embedding approach still shows better performance, but the difference actually is insignificant, and sentiment approach received better results for 4 out of 5 metrics, like in the case of Apple. Another company that had nearly similar results for both feature sets was Google. The difference are negligible, only 0.04% for MAPE. For Amazon and Tesla, sentiment again proved to be a better feature, scoring higher for all of the metrics. Both of those additional experiments, they further demonstrated that sentiment as a baseline solution still performs better than the proposed embedding vector approach. Next slide. So yeah, the results of this study provides further evidence in support of sentiment analysis as an effective tool for predicting price movements in financial markets. It showed that the binary sentiment polarity extraction approach outperformed sentence embeddings in terms of accuracy and training time. For some cases, the embedding approach proved to be useful on 5-day prediction window, outperforming sentiment baseline solutions. This suggests that the choice between binary sentiment polarity extractions and sentence embeddings as the preferred approach can possibly depend on the specific task and the prediction horizon, as well as the effectiveness of sentiment as a predictor in the given context. In the majority of the conducted experiments, the sentiment approach outperforms the embedding vectors method. This fact might be counterintuitive because embeddings seem to encompass more valuable contextual information. However, sentiments tend to represent information in a more concise way, bringing less noise into the prediction model. Nevertheless, the embedding approach still has an advantage that it does not require an additional model for sentiment extraction and the consequent quality verification of that procedure. On the other hand, sentence embeddings approach doesn't require us to verify it and can produce similar results to sentiment extraction, retaining more of the semantic and contextual information contained in the text. Nevertheless, the model training time for sentence embedding is significantly longer. These findings suggests that sentence embedding could be considered as a robust solution after further works due to its similar performance to the sentiment extraction. Yes, thank you for your attention. If you have any questions, feel free to ask.
Yes, thanks a lot. So we have time for probably one question. Any questions in the audience, either online or offline? Please just speak up.
Okay, yeah, I have a question. Thanks for the talk. I'm not familiar with stock price prediction field. What usually related work do? I mean, which additional field do they use? I guess sentiment polarity score should be somehow known for stock price prediction already.
Yes, yes. So the current approaches, most of them use the sentiment polarity extraction from multiple resources like social networks, or some of them use the financial reports in order to predict long-term price movements. But the of the text itself isn't very research topic. But even if we talk about the sentiment polarity extractions, most of them perform rather bad in the in terms of testing on the real data. When we try to apply these models to the real stock market movements, it only performs good on the historical data, but it is actually a very under-researched topic because the price movements are rather random, and it is very hard to find some robust solutions to predict the prices. Yes.
Okay, thank you.
Thanks. I believe we have to move on to the next and last talk. But yeah, thank you again, Andrei.
Thank you.
Right, and the next and actually the last talk of this session, and in fact the last talk of the NLP track of AIST this year, is whether large language models learn at the inference stage by Vladlen Kulikov, Ilya Makarov, and Radoslav Nechev. And I see Radoslav is here in Zoom. Can you say something just to make sure that...
Yeah, hello everyone.
Hi, yes, we can hear you. Can you share your screen?
Definitely. So here we go. It should be up and running now.
Yes. Yes, Daniel, please move on. 15 minutes is yours.
Thank you, Andrei. So hello, everyone. Thank you for hosting me here today. Unfortunately, I was unable to join in person, but hope next time it will be it. So we have a lot of different discussions on recent advances in NLP, especially in the generative models, including transformer-based architectures. And with my colleagues, we tried to analyze why actually they perform really better in some cases when we provide some additional information during the inference stage. Or is it so-called the learning and reasoning effect during the inference stage? So main goal was not actually to provide some new approach to make it even better, but to understand and explain and maybe provide it to other people the pipeline, how to make it work, and analyze what are the main reasons of this happening. So just in case, the main question is, how do these models, especially transformer-based models like GPT or Bloom family, learn during the inference stage, learn in quotes, of course, so they incorporate some additional novel information which wasn't present during the training stage, with no changes either to the architecture and to the model parameters. And in addition, we tried to cover these two questions because they are quite widely known, but they're not that strictly defined. First of all, what is Ellender effect, or learning and reasoning effect? And do they actually learn and reason during the inference stage? By them, I mean the large language models, or they simply simulate some intelligent behavior. So there are a lot of different papers, of course, on this topic. I've only brought 3 of them that for me seems a little bit most relevant for this particular research, but actually in the original paper supplementing this speech, we have more than 15 different sources, and they all are important. So first of all, there was a first paper which provided the chain of thought prompting in large language modeling in the same approach we do, the first one. Second one is just the original paper on GPT-3. And the last one is actually quite old compared with all the other papers. Paper on the few-shot learning in machine translation from back 2018, but we have a few relevant ideas from the paper in here. So let's first of all formulate the hypothesis which will help us to move on. Main hypothesis in this work, and we will try to support it with several experimental and literature results, is the following. Large language models, and by large language models, we assume all the models which have big enough parameter of space parameters. I will define what is big enough a little bit later. We assume that they create some inner language spaces that contain not only the language itself, like grammatics, semantics, and so on, but some patterns of rules and reasonings which are implicitly, not explicitly, embedded in this space. So LLMs, instead of learning something new during the inference stage, simply adjust their state of mind to the particular already learned behavior trajectories. So main idea, once again, of this hypothesis is that the majority of the information is learned and embedded into this space during the training stage, and during the inference stage, the examples of resonance, chain of thought, and so on only provide some instructions to calibrate the behavior of the model. So I will be brief on the problem overview because I understand that everybody on this conference is well aware of all the problems we are solving with language models, but just in case, we assume that we have given a sequence of some tokens from finite dictionary, which contain description and maybe one or several examples of the behavior on the desired problem. And we assume that these behavior examples help us to solve the problem. Let it be easy classification, regression, text generation, whatever. So first of all, let's take a look at the data size and the model size for which we actually observe this learn and reason effect, because if you take Nano GPT provided by Andrei Karpathy with 300 lines of code, then you definitely will not see any Ellender effect, and that's fine. So according to the data we checked in several sources, all the sources list once again are available in the paper itself. The corpus itself, corpus of data, meaning should have at least 300 billions of tokens, because otherwise it's kind of too small. And also the models should be of size billions, not millions, of course. That it should be approximately 33 or 50 billions of parameters. However, even 7 billions seems to be enough for certain types of tests. For example, if you are speaking only about the machine translation. And speaking about that paper on unsupervised machine translation and how is it related for the current speech. Actually, translation systems show us that if we're speaking about unsupervised machine translation, from that time, we can see that if we have two different models trained for language modeling on two different languages, we can simply try adjusting the internal spaces together by using only small amount of label data. What I mean, we can have some kind of language model or just word embedding model like word2vec, fast text, and so on. And the other one in here on the slides are just adjusted as some kind of strange clouds. And the idea in there is the following. We assume that all the languages are actually based on the real world scenarios outside there. And we know that actually word sun and sky are usually much more aligned, and they usually come together than words sun and I don't know, dimethyl or hedgehog or something else. So when we provide some examples of words that directly translate one into another, for example, word gato in Spanish, I guess, or Italian, sorry, I forgot it, and cat in English, we simply adjust these clouds of points, and then we can get that time, of course, almost state-of-the-art approach with almost no data which is aligned between two spaces. So the assumption is the following. These models already have created some internal states, and then we simply align them with several examples which are labeled for first and second spaces. So the spaces are aligned as the mark D, and now we get the aligned spaces and the translation can be performed rather well. Okay, that was the idea from the machine translation. And later we tried to adjust this idea to the chain of thought reasoning, because when we provide some chain of thought reasoning for the model or provide just an examples to make the model work better, we can see that the model starts working better, but the reason might be the same. we might simply adjust the internal state, internal language space of reasoning of the model, because the model is definitely over-parameterized because it contains billions of parameters, and it might cause the better behavior. There is even an important note because which follows our observations and experiments, and it somehow proves our results. Because when we provide some examples for the model how to work in the upcoming problems like classification or text generation in specific form or some arithmetic problems, even providing the examples with wrong reasonings. So we provide example that the model should follow some path of reasoning, but the example itself is just incorrect. For example, it has arithmetic errors or just broken logic and so on. Even such examples help the model to perform better and to achieve better results. But if we change the order of reasoning, for example, we try to just shuffle the sentences within these examples, then the whole sequence is kind of broken and the model behavior fails. The model quality fails, sorry, and the model behavior is not as we expected. Okay, to provide some experimental proof of our claims, not only to refer to some other external research papers, we've run the experimental setup with 5 different prompt and scenarios. First one was absolutely no prompt, so we simply ask the model to answer to our question, just like in zero-shot learning. For example, compute something, I don't know how many computers are in here. And we also had 4 additional prompting scenarios. First of all, standard prompting. So we have simple example in here, like one-shot learning. For example, question, there are 9 computers in the server room, 5 more computers were installed each day, blah, blah, blah. And the answer is 29. After that, we assume we send another question for the model, and we'll ask the model to continue the sentence to generate the answer, as we usually work with this language modeling approach. The second scenario is chain of thought prompting. So we provide a question, and then we provide a chain of thought sequence. So we not only provide the answer, but the chain of thought as well. Third scenario is actually invalid reasoning. So the same stuff as we did with the chain of thought, but now the chain of thought is actually incorrect. But in this case, we still have the correct sequence of steps. So we had original 9 computers, then we have for each day, we have arithmetical errors and the answer. And finally, the irrelevant prompting. So we have question on something related, for example, with computers or with vegetables or with something, and the answer is just random coming from another example, for example. So we had 5 scenarios, and we used a couple of open and closed source models because we wanted to check the behavior either on some state-of-the-art models like GPT family or some open source models. Just in case, this work was mostly performed during spring, so we don't have the most recent models like Second Llama and so on. So we mostly focus on Bloom, if we're speaking about open source models. We started using models from 500 million of parameters to 176 billions, so including Bloom, MT0 XL, and Quankao, and of course GPT-4 because it's kind of state-of-the-art for now. So I will provide the example table, so it's much easier to see, but the main idea was kind of simple. Models with a small size, including Bloom up to 7 billions, could not provide any useful improvement using chain of thought, either correct or incorrect, so they're not present in the table. And MT0 was also kind of inefficient if we try to provide some chain of thought reasoning. While Bloom 176, Quankao and GPT-4, and also including previous to GPT-4, GPT 3.5 and 3 models like TextDaVinci 0.2 and 0.3, provided some useful improvements. So first 2 columns in here, speaking about the models, correspond to open source models, while last 3 correspond to OpenAI models, which are kind of close. And we have percent of the correct answers in 5 scenarios. So no DEMA, no prompting at all, then standard prompting, chain of thought, invalid chain of thought, and irrelevant chain of thought. And we can see that actually Bloom behavior did not improve on the arithmetic reasoning at all using any of the examples except standard reasoning and chain of thought, so it improved the behavior a little bit. For the Hanako, it seemed a little bit surprising. So without any demo, it performed much better than with standard prompting. But chain of thought and invalid chain of thought provided improvement of the score. So once again, we prove the hypothesis that actually the order of the prompting is more relevant than the correctness of it itself. And speaking about the OpenAI models, we can see that we solved them. We did not use them with no prompting at all. So we use only with standard prompting and chain of thought. We can see that chain of thought improves the behavior. Invalid prompting doesn't break it, and sometimes it even improves for some reason. Maybe it's the consequences of not big enough size of the tested dataset, but for all the other models, this size was quite enough because the results were rather stable. And even when we provide some irrelevant prompting, we can see that it might improve or not degrade for GPT-like models spoken about OpenAI. And last but not least, GPT-4 provides great results out of the box. And with prompting, we can either achieve the same behavior or even break it, despite we're using some useful prompting, so it's standard prompting or chain of thought with correct examples. Same stuff was achieved with question and answer and reasoning on the Bamboogle test. So we can see exactly the same behavior. Chain of thought either improves everything a lot or doesn't change it for GPT-4. Invalid prompting, in this case, can break it a little bit, but still, it's really close to correct prompting, but irrelevant breaks it a lot. So the conclusion might be the following, and I decided to just break it into the couple of questions we formulated in the beginning. So first of all, what is learn and reason effect? We assume, according to the research we performed, that learn and reason effect is more about finding some similar reasoning patterns in the latent space the model has created during the training stage. And then these examples, chain of thought or just several shot learning, provides the model example how to calibrate itself to find the appropriate maybe a projection of its own parameter space for the desired problem to solve the problem better. So it seems like the application of pre-existing knowledge rather acquiring anything new. And speaking about the idea of large language models learning during the inference stage, seems like they, okay, I cannot say that they're not learning during the inference stage, but for now, we have not found any exact evidence that they actually learn something new during the inference stage, but we can assume that they are kind of exploiting their already existing knowledge, and that once again is proved also by the results which we observe when we provide incorrect prompting, but preserving the desired sequence. So when the model is just following the path we provided it, it achieves better results, even if we provide it with wrong examples. So that's kind of it. And if you have any specific questions, thank you. Just from my, not thank you, sorry, you're welcome. Just from my side, actually, the area is rapidly evolving, and I understand that if there are some new results, this might become a little bit incorrect just every day, because we got into really tricky area of trying to explain why all these models work. So I would be glad to hear any of the questions, including the questions which just question the correctness of this paper as well, because I want the discussion to be useful for all of us. Thank you. You're welcome.
Thank you, Radoslav. Thanks a lot. This sort of concludes the AIST'2023 session, but maybe we still have time like for one quick question. I guess people on site and online are already anticipating the closing of the conference, but yeah, still any questions? Okay, yeah, just a brief one from me. I'm a bit confused, in fact, about your final claim or statement that large language models don't learn anything during few shot scenarios. isn't it sort of trivial? And I mean, does anyone actually claim that models learn anything in few shot scenarios? Of course, they don't, because their weights are not updated. So like, what?
Okay, may I then fix a little bit this formulation? Yeah, you're right. So we're not speaking about the learning in classical paradigm when we just update the model weights or add some another adapter. No, by learning, we merely meant that the models do not acquire any new knowledge. So if they are unable to solve some problems if they're not trained to solve some problems during the training stage, they won't acquire this ability, even if we provide them some useful prompts, some examples, and so on. So we only can make the model solve the problems they already have seen during the training stage, maybe in a little bit different scenario, but we cannot generalize them to unseen regions of our feature space or problem space.
Well, but we do know that we can, I mean, just this claim sounds to me a bit self-supporting and...
Okay, it's a little bit obvious, right?
Yeah.
Okay, then it might be a little bit obvious. So the main reason we performed actually this research was the curiosity to find out whether they do or do not, because when we started, it was kind of a little less than a year ago. There were several examples, like providing iris dataset to ChatGPT, and it was able to perform the classification on the inference stage, providing some examples and improving the quality of the answer a lot. So we tried to make a little bit bigger overview, including a couple of different papers, different approaches, to actually approve or claim that it's not learning during the inference stage. So yeah, we're not trying to provide any novel, I guess, result in terms of its astonishing result. We're trying to actually a little bit more formally prove that no, they're not learning yet.
Okay, thanks a lot. I guess it's time to thank the speaker again and close the session. Thank you, Radoslav. And now, yeah, I step down to leave the space for the closing session.
Thank you, Andrei, for chairing. And now we proceed to the final and still very important part of our conference. Which is try to summarize what we achieved and what were the main highlights. So this is 11th edition of AIST conference. First of all, we're very glad that many people made it offline, and many nice and really high quality talks were presented during these 2 days. And the first nomination in the natural language processing area award goes to Anton Alexeyev, Sergei Nikolenko, Gulnar Kabayeva for their work on Kyrgyz language. So with this, I would like to please Anton to come and to make some short 1-minute presentation and highlight their work. So, but first, let's.
Well, first of all, thank you for the honor. I guess now I'll really have to continue the research on the topic to make the data set even more fine-grained and more justified. The whole purpose of this work was to create the multi-topic classification dataset for Kyrgyz language, which would and is essentially the first dataset for the applied NLP task in Kyrgyz language. And then the overall idea, why would that be, why such a task, is that there is an urgent need in some dataset to find out whether the multilingual models work for Kyrgyz language. And as we've shown, they do to a certain extent. and outperform the very basic bag of engrams approaches by a large margin. The work is going to be continued, and now for sure, and more interesting works I hope are to come, because during this year and a year and a half maybe, a large community of volunteers in Kyrgyzstan evolved. So this is it, and I'm pretty sure that there will be a special time for that, but may I have some personal remark. I would like to thank the organizers who make the conference happen, who made this conference happen again, and of course our fabulous hosts who managed to do everything like perfectly, despite the trying times.
Thank you. Thank you very much. The next section is computer vision, and awards go to Razan Dido, Andrei Galichin, Pavel Astashev, Dmitry Dilov, and Oleg Rogov. And this is work on deep learning-based bone pathology localization with classification with X-ray images. So I'm not sure whether Oleg is for first time at AIST and arrived just this morning and already got Best Paper Award. So please.
Yeah, this is probably because yesterday I was giving a speech regarding the artificial general intelligence, I believe. Yeah, so I think here all the credits go mostly to Razan Dibo, who is now the PhD student of the Tensor Networks Lab at the Skoltech. So we all know that attention is all you need, but sometimes you have to look only once. So we decided to combine these approaches, and eventually we found an architectural approach to address a very important medical task of child's wrist trauma detection in hospital. We eventually got past the preclinical trials, and we developed the approach that combines the state-of-the-art approaches in the object detection, gradient attention mechanisms, and the shifted window block in it. So, well, I think that as once Andrei Kolmogorov said, that really new things lie in between something trivial and something incomprehensible. Thank you.
Thank you very much, Oleg. The next award on social network analysis goes to Sergei Sidorov, Sergei Mironov, and Alexei Grigoriev on a work on limited distributions of friendship index in scale-free networks. Please. Please say a couple of words about your work.
Thank you. That's a big surprise for me. Thanks, organizers. Well, friendship index was studied a lot in the social studies, but what hasn't been given enough attention in network analysis. So here we did some extensive research on friendship index, and it's a continuation of our work. Well, we've studied a lot of distributions, how it's distributed, what its limits are, and well, actually, I think now it's time to put friendship index away and move on, because it's not a great measure. It's not a all-solving one, but I hope this. I hope you like my talk, and all this topic is.
Thank you very much, and congrats once again. So the next talk is on machine learning, goes to Vladimir Berikov on ensemble clustering with heterogeneous transfer learning. Vladimir, say please a couple of words about your work.
Thank you very much for
it's a lot. It's a bit surprising for me. Yes. So this work, the idea of some additional information which can give some insight to the analysis of data, of target data is used, and the algorithm is based on finding some useful meta features, and data from both domains are quite different. The features are different for the domains, and we should find some structural properties of data and transfer knowledge from one domain to another domain. Thank you very much.
Thank you. Last but not least, last award goes to Dmitry Ignatov on his theoretical work on asymptotic coefficients for the maximum anti-chain of partitions and related counting inequalities. And I really hope that Dmitry will decrypt now what his contribution is.
Thank you. This is a bit unusual being an organizing member and receiving this kind of award, but I always wanted to contribute with this theoretical section with something worthy, and it was a pleasure for me that the committee evaluated my work by its scientific merits, and I was also happy to apply data mining and machine learning techniques to the problems that were posed by such eminent mathematicians like Giancarlo Rota, known in combinatorics, Ron Graham, Harper, Canfield, and Kleitman. So here I just added one small brick to our knowledge on the number of maximal anti-chains and anti-chains of partitions in particular, and also somehow help to reduce uncertainty in some asymptotic coefficients. So thank you.
Thank you, Dmitry. And let me now say once again, great thanks for our hosts. We all heard probably about Armenian hospitality, but now we certainly all experienced the best of it. And this conference, this event would not happen unless Habet and Amalia would do so much during this half a year or more. And first of all, thanks for just proposing an opportunity to host the conference and providing all the resources and all the support and our every need. So Habet and Amalia, let's thank them and Computer Science and Engineering Department of AU. So thanks a lot. Thanks. And of course, thanks for all our supporters from Skoltech, IRI, Mises, High School of Economics, those who basically contributed time of their people or other resources to the conference. So with this, I'm glad and a bit sad to conclude this edition of AIST. And I hope to see you next time at the conference. Stay tuned when and where it will be, and we be sure that we're working to make it happen next time.